Everything.
I do.
I
don't mean the work, I mean the weather. Yeah, a bit.
So you know, maybe more than I do.
Maybe.
Certainly more than I
That's
do.
really good.
Quello là. Io incolla, sale, finestra, nulla di silenzio.
Hard. Locality is
Go again.
Flavio,
Go again then.
Flavio, Alt F4. No, sto scherzando.
No.
Sto scherzando.
Go again, go again.
Forse F1, prova F1.
No, go again. Go again on the
It's the only time in the week. Here that I was learning QFT. I explained you a bit of it. I was using the notes of this. Yeah, it's look.
Flavio, prova Ctrl L. Ctrl L.
No, it's.
Yeah.
Because they changed the new double format.
Alright, welcome back. Talking about scattering paradigm, quantum measurement causality in QFT, please.
Okay. Thank you very much. I really want to thank the organizers for this invitation at this very nice workshop at this very nice location. And I want to thank you for coming back to this room after such a long day. My talk is basically unnecessary at this point. I should also clarify once again that unfortunately I'm not a historian. And I was just very lucky to have friends who are historians of physics and collaborators like Turing, who is a philosopher and historian of quantum field theory. We have done together some work that I will talk about in the first part of this talk. So it's going to be hopefully a refreshing historical introduction to this topic of measurements in quantum field theory at this time of the day. Or I will manage to make you fall asleep. And well, let's see how it goes. It's going to be an immature, non-exhaustive historical introduction to the topic. That's what I want to clarify. Okay. So, well, when we first started learning quantum field theory, we really formed the impression that quantum field theory is indeed a theory about scattering processes. So the question we wanted to ask is whether this is really the case. Is quantum field theory a theory about scattering? And the most interesting question from the historical perspective is how did quantum field theory get established as a theory about asymptotic scattering? In fact, standard predictions in quantum field theory take the form of asymptotic scattering amplitudes. But that's not exactly enough for defining and describing finite time processes, or more generally, local processes in space and time, like is relevant, for example, in quantum information. And for the longest time, quantum information was not really intersecting so much with QFT. But now we're all wondering, how can we really formulate local measurements in quantum field theory in this way? So I will talk about the applicability of the scattering paradigm, but for describing local QFT measurements, basically the finite time estimative type of picture for certain effective models for QFT measurements that I have worked on. And then I will analyze causality issues like impossible measurements for these type of models, and I will discuss the limitations and what can be said beyond this treatment. Okay, so our starting point for this note that we wrote with Doreen Fraser, as I said before, for a very nice special issue that was bringing together physicists and historians. So our starting point for this note that we wrote recently is that this work by Bloom, Alex Bloom, describes this a paradigm shift, as he calls it, from instantaneous or stationary states, as we're like familiar with from quantum mechanics, to asymptotic scattering amplitudes in QFT. And he asks for an explanation to the following striking fact that relativistic QFT is so readily formulated as a theory of scattering. And indeed, this kind of treatment was very important even for the establishment of this theory as a physical, consistent physical theory. And he's asking in what sense is QFT really a theory of scattering processes? And in what sense it was just like contingency that somehow scattering problems prevailed in the history of QFT, or it follows from certain philosophical biases, perhaps. So this question was our starting point, and we wanted to contribute a partial answer to this question based on recent developments in quantum field theory and local measurements. Because what is interesting is that in parallel to this establishment of the quantum field theory as a theory about scattering historically, in parallel to this establishment, there were several episodes in the history of QFT where people were actually trying to describe local measurements, were worrying about causality and all that. So we started from the 1930s because this is when the famous debates about quantum field measurability took place. Coincidentally, this is also the beginning of the measurement theory as we use it today, the work of von Neumann. So yes, we revisited some work of Bohr and Rosenfeld, two papers in the 30s and the 50s. And there is a lot to say about the algebraic tradition of operationalism. Work by Herwig and Krauss later in the 70s, and developments in quantum field theory on Kerr spacetime that enforces more of like this local perspective in QFT in a way. Then comes quantum information, relativistic quantum information, until, well, the famous impossible measurements proposed by Shorkin, and all this work that somehow arrived today, and a lot of people have developed many different approaches about how to tackle this sort of like causality issues in local measurements. So all these people have been asking this question: which local operations or measurements are possible in QFT? So this work, actually, this history note that we wrote, came out of this other longer review paper that we wrote with Doreen Fraser, that was very kindly advertised in the previous talk. So while we were writing this review paper, we saw that there is a lot of interesting stuff to say about the history of the topic, and so we split this in a separate note, basically, to not... So in this review paper, we recommend that we can view these impossible measurements as a no-go result, because philosophers like to spell out the premises that go into this kind of argument. It's not really a theorem or anything, it's like just a no-go argument in which you don't really prove the conclusion, because even the premises are a little bit just intuitive, not really formalized all the way. You set the premises, and then based on these premises, you generate examples that lead to the unacceptable conclusion. And then all the different responses to this problem can be categorized with this in this structure. So I'm not going to go through this because basically in this conference we have already heard about all different responses to this problem. But instead I'm just using this no-go result as a starting point for going backwards, like to do like historical flashbacks about each of these premises that I put here. So, for example, the first one is about associating local field degrees of freedom over regions rather than points. The second one is just some notion of dynamics, some notion of ideal measurement theory for relativistic quantum theory that we also heard about exhaustively in the previous talk, which is basically the standard rules imported into QFT, plus some extra notion of partially ordering of spacetime regions that you need in Minkowski spacetime, microcausality, and yeah, the conclusion of the impossible measurements is that there can be superluminal dependencies between region 1 and 3. Okay, so regarding the first point, So, okay, this debate about quantum field measurability in the 1930s was based on this debate between, on this like so-called small war of Copenhagen that was created, that came after this work of Heisenberg first. So all this debate had a lot to do with uncertainty principle or complementarity. So Heisenberg was the first to try to actually extend this principle in relativistic setups. And then he was trying to argue that somehow, whatever this new theory is supposed to be, the quantum field theory that was not a thing yet, whatever this theory is supposed to be, somehow the uncertainty principle and the limitations on quantum field measurements are not going to be anything like more severe. There will be basically, they will be following just from ordinary uncertainty principle. Then Landau and Peirce challenged this in a paper in 1931, and they argued that indeed the limitations on quantum field measurements are more severe in QFT. And that had to do basically with how do you even measure, like arguing against this concept of field at a point, associating quantum degrees of freedom with points. But then Bohr and Rosenfeld responded to this, challenging their assumption that electrically charged point-like particles can actually be used to measure the quantum field at a point. And interestingly, they argued that one must consider spatially extended, macroscopic charged test bodies, macroscopic in the sense that the atomistic structure can be ignored, and whose charge density can be adjusted, and they propose some kind of mechanism through which whatever back reaction you have is compensated for, and somehow you can say that some measurement on the charge body corresponds to a field measurement. So this point of insisting that this kind of like test body that measures the field has to be macroscopic, of course, it's in line with like Bohr's view on quantum measurement, that somehow like measurement outcomes have to be classical in some sense. They reside at the macroscopic level. Yes. So so there was a lot of back and forth about this very basic point, whether quantum fields make sense at the point, if they're measurable at the point, or if we have to smear over regions. Then when we decide, okay, somehow this was a little wrong, but the other point that I want to talk about that's only briefly mentioned in the papers of Bohr and Rosenfeld is the issue of causality, because somehow when you consider the commutation relations that the field satisfies, and you say, okay, do I actually have microcausality, statistical independence in spatial separation? So even today, the operational interpretation of microcausality is not clear unless you actually have a measurement theory on top of your QFT. And this is a point that is stressed by Rich. There are protocols that you can imagine in which somehow addressing this spatially separated degrees of freedom, this notion of like relativistic locality can be associated with statistical locality in the quantum information sense, and this is a nice recent work by Papageorgiou et al. But overall, and this is why this is explicitly a premise in our no-go result, in a general setup of measurement, microcausality is not going to be sufficient for blocking this certain type problem. That's one of the models that you need more structure. And where does this more structure come from? It can come from dynamics. There are other dynamical notions of causality. Microcausality is rather more of like is characterized in a nice paper by Ehrman and Valente as a kinematical condition. It just splits the degrees of freedom in a way. But then there are other dynamical notions of causality, for example, the local primitive causality or the time slice property that we saw also in Christoph, that can really play a role in the causal behavior of our measurement theory in QFT. So microcausality is not going to be enough, and this intuition that space-like separated subsystems are independent is just an intuition. In most cases, it doesn't give this notion of subsystem locality that we would like to Okay, then what about ideal measurement theory? There were several attempts. Of course, like the first thing to blame for this type of problem is the state update rule. Maybe the state update rule doesn't satisfy the like-cone structure, so to say, of the theory. So there were early attempts in the 1970s by Hellwig and Krauss, where they propose an ad hoc modification of the state update rule in a way that it's made covariant. So, and it satisfies the microcausality assumption. Of course, this is also not enough for, like, let's say, you just use the state update rule. Do you take the circuit type problem? In general, yes, because it's not an issue of covariance. It doesn't rely on the premise of covariance. It relies on issues that have to do with how operations or the dynamics of the theory can enable signaling between specially separated regions. And in fact, this more kind of like dynamical treatment of the measurement was worked out in a series of other two papers by Hellwig and Krauss, 1969-1970, where they say that this operation that we want to have, something like we'll use the state update, it will be a change of state that is brought about by some kind of apparatus that we have to couple to the system, to the quantum field. And this is modeled using a unitary finite time S matrix interaction between some apparatus that they don't specify at first and the system. So, in fact, it's actually quite curious that the Krauss operators that are so famous and so popular in quantum information first appear in this context, this like relativistic setup. What they emphasize is that this type of result that they get relies on just mathematically possible. The goal is to formulate mathematically possible operations, and of course, there would have to be a more physical approach that would single out how do you prepare the apparatus, what kind of apparatus you should have, and so on. So, and they make a comment about the algebraic approach. They say that this type of approach could be used to formulate within AQFT an actual requirement of what kind of operation is local over a bounded region, which of course we know today that this type of approach is possible thanks to the framework by Huster and Ver, which is in this kind of spirit, because in fact they point out that this kind of like assertion of algebraic quantum field theory that somehow the local algebras correspond to what is roughly measurable inside the region is just like an assertion, and there's no real like procedure to understand how to actually spell this out. And in fact, when you go to papers by Hagen, Caslav, you see that they too are mostly talking about scattering in the end. So this is the kind of point that they make already in the 70s. And yeah, it was not fulfilled until very recently. Okay, so all of this was to say that, in fact, if we want to import some notion of ideal measurement theory to QFT, we're going to have this problem. But then when we start thinking more carefully about the role of dynamics, these two premises together form, like, if you want, some kind of like more dynamical finite S matrix type treatment of the local measurements that in general are by definition not ideal. So it's like saying that you shouldn't assume ideal measurement theory, but actually figure out the details of how you dynamically implement the measurement. So the dynamics has to take this into account. And this can somehow block the conclusion completely, or at least approximately. So in fact, in this type of like paradigm, in this kind of like scattering, local scattering framework, we have either approximate or exact resolutions of impossible measurements. We analyze this issue in the context of unrotative type interactions, and this is what I will also talk about in the rest of the talk. So the open questions, though, is that, okay, as we discussed in the end of the previous talk, somehow these familiar rules of ideal measurements should be retrieved in some kind of limit that is not clear. And the question is, how close can one get to ideal measurements without violating causality, basically? And then another issue is that, okay, when we talk about the physical picture of the measurement process, for example, what is actually being measured, we might want, at least in some cases, to appeal to the concept of a particle, something like particle detection, which is also what these Unruh-David type models were initially designed for. And is there really any regime in which the causality is the causality of the model is intact, but also you can retrieve something like particle-like phenomenology? So there is a certain friction there. So yes, it's not like easy to distill a complete physical pictures in cases in which we care about particle detections and things. And I will go back to this point later on. Okay. And one more reminder about the impossible measurement topic, or like example, and I will reintroduce again this type of condition that we heard about, the causality criterion that we heard about in the previous talk, which says that basically, if you have a space-like separated degrees of freedom on region 1 and 3 and some operation in the middle, there is a very nice condition, namely this one, that if it gets satisfied, then there cannot be dependencies between region 1 and region 3. Of course, if nothing happens in between, if this operation in between is a trivial operation, this condition reduces to macrocausality, but you see that it has like this extra feature of composing this operation to the observable 3. And just for the rest of what I'm going to say, keep in mind that this I call condition S from, I don't know, Sorkin, and M is like just macrocausality. Why do I say that this is an ad hoc condition? I say this in the sense that it's model independent, so it doesn't really tell you how to actually implement dynamically the measurement, how to model the apparatus, how to induce this operation. But it also means that it has to hold, if you don't want this causality violation, this condition has to hold no matter what. So whatever proposal you have for your measurement theory, then somehow this is an ad hoc criterion that has to be met in one or the other way. So we'll discuss this condition in the context of Unruh-David type interactions. And this is basically the only thing that hasn't been really explicitly discussed so far in this conference, I think. So okay, I will define state-updated induced observables for Unruh-David type model. Then I will discuss the causal factorization of the local scattering maps. I will discuss this extra condition that we impose for the induced update map to block impossible measurements and whether this is satisfied or not and why not and all that. And then some interpretation of the result and some open questions. Okay. So this is selective state update and this is non-selective state update. So what do we have here? We have that the state starts from some, the field starts from some state rho phi, and then some scattering matrix S that here in this little sketch is like supported in this coupling region of the field to some apparatus. That's just general so far. So given the outcome I, which correspond to some eigenbasis of the apparatus, we can derive, and this was done in this paper here, basically the P of n elements that update the state of the field. This is a selective state update. These P of m elements are actually these operator valued, if you want, transition amplitudes between the initial state of the detector and the final state of the detector. It could be an energy eigenstate if you want the detector to click to detect something like a particle. So this is this has the P of m element properties. And this S will be something like a time order exponential of some interaction Hamiltonian that's supported over this region. Of course, if the detector is, the reading out of the detector happens in the generalized out region, which is everything but the causal path of the interaction, when the coupling is off, so reading out of the detector cannot really have an actual physical effect on the state of the field. The state of the field is global, is what it was. So in fact, more of like an epistemic interpretation of this state update seems to be suggested. because you basically, by reading out the detector whenever you want in the out region of the coupling region, you infer information about the state of the field. You don't really change it or collapse it. So for non-selective measurements, because that's a tricky point, but for non-selective measurements, we don't even have to care about that. Because we sum over all possible outcomes of the detector system, all possible energies, for example, whatever that is. And we can see with like simple manipulations that in the end we're simply left with the effect of the dynamics, like the effect of this local scattering map on the state of the. And of course, okay, it also has a dependence on the initial state of the apparatus. But we don't have to worry about outcomes or anything like that. And I can associate this non-selective update state of the field with all the out region of the coupling region. Okay, what about two successive scattering maps? When you have an actual model for an interaction between some apparatus and the field, you actually have to check if something like a causal factorization holds or not. In general, it will not hold, but for certain types of model, it will. So in this work with José de Ramón, who is in the audience, and Eduardo Martín-Martínez, we derive this causal factorization property for this type of scattering maps, where the interaction Hamiltonian is basically given by some kind of like detector current operator, coupled to the field over a region that's singled out by this spacetime Smith function. So what we show is that, okay, for causally orderable interactions, which means that B intersect the causal path of A, what do I do? You're back.
If it's not plugged, then it dies. But,
It is plugged.
Is the block turned on?
I think he just plugged this one in. It was not fully plugged in. Now it's okay.
Okay, so it's relatively easy to see that if you have this type of causal factorization, then for space-like separated interactions, you also have that the scattering maps commute, which leads to the conclusion that there will not be faster than light signaling in space-like separation or retroposition in bipartite scenarios. And this is just for bipartite scenarios. Then we have to worry about more than two regions and for this higher order causality constraints on the scattering maps. Okay, the condition that we derived for the sorting type problem to not happen is that, okay, it's not sufficient that expectation values are unaffected in space-like separation. Basically, what you want to impose, and sorry, I speak a bit faster because my time is basically running out, is that a local kick over here will not be propagated to region B through some operation in the region A when you model them in this particular way. So the additional condition that we impose on the scattering maps is this one, and here I'm missing a lot of identities because this is coupling A and the field, B and the field, here, okay, identities, and here I would have. So, but roughly this condition looks like this, just in more simplified form. And the reason why we saw that this fails in general is when the dynamical current of the probe that you couple over this intermediate coupling region is non-local. Is not microcausal over the coupling region. Okay, we want to make sense of this condition basically, and we want to relate it to what we saw just before. If you stare at it for a second, you will start seeing that this thing here in the parentheses starts looking a little bit like, and if you take several traces, suitably defined, blah, 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 this starts looking a little bit like induced field observable over the coupling region B. And this will be basically the map over A, the dynamical map over A, acting upon this induced observable, not commuting with C when this is a causal. Okay, so these are the definitions basically. That what I just showed you can be written in this nested form where these are the definitions. So the violation of this criterion S in this context, this one, shows that due to this non-local dynamics, the dual state update map of a region A does not define an observable in the causal complement of OC here. If we actually assume that this local kick over region C is also generated by some kind of like local scattering map over region C, yes, then I will go to this point and then there is the following observation, because this is basically something that we're currently working on. So the observation is that if you have microcausality, as I said, the causal factorization follows. But if you have this type of property of the local scattering maps, that in more formal treatments of interactions in QFT is known as like a Pogolyubov identity. If you have this, then this condition as follows. But this is not if and only if, because basically this dynamical condition, the dynamical constraints are stronger. Whatever structure you put on top, like preparing the probes or whatever, will only make it. You could engineer this condition to be met, but in general, it's going to be a weaker condition. So the possible operations are very much restricted by the structure of these local scattering maps, order by order if you want. The more regions are involved. Then we want to understand a little bit better, and I have to say that this is a very interesting observation that we want to pursue further, but it was not my observation, it was observation of Robin Simmons. It's something that we're working on with Caslav and Robin. So we also want to understand better what is this failure of local time slice property within this intermediate coupling region. What does it mean more in an operational way? How, in what exact sense, some kind of like ill-defined probe can work as a superluminal repeater in that sort of fashion. Okay, and I'm very much out of time. That's what I want. Well, there are certain limitations to this scattering light picture, because this assumption of compactly supported interactions is basically an idealization. In another work with José de Ramón and Eduardo Martín Martínez, we try to relax this assumption. But the problem is that if we want to go back to some notion of particle detection that is relevant for these type of models, the regime in which we have a clean resolution, a clean like particle-like phenomenology, is basically the long-time regime. The interactions are always on. It's not even like asymptotically weak. So it's exactly the regime in which this scattering light picture doesn't work. And we really don't have good notions of causality for that. And this is a paper with, again, José de Ramón and Anastopoulos that we recently analyzed this friction. Well, yes, there is more things like continuous time measurements that are not directly described in this way. And this is what I will not have time to talk about, but there was a reminder in the end of the last talk that indeed the initial motivation of sorting was to advocate for histories-based approaches. And I'm aware of some treatments of this type of problem in the consistent histories approach that I find very, very interesting. Yes, I just show this here and I will have to skip it actually. But it's interesting that to actually talk about in the very end, it would be nice to draw some conclusions about the measurement problem in theory. So the consistent histories approach brings in some notion of decoherence that can be particularly useful for this. And yeah, overall, existing accounts of like the measurement chains don't offer this type of resolution to the measurement. How do you actually get the outcomes of this? So basically what I was trying to argue for this whole time is that impossible measurements are impossible dynamics, basically. And yes, it's interesting to investigate the role that dynamics plays when you want to actually think about the measurement problem in QFT, because this strict dichotomy between measurement and dynamics gets completely blurry. So we will have to reevaluate even the formulation of the quantum measurement problem in this context. Okay. So thank you very much.
So you mentioned that microcausality is not enough to get subsystem locality. If you have the split property as well, it gets very close. Do the references you mentioned talk about it? Is that the direction that they go?
No, because the references I mentioned are more about the context of like closed models coupled to the
The earlier ones at Diablerets.
So there is okay, you mean this one. There is some work in the context of unroot-David model, which is by Eduardo Martin Martinez, where he shows really when two detectors that are spatially separated are independent when the microcausality condition is satisfied. And the one I mentioned, this is also something that Caslav has worked on, can say a little bit more about it. I understand that this is also about how the regimes of the measurements that you want to it's not about the split property, really. It's just about regulating the regimes in which these degrees of freedom are probed by some kind of like auxiliary degrees of freedom.
I would not necessarily see now in this context of the measurements, but this is what we show is that if you have a scalar field and then you have interaction between the particles through the field, that you can then chop the whole unitary in such a small time instances that at the end you can see this in a circuit picture of a subsystem locality, what people in quantum information show, and then you can prove that you can chop in such a way that you have always bipartitive interaction of the particle and the field and the particle never direct interaction for the purposes of the PMV Boson-Letovedral proposal to show non-classicality.
But I'm definitely more interested in understanding a little bit better in this context the role of split property, and I think that this is one slide that I actually skipped, which is that in which cases these actual local unitaries, due to the split property, if I understand correctly, somehow correspond to global symmetries that work by yes. I'm showing the wrong slide again somehow. I don't know why.
One away from where you are now.
Okay.
There.
Right. Okay. So I don't understand very well. This is a consequence of the split property what they're proposing here. That basically you might think that you're doing a local unitary thing over here, but basically what you're doing is the counterpart of a global symmetry, somehow thanks to the split property. But so I just take it as motivation that and that's also how they explain it, that I think that if you have this is more like a kinematical property, more like as a passive transformation, but when you actually induce these transformations dynamically, they're like active unitary transformations and they cannot fall into this category of this. So there's definitely going to be in this story consequences of the split property, and that's already a point in this direction, in this formal treatment. But in this level of having a particle interacting somewhere, and I don't think it goes all the way down to the split property basically.
There's Miguel and Valentino. Let's start to be short, please.
So this is about the unroot detectors. So, yeah, if I understand correctly, so you have this model, right? It's very general, and then you work out in which situations you don't have signaling, right? I mean, we have several unroot detectors in different space-time regions, no? Or okay, but the conditions you got seem to relate the three or the two of them, right? I mean, that you have. And my question is, did you come up with some set of conditions on the interactions such that no matter how many unroot detectors I put out or where I won't have signaling?
And that's the other point that I keep. In general, no. So you cannot say no matter how many, no matter what the configuration, because when this thing is violated, the only thing that this wouldn't be violated is that basically the interaction in between is point-like. So basically, this non-locality that you have due to the current doesn't have space-separated points to be linked through this non-local current, right? So if you have like something like a point-like detector that has other problems, but at least you avoid this. In general, you will have this issue with these effective models. And then when you try to actually put down the scales, because we also worked out what this condition looks like in perturbation theory for weak couplings, then you want to have some assumptions about the coupling strengths of all the detectors and some assumptions about energy caps, masses, like all these like physical things. And in general, this constraint will depend on the full scenario, which is what I think is also very puzzling because it becomes like suddenly a global constraint. So then this question of what can I measure here through this process, no matter what is going on around, is ill-posed.
No. That's not what I'm asking. I'm saying, could you give some restriction on the set of possible interactions, such that no matter how many you have, you don't get a signaling? It's a different question.
I would say
because you could take trivial interaction, and of course you don't get signaling, right? But it's not very interesting.
Yes, yes. If it's trivial, yes. But if you want to define some degree of violation of this and quantify it by means of the physical scales of the problem, the physical scales will correspond to the full scenario sample because of the non-locality that links it all together. But we can discuss more.
So I'm asking a very naive question because I'm having a little trouble following how people think about this. This is not particularly to you, but it comes up here and some other things. So there's a question you asked, which is QFT just scattering? You answered at the end, yes and no. This is kind of an odd question. I don't quite understand the question. If it were just scattering theory, you'd say, well, it's not a very good theory. Quantum mechanics wasn't developed to explain scattering. It was developed to explain spectra. There are a whole bunch of other things than scattering. There was a moment when people thought by S-matrix theory they could kind of forget about what the actual interactions were and just go to asymptotics from states before to states after, but that doesn't look like any kind of fundamental theory at all. That's just ignoring, near field effects. It's ignoring all. So I don't quite understand the intellectual orientation of asking a question like that. It seems like the answer, yes, QFT is just scattering theory, would be a disaster for QFT. And the other thing I don't quite understand, I keep getting the sense people here keep putting in no signaling as an axiom and then are back forming what has to be true to avoid signaling. And that seems to be also the wrong way around. I mean, shouldn't you be building models of physics and then asking them whether you have signaling rather than deciding ab initio you can't have signaling, especially in the light of violations of Bell's inequality? So I'm just trying to understand the way you're thinking about what this work is about.
Okay, for the second question, if I can say something briefly. Well, here the spirit of these effective models, I think, is in this direction. That, okay, I have some light-form structure of the spacetime that ideally I would like to respect the way I formulate the measurements over fields that are defined on the spacetime. And then you check if these measurements, if these models for effective interactions of probes with the field actually satisfy this light-form structure of the spacetime.
When you say you'd like to respect it, you mean by a no signaling theorem?
If there,
I'm trying to understand what kind of respect it is.
Yes, because if distant detectors can see each other through these interactions, this is problematic.
Why?
Because it's incompatible with the light-cone structure of the space.
Why isn't violations of Bell's inequality problematic in that way? We know that occurs in nature.
Yeah, but this is not about signaling. So
that's what I'm trying to understand.
Okay, that's a bigger discussion. And about the first point, well, yes, I mean, yeah, it would be quite restrictive if you said that QFT is all about scattering. So this is what we're kind of like trying to push against. But then indeed, within the scattering paradigm, with generalizations of the scattering paradigm, you can model local measurements. But of course, this is not the only way to do it, I would say. So that's the partially yes, partially no thing.
Okay, let's thank Maria again. Part of today is it's over now. We have 2 short talks on advertisement on our sponsors. And we have Valentino Jadrisko from Constructor Capital, who's going to give us a presentation of how we can relate to them.
Good afternoon all. It's a pleasure to be here among fellow physicists. I'm Valentino. I work as an associate at Constructor Capital, which is a VC firm, but today I'm going to give you first some intro to Constructor Group and the Constructor Capital, which is a VC firm part of it. And how we do investing in quantum companies and what we have learned so far. Okay, so Constructor Group is a global institution founded in 2019 by Sir Bell. Basically, first he started by founding Schaffhausen Institute of Technology in Switzerland, and after that he also acquired the biggest private university in Bremen, Germany, previously called Jacobs University. After that he put this under one umbrella called Constructor Knowledge, and this is the entity which offers basically bachelor, master, PhD level education, as well as aiming towards leading research. So this is the first entity. In total we have 3 entities. The second entity is basically Constructor Technology. It's a tech firm offering products and research in space of educational technologies, AI, and this is something which Alexander will talk more about it later. The Constructor Capital is basically in the middle of this, trying to offer support to both of these entities. First, I'm going to start with our strategic advisory board. Here you can see that we have a majority of the people here are top leading scientists in the world, and 2 of them are also Nobel Prize winners, and among them we have 5 quantum physicists. This is to say that we're quite embedded in the scientific community, and we are trying to put great efforts in listening and of inputs we get from them, and trying to get closer and more aligned with the joint goals.
Was it many of the
These are
darker borders?
These are the quantum physicists.
Oh, okay.
Yeah. More about Constructor Capital, which is a VC firm. What is a VC firm? It's a venture capital. It's a type of investment fund which invests in startups. So we have 3 main investment areas. The first one is the software that we invest in mainly business-to-business software solutions. The second one is the deep tech. Here we focus on innovations coming from universities and research institutions, mainly in the space of physics, such as quantum, advanced materials, semiconducting, photonics, and so on. And the third one is educational technologies, where we look for software which improves the way we learn and the education space itself. Just to mention that in software tech and both in deep tech, we are also looking at AI stuff, which is very popular today. We have basically 5 main partners. I will start with Sir Bell. He's the mostly known. He's our co-founder and chairman. He's mostly known for starting Acronis, Parallels, Acumatica, and 2,000 other global IT companies across the world. Matthias Minter, he's ex-McKinsey, senior partner there, spent 26 years, and he's our managing partner. It's interesting to say that among our partners, we have 2 physicists by education, and in total, among our team, there is already 4 of us who are physicists. So we are early stage focused, meaning that we invest in pre-seed, seed, Series A, which means basically we go from the beginning towards, let's say, some later phases, let's say 5 years old startups, meaning our ticket sizes when we invest, check sizes are from $100K to $5 million. I believe I mentioned everything I need to this on this slide. Yeah, maybe, yeah, it's a $150 million size fund. So this is the size of our fund and how our ticket sizes, as I said, are going to up to $5 million. So we are completely geopolitical agnostic. We have partners ranging from different nationalities, from Singapore, Switzerland, India, and Cyprus, totally abiding the neutrality and inclusiveness of today's world. We have no geographical restrictions when it comes to investing, so we can invest all over the world. Usually it means that our 70% of our portfolio is under 8 hours flight from Zurich, our headquarters, purely from logistical reasons. That said, we are trying to leverage our non-restrictions of geography in our investments and trying to find the most attractive deals all over the world. As I said, our headquarters are in Zurich, but we have presence worldwide, and we have actually official opening in our Abu Dhabi office next week. So we are able to spread around. But it's also interesting to say that we are a completely remote working team with team members in Germany, Italy, Switzerland, Croatia, Cyprus, Abu Dhabi, Singapore, and India. In addition to just offering money to startups, which is their primary goal, obviously, to get money from us, we offer extensive access to our network of world-leading scientific institutions, and also business networks of leading companies. And that's to say that for companies and startups, it's not sometimes it's as important to get money, but also to get access to network, because it gives them higher leverage and higher ability. In recent decades, we have seen quite big improvements in technological and changes on how we are doing business and how we are living, basically from internet era by today's giants of Google and Meta towards online space, guiding the customers towards offline brick and mortar stores, to today's exponential rise of AI led by OpenAI. But we strongly believe that the next thing which is going to happen is quantum computing. We are not sure when it's going to happen, because we're still in the phase of getting to the quantum advantage and practical usefulness, but we believe we are on the path towards it. That's why we are strongly focusing on it. Today, we are seeing already many quantum computing companies claiming that they have some kind of a product running quantum computing platform. Usually this means that they boast themselves with number of physical qubits. Unfortunately, the physical qubits are not offering us commercial or practical use which we are expecting from quantum computing systems. Recently, QuEra, a neutral atom-based quantum computing platform, published an article where they showcased 48 logical qubits. But to get to any kind of usefulness or to start talking about quantum advantage, we really need to get above 100 plus logical qubits. Hopefully, this is something which we can see in the next 2 to 3 years. But here you can see how many logical qubits you need for certain different applications. It's very hard to get logical qubits, and there is, let's say, a ratio of 1 to 7, depending on the platform, between physical and logical qubits. And regarding our investment criteria, so our team has invested in more than 20 companies, quantum companies, in the last 10 years. So here we set up some criteria which are not obviously the ultimate truth, but we hope that they can help in making decisions both for investors and founders. First of all, what we look for is a solid research background. We want founders to have a clear, let's say, evidence of the research which is leading towards the product which they're marketing that they can build. Meaning that we want to see papers, citations, age indexes, embeddedness in the quantum communities, awards, presence on conferences, and so on. The second one is embedded leadership in chief scientific roles. Too often we see that the main researcher or PI or professor develops something, and then their postdocs or PhDs go and start a company, but the professor or PI stays on the sideline, not really being hands-on on this. He's his advisor 1 week, once or twice a week there. We don't want this. We want them to be fully present there, fully hands-on, because in the early stages of these kind of companies, we need technological and scientific advancement, which is needed. For this, we need all the possible effort from all the talent there is. And also it gives much more credibility towards this company from perspective of us investors, that we see that everybody's all in. And the second one is capability of securing non-dilutive grants. So this is the public grants, and this, as we can all know, that research is very expensive, equipment expensive. So we want to see basically one by one. So if we have a $1 million private investment, you want to have at least 1 million of non-dilutive private public grants. This is making the business case more attractive also for founders, because they keep more of their company, and also for us investors. The fourth one is the setting of realistic product and financial targets. Unfortunately, too many companies go and say they're gonna change the world, and this is non-realistic, because it's not. They need to go and be realistic in towards saying how much money they will have and what they can achieve with this money. So this is in regards with what is available to them, but also in terms of what is the state of the art. They cannot claim that they're going to achieve something which is orders of magnitude better than what we have today. This is in terms of product targets, but also in financial targets. They claim that they can get to revenues of 100 millions in 2 to 3 years, but this is never gonna happen. The fifth rule is basically leveraging university and laboratory networks. We want these startups to be embedded and physically close to universities and research labs. As I said before, it's very important that they have access to labs, then the costs get lower, and also they need to have access to top talent, and top talent is usually around universities and network hubs where there's PhDs, postdocs, and so on. And the last two are more general one, which we also apply to other kind of companies which we invest, is unique product value proposition. So basically we want the startups to have at least 10x improvements in the product, which at least in one area of the product which they develop. And the second one is we are not just a VC firm, we are bigger than, we are a group of things, and we want to leverage this and then obviously we need to be on the same side as other startups are, and then that they want to have us being more on hands-on. I'm going to go towards a little bit explaining our current portfolio. So basically in our current portfolio we have more than 15 companies. Big part of them are deep tech, and 4 of them are quantum-focused companies, but not just. So there is also AI, computing, optical computing, and AI-based research for materials. And here I'm going to finish with...
Acronis is not part of it?
No, Acronis is a much bigger company, like $4+ billion. So it's our team is embedded with them, but there's much more. Yeah. So Quera, this is one of the companies, is like the biggest, let's say, our leading company in our portfolio. It's a neutral atom computing platform based out of Boston, and it's founded by top scientists from Harvard and MIT. Basically, they're already able to, and they already have a product online, which is a 256 quantum qubits quantum computer available on AWS cloud, basically. And they have, as I said before, they have showcased 48 logical qubits, and they have a clear roadmap, product roadmap in developing 100 qubits. Logical qubit system in the next 2 to 3 years. Another interesting thing for them is that they're most cost-efficient company. So they have the most results for the least amount of investment. It's also worth noting that we're the biggest investor in them. The second company is a quantum computing software company. So in quantum computing, we're not just seeing hardware companies, but also software companies. There's a clear need also for this, because as hardware is developing, we need software to control this hardware. It can be firmware, middleware, or direct application layer. Also, Kurus here is a German-based company which is developing software for accelerating research and lab experiments. Basically, we understand that operating quantum computers can be manpower intensive, and there is a need for software improvements and automation. The second two companies are in the field of quantum sensing. So Kunami is a Swiss-based company leveraging nitrogen vacancies in diamond atoms for use in magnetic sensing in materials. It's basically a research from University of Basel. These kind of companies are much closer to achieving commercial success, as the main efforts are among product development and technological improvements. And the last company is also nitrogen vacancy diamond atoms, but now focusing QDTI, focusing on biomarker detection with the goal of accelerating drug research and biological diagnostics. So basically, they're able to go up beyond the current problems of background from in optical detection. And this is also founded by guys from Harvard, Chicago, and other universities in US. With that, I'm finished, and thank you for your attention, and I'm open for questions.
So I would
will ask was some short question to ask now. Otherwise, we will have plenty of time during there will be a refreshment afterwards. Valentino will be here only tonight, so I ask whoever has interest in talking to him about what we just said to approach him during the drinks. There will be enough time. If there are now some clarification, short questions, we're taking them now. Otherwise, we move on. Okay, so I guess we can postpone to the discussion. There is a yeah. From Constructor Technology. Yes, exactly right.
Yeah. In our agenda, the last 2 years, today I'm a constructor, and the good news is that there's going to be only one demo. And I'm going to be as quick as possible because I understand that I'm the only guy who's standing between you and you to have relaxing dinner. And I hope that this product, which we built for researchers, is the most relevant for you for this specific audience. We started building it for researchers who are using computational methods in their research, like machine learning, artificial intelligence. And my question before I start, who of you guys are using machine learning or artificial intelligence methods in research? 3, good, perfect. 4. Yeah, not much, but I do hope that this short presentation will somehow attract your attention and you will think out about using this broader and more actively. So again, I will not be annoying you with some slides about constructor technology and the product itself. I would rather show you how it works. And on specific example, this example is taken from material science, and this research work was done by Konstantin Novoselov group, who is actually well-known, very well-known scientist, Nobel Prize winner, inventor of graphene. And what's the beauty of this article for us, for constructor technology, is that all the computational analysis was done within this research using our platform. And if we scroll down to the very end of this article, we will find here references to GitHub, which is obvious. So any article should have this reference and keep the data in GitHub. But we also find here research constructor link. And if we follow this link, then we drop into the short description of the article, short description of the work which was done by a specific research group. You don't need any account, anything, just to have access to this information. All the data frames, data sets, publications available here. So it's just distributed by link. But the most important here is this button, duplicate. And if you press this button, for this you need account on research platform, constructor research platform, and then systems start immediately recreating the absolute copy, clone of environment that was used by a research group of, in this case, Konstantin Novoselov, with all the artifacts, all the research content, everything, all the data sets, models, etc., etc. So it will take some time. But again, so of course it depends on the complexity of the model. I already have here the pre-installed and pre-deployed environments. And if we go to some environment, we'll find here this collaborative interface where you can check the publications that are related to this article. You can connect any computational resources for your compute. It might be Google, it might be Azure, it might be your university HPC or any other data center. You may create a group of researchers who are simultaneously working on the same project and have access to all the data, to everything, and some can bring data, some can build models, etc., etc. You can find here a beautiful data catalog that allows you to instantly review the results of research in 2D modes. In this case, it's 2D materials, crystal structures, but it can be proteins, it can be anything else, depending on the nature of the project. And then we can also create a link and share this link with anyone else, and then those guys will be able to also open the project and use it or reuse it or modify it depending on which whether you agree to share this content with them. Then if we go to the desk, what we'll find here the description of the project. We will find here all the data that was used. We can modify it. We can work with the workflows. Just build new workflows or reuse existing workflows in environment using our data sets to either reproduce the results of research work or get our own results. And of course, we can review the publications. We can work with the VS Code to do some new stuff and share it with the colleagues, and many other things. So you can use our own compute resources, or again, as I mentioned before, you can use your compute resources that are available to you anywhere. So this is quite powerful, interactive and collaborative environment that allows you to use, again, to summarize, different source of computational resources and work collaboratively on the same project with a group from one university or different universities, or it might be research project, it might be educational project. So you can teach students to deep learning, machine learning, and many other things. So this is very short. I promised you to be very short. Of course, you can try. I'm here till Friday, so you can ask any questions. And if you're interested to try this out, so I'll be here to provide you all necessary information. That's it.
All right. So now, as I said. We have a bit refreshment downstairs and apero at the bar, and dinner is at 7:30. Free time. Let's thank all the speakers of today.
Quite far this direction. I mean, this time it will be colder and hot and snow or whatever. But it means also that most likely, except for those who really want to leave immediately after the sessions, we'll have a standard lunch here, and we leave after lunch for those who want to go for a walk together. Everyone can do what they want. I will still confirm the cancellation of the glacier when I get it, but I can already tell you it's at least 95% chances that we have to cancel it. And then also, if we do that, there is the possibility now that this evening session that we had tomorrow evening after the dinner with Ottfried, Wigner, and Victor who is somewhere here, could be actually put just before dinner, so starting at, I think it means 5:15 or something like that.
Yes, 5:45 until a quarter.
Standard time. Yeah. And so that we have the two lectures, plus the drinks, plus the dinner, plus the like yesterday. So I guess, Victor, where is Victor? Would you agree? Yes. Good. And Ottfried has no choice since he's not yet here. So I guess we do like that in case we confirm the cancellation of the lecture. Okay? And
I will circulate now a piece of paper where you can write, so in case the excursion takes place, if you write if you want to come and if you want a lunch
with you, or you are having lunch at the hotel. So.
Yeah, and if it is cancelled and you still want the lunch back,
yeah,
then go down and ask, inform the reception that you want the lunch back. But I guess most people will just have a standard lunch. Okay, and now we continue and over to the chairperson, Maria.
Okay. So the first talk of today will be by Howard Wiseman, and he will tell us about Turing, Wigner, and Bell.
Thank you, Mary. Yeah, so Turing, Wigner, Bell, the high frontier for experimental metaphysics. So, yeah, so in this talk, as we'll see, is pretty literally beyond Bell, but we'll get to that in this way. So I put up my principal co-authors for this talk as Eric Cavalcanti and Eleanor Rieffel, and I'll see in a minute which papers they are. So Eric and I are at the Centre for Quantum Dynamics at Griffith University here in southeast Queensland in Australia. Eleanor is in Quail in NASA in San Francisco. So we're part of the Centre for Quantum Computation and Communication Technology, which is supporting this work in Australian Research Counter Centre. And my attendance here is partly supported by the Blau faculty. Okay, so there are two papers that I'll principally be presenting the results of in this talk. So one, which has got lots of co-authors, was published in 2020, A Strong Modular Theorem on Wigner-Span Paradox. And the other is one with just these two co-authors, Eric Cavalcanti and Eleanor Rieffel, which was published in Quantum in just last year. Okay, but yeah, let's start with an introduction, which will basically explain why I chose the title, or at least partly explain why I chose the title for this talk that I did. So experimental metaphysics. So for anyone who doesn't know, so metaphysics in the literal sense, the name this comes from because it was the book that was after Aristotle's book on physics. But what was contained in this book was what's sometimes called the first principles of philosophy, fundamental nature of things, time, space, experiencing, things like that, okay? The most fundamental things we can conceive of. But there's another sense that you could understand metaphysics as being the study of physics, in the same way that metamathematics is the study of mathematics, for example. So metaphysics then is a question about what constraints are there on the possible theories of physics. So then what is experimental metaphysics? Well, it's a term that Abner Shimony coined in 1987, or maybe perhaps slightly early, but it was well known from this volume, published in 1987, Philosophical Consequences of Quantum Theory. And yeah, it's got a bit more currency recently. So there's this conference in 2017 celebrating the 30 years of experimental metaphysics, for example. Whoops. Sound good?
Do magic.
Okay, so that's that experimental metaphysics. The high frontier, well, that's where we are, obviously, but no, we'll get to that. So Bell, yeah, everyone knows we're here to celebrate the 60th anniversary of Bell's theorem. This picture, or pictures like this you've seen a number of times. This is the paper. This is from Bell's conclusion about what he'd shown in this paper. The statistical predictions of quantum mechanics are incompatible with separable predetermination. That is, in any theory in which parameters determine the results of individual measurements, there must be a mechanism whereby the setting of one measurement device can influence the reading of another instrument, however remote. Okay, so I highlighted some part there in brown because at least since 2015, if not earlier, we could replace that phrase with the results of Bell experiments. Okay, so I want to make a prediction between this part in black, which I'd say these are about metaphysical assumptions, right? Assumptions about the way, the possible theories, nature of the theories we have of the world, whether the results of individual measurements are determined, whether the setting of a measurement device can influence the reading of another instrument. Those are metaphysical assumptions, whereas the statistical predictions of quantum mechanics, that's an empirical statement, right? And so it's important to keep those things clearly distinct. Yeah. Okay, so that's Bell. Wigner. So the reason Wigner is in the title is because of Wigner's friend. Okay, so we'll get to this. This is an exciting area in foundations at the moment, and it dates back to this 1961 paper by Wigner called Marks on the Mind-Body Question, and it's probably, I think, worth just reading through what he says. It says it's natural to talk about the situation if one does not make an observation oneself, but let someone else point it out. It's the question, what is the wave function if my friend, and that's where Wigner's friend enters into the literature, if my friend looked at the quantum object? The answer is that one could only attribute a wave function to the joint system of friend plus object of this form here, which follows, it's weird, isn't it? Okay, which follows from the linearity of Schrodinger's equation. Then he says, this appears absurd because it implies that my friend was in a state of suspended animation, in other words, in a superposition of these two possible observations, before he answered my question about what he saw. And Wigner's conclusion from this is that it follows that the Schrodinger's equation cannot be linear if it is accepted that my friend has the same type of impressions and sensations as I. Okay, so I didn't call this obviously a theorem. This is just Wigner's personal conclusion in 1961. But yeah, he talked about the mix of. And then finally, Turing. So I'm going backwards or in time this way as opposed to the title of my talk, which goes forward in time. Back to 1950, and Alan Turing's paper in this journal Mind, where he famously introduced what's now called the Turing test, which he called the imitation game. So he starts, I propose to consider the question, can machines think? This should begin with definitions of the meaning of the terms. And he goes on and talks about this. Then much later, he comes back to the original question, can machines think? I believe it to be too meaningless to deserve discussion, okay, just without defining what we mean. But having defined what he meant and giving an operational definition of thinking in terms of the Turing test, he goes on, nevertheless, I believe that at the end of the century, the use of words and general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. And I think this statement of Turing is more true now even than it was in 1950. Okay, that's a joke. Because it probably is not true that at the end of the 1900s that one would be able to speak of machines thinking without being able to be contradicted. But I do believe that at the end of this century, it would be very likely that this will be the case. Okay. All right, so that's the background to the work that I'm going to present. So to give some more, I guess, background, so what are the theorem and results that I'll be talking about were inspired by some early work by Caslav in this paper here in 2018. And so the essential thing which he did, the scenario he produced, was to incorporate Wigner's friends into a Bell experiment. Okay, so it's combining those two things. And in doing this, it's very important to realize that in all of this work, there's an assumption which is completely contrary to Wigner's assumption, which is that it is possible for friends to be put into superposition and that friends do not collapse the wave function. There's also, so I should note, related work, but not quite as closely related, by Renato and Daniela Frakaga, and I think Renato will be talking about something related to that later today, whereas Caslav will be talking about something different. Okay, so that's the background, and then the theorem, which we in the local friendliness theorem, although not in the original publication. we introduced the term local friendliness, but didn't call it that theorem. I want to get to there by, first of all, going back to Bell's theorem. Okay, so now this is a fine-grained version of Bell's theorem. It's based on work by myself and with Eric 10 years or not quite ago. So it's basically, yeah, it's formulated in a way that sounds very metaphysical, except of course for this last empirical statement at the bottom. Okay. So the first assumption is basically a free choice assumption, which everyone agrees, I think, is necessary for Bell's theorem. And the rigorous statement is that if a free choice is correlated with any set of experimentally relevant events, then it's a cause of one of those events. Okay. And I should point out that, right, these words in small capitals, I'm not presupposing a definition for words like, events or cause, but these assumptions in conjunction, because they use these common terms, they lead to definite statements that one can make, even without having a particular definition in mind of what a cause is, for example. Okay, so these are just, if you like, empty categories that get their meaning from the surrounding assumptions. Okay, second assumption, relativistic causal arrow, we call it. It says that any cause in an event is in its past light cone. And you might think that well, isn't that just what Bell called local causality? And the answer is not quite, because maybe I'll skip over one. What is necessary to derive local causality as used in Bell's theorem from this notion that causes have to be in the past light cone of event is what's known as Reichenbach's principle of common cause. Okay? And that says that if two sets of events are correlated and no event in either is a cause of an event in the other, then there exists a set of common causes such that conditioning on their values of those common causes removes the correlation between those two original sets of events. Okay, so that's basically just the principle that, if you have correlations, it must be explained by a causation, right? Either direct causation or a common cause. That's the loose phrasing of it. This is the precise phrasing of it. So that with relativistic causal arrow gives you roughly what Bell called local causality. Not in 1964. But then we have this other assumption, which we call absoluteness of observation, which is implicit in Bell's work, almost everybody's work, until people start discussing, how does many worlds react to Bell's theorem, how does cubism react to Bell's theorem, etc. So there's this assumption of absoluteness of observation, that any observation is an absolutely real event, and by that we mean a single event, okay? And it's not an event relative to anything or anyone or any world or whatever you want to say. Okay? We just don't have to qualify what we mean by observation in that sense. It has a straightforward meaning of what that is. Okay. And then finally, so the actual Bell's theorem then is that we have a contradiction between these four metaphysical assumptions and Bell correlations, right? This empirical either assumption, if we haven't done the experiments yet, or fact, if we have done the experiments and they come out as expected, that the statistical predictions of quantum mechanics for loophole-free Bell experiments, in other words, that they come out the way they have come out, violating Bell inequalities. So I think I already said that. Okay, so that's Bell's theorem, right? So what do we get by including Wigner's friends into the picture? And that's, as I said, that's what's in this paper here. But again, I'm going to be relying on this paper by Eric Cavalcanti and myself for the sort of fine-grained version. The beginning looks exactly the same as Bell's theorem, right? So this is what we call the local friendliness no-go theorem. The conjunction of these is a contradiction, so the first three are exactly the same. The crucial thing, and maybe I should have said this, I wanted to say this back here. Right. different physicists obviously have different ideas about which of these to give up. We know that we have to give up one of these assumptions, and different communities are more partial to giving up different ones, but certainly a large section of the community is the physics community. I mean, would say that this is the one. Reichenbach's principle of common cause is the one to give up, because we know that this is the one that quantum mechanics, the theory of quantum mechanics itself, does not satisfy. Okay, you can argue that the theory of quantum mechanics is compatible with all of the others. I just mean ordinary Copenhagen quantum mechanics here, but not Reichenbach's principle of common cause, because this does not postulate causes for correlations. Okay, so the significance of the new theorem is that we don't use that assumption. We get a contradiction without using Reichenbach's principle of common cause. But the price we have to pay for that, if you like, is that the empirical assumption we have to make is a much stronger one than required for Bell's theorem. Okay, it's not just that we can do experiments with entangled particles at a distance and see Bell correlations, which we know we can do now. So I'm calling it here Bell correlations with superpowers. Okay, and a superpower is the idea that a super observer can approximately at least reverse the evolution of an observer. Okay, or the friend. Okay, so that's a pretty strong assumption. But I want to emphasize that it's not a metaphysical assumption. This is, if you have in mind a particular super observer, as they're sometimes called, and a particular friend, then that's an empirical matter whether that super observer can reverse the evolution of that friend. So I want to make that clear that that's not metaphysical. All right, so how does this work? So this is the scenario that Caslav introduced. We have, begin with two boxes containing two friends. Well, sorry, they're not friends of each other. Two parties, Charlie and Debbie. They might be friends, but that's irrelevant. Okay, they're going to play the role of friends, but in the sense that, let's just concentrate on, oh, sorry, so they're sharing an entangled pair, and we're going to now concentrate on one particular side, Charlie's side. So Charlie, sorry, before we do that, Charlie and Debbie both make measurements of their quantum particle. Now let's have a look on Charlie's side. So Charlie is the friend for Alice. So Alice is a super observer, someone in the role of Wigner, as in Wigner's original paper. And Alice is the one who's going to make measurement choices. Okay, so if she makes a choice, x equals 1, so x is Alice's choice, then she simply asks Charlie what he saw for his measurement result. And she'll write that down as her own record in that run of the experiment. On the other hand, and this is where the reversal comes in, right? If she chooses any other setting, and there could be at least two, there could be more than two settings. So in any other case, what she does is press a button, if you like, which reverses the evolution inside. That's reversible. There you go. Inside the box, so that we go back to a situation where Charlie is now unentangled with the initial qubit, which has entered his box. And then Alice simply throws away Charlie, keeps the qubit, and makes her own measurement on that qubit in whatever basis is indicated by her choice. Okay. Now, so how does that work with the assumptions? So the assumptions of absoluteness of observations, importantly, applies to the observations by the friends. So that means that there exist these variables, A, B, C, D, the outcomes by all four parties in this experiment really exist. So it must be a joint distribution, joint probability distribution for those outcomes, conditioned on Alice's and Bob's choice, X and Y. And so the observable outcomes, which is what the super observers see, can be obtained by marginalizing over the variables C and D. So that's the first point. The second point, we can put together relativistic causal action and interventionist causation to conclude that the probability of Alice's outcome is independent of Bob's setting, because we have this space. Oh, I should have pointed out, right? So this is a space-time diagram. The crossed lines are light, light signals.
So this side is space-like separated from that side in the sense that, right, so Alice's outcome must be statistically independent of Bob's choice, and likewise Bob's outcome and Alice's choice, and also the C and D are independent of X and Y because they're not in the future lifetime of that. So we coined the phrase local friendliness for these assumptions. So the conjunction of these three assumptions, and yeah, we can work out, you know, what the consequences of these are. And so what we find from these assumptions, plus the fact that in this setup, you know, when x equals 1, Alice just records Charlie's result, and when y equals 1, Bob just records Debbie's. So we can take those constraints, grind them through, and derive what we call local friendliness inequalities. So these are things analogous to Bell inequalities, but not necessarily the same as Bell inequalities. For some particular cases, they're the same as Bell inequalities, but in general, they're different. And moreover, what we show is that, that these inequalities then, which we get, can be violated if the appropriate superpowers exist. And what that means is, even in this imperfect sense, as long as the probability for Alice and Bob's result, given that they undo Charlie and Debbie's measurements, is approximately the same as if there had never been the Charlie's and Debbie's measurements in the first case. So that's all that's required. There's no, it doesn't have to be exactly equal, it just has to be good enough for experiment, and then we can violate these local friendliness inequalities, which means we have a new theorem of experimental metaphysics. Okay, it says if we can do this experiment, we can rule out a set of metaphysical assumptions strictly smaller than the assumptions used in Bell's theorem. Okay, and that's the sense in which it's beyond Bell. Okay, so we in the 2020 paper, yeah, so there are a lot of technical details which I'm not going to go into it at all, but we did an experiment, a photonic experiment. We got some results. We violated local friendliness inequality by 17 standard deviations. So wow, why haven't we got the Nobel Prize already? Okay. Well, so the answer is that, so the friend in our experiment was just a single qubit. Okay, in fact, just a path encoding of a qubit for a single photon. So we didn't, that was sort of necessary because we don't actually have superpowers, right? Okay, so we have to do an experiment that we can do, and in the present day. So then that raises the obvious question: can a qubit be a friend? Well, so it might surprise you. Some people think so. There are some people in the literature who put their money on the table and said, yes, this is a real Wigner's friend experiment. But that's not what we committed to in our paper. So we called it in the paper a microscopic proof of principle version of a Wigner's friend experiment. Okay. But then that raises the question, well, how would you do a real experiment? What would make a friend, inverted commas, into a real friend? So we didn't give any definite criteria in the 2020 paper, but my opinion, so I'm emphasizing that, I'm not speaking for all my co-authors necessarily, but I think the most convincing answer is what Wigner said in his 1961 paper. His concept of a friend was a being with the same types of impressions and sensations as I. Now, obviously this is difficult to work with because sentience is something that nobody knows how to judge even, let alone to measure. So as a fallback, what we're going to consider is a slightly, perhaps less controversial thing of thought. Okay? And so now this finally is where we get to where Turing enters the story. Because what we're asking now is, if we can build a thinking machine in the way that Turing talked about, how can we build a thinking machine that could be unitarily reversed as required in the experiment? And the answer for that is an artificial intelligence realized on an enormous fault-tolerant quantum computer. Okay, and so that is what I'm calling the high frontier for experimental metaphysics. Okay, so I'll talk. How's my time going?
You have another 5
Before
minutes.
then? Okay, all right, good. So this is what we talked about in detail in this paper. So we call it a thoughtful local friendliness no-go theorem. Prospective experiment and new assumptions. So I'll briefly, I'll briefly say something about what the experiment we imagine is. So in that paper, instead of talking about Charlie, we talk about a new party we called QualE, who is a human-level artificial intelligence running on a universal quantum computer. So that's QualE's world line here. We need QualE to be able to think and respond roughly on the same timescale as a human. And in this paper, we did some estimates for what that would require in terms of quantum computing. And the answer is, scary even for people who are trying to, run Shor's algorithm, with something like 10 to the 15 logical qubits and a 10 to the minus 12 logical gate time. So not going to happen anytime soon, but I had been telling people that, it's not going to happen it may be future generations who have to realize this, but I had a young visiting PhD student from France who took issue with that. He thought he was definitely young enough and he was optimistic enough about quantum computing to really think that this could be achievable in his lifetime. So I hope he's right. Okay, so the idea is before going into the experiment, QualE would pass a Turing test, as rigorous a Turing test as one would like. And then during the actual experiment, in each run, QualE is going to be making a measurement of a qubit and then either conveying that information to us, and we have a complicated way in that I'm not going to go into, way to set that up to match the assumptions. But basically, either QualE makes a measurement and then that measurement is reversed and Alice makes her own measurement, or QualE just makes a measurement and that information is conveyed to Alice. So yeah, that's more or less what I said there. So I think I won't go through the details here. I should mention my +1, Ela, is responsible for this picture, just to mention her. So Alice and QualE are on one side of a divide here, so Bob is a long way away, being space-like separated, and because the time scale of this is of order 1 second, right, if you have to, assuming that the QualE is acting something like a human, that means that this Bob has to be, on the moon or something like that. So we'll see how that comes into things in a minute. Okay, so that's what the experiment would roughly look like, but what would it mean? So in this paper, we formulated a new version of the theorem, now slightly different, specifically tailored to this type of experiment, this concept of what a friend is or could be. And what I'm giving here is not precisely what's in that paper, but it's a version suitable for this talk. Okay, so the beginning is the same as before, interventionist causation, relativistic causal action. But the third, instead of assuming absoluteness of observations, we're going to be specific and talk about absoluteness of human thoughts. Okay, so that's any human thought supervenes upon an absolutely real physical process in the obvious bounded region in space, in other words, in my head, and time, right, the time that I'm taking to have those thoughts. Then we have an assumption which we explicitly call friendliness, or here, friendliness to human-level artificial intelligence, which says if the client passes an open-ended Turing test, then they have thoughts, and any of their communicable thoughts is as real as any communicable thought of a human. Okay, so that's not saying that those thoughts are real, it's only in conjunction, then it's not saying they're absolutely real, but if we've already committed to human thoughts being absolutely real, then that would be committing to a human-level artificial intelligence also having absolutely real thoughts. Okay, and so those are the metaphysical assumptions. Now the technological assumptions are unrealized at this stage. So one is that human-level artificial intelligence is possible, okay, which we're Not at yet, but I think a lot closer than, it seemed to be a lot closer than we were 10 years ago even. And then lastly, that universal quantum computing can be done, but as I said, at an extremely large scale and also very fast. And then finally, as sort of an afterthought, because I think most people think if we've achieved this, we will have, quantum communication to the moon will have been, that would have been done decades before. But that's the sort of thing which you would need. Okay, so again, I'm not going to have time to go through all these implications, but we talked about in that paper that all of those assumptions, so the 4 metaphysical ones and the 2 technological ones, are all relevant to quantum interpretations in the sense that there has been a seriously proposed quantum interpretation which rejects each one of those and not obviously any of the other ones. Okay, so that's the sense in which they're all relevant. So yeah, so the point maybe just to go back, it's a no-go theorem, right? One of these must be wrong, but we don't know which one it is. And if you look at the range of interpretations out there, or modifications if you prefer, in some cases, then they all reject one of those assumptions. And I think, but the most interesting thing I think is that all the physicists think that quantum theory needs no interpretation I think there are a lot of physicists who would just look at our list of assumptions and say, yes, I believe that, 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 and then, well, then you have a logical contradiction.
Is there a difference between the capital Y's and the lowercase Y's?
Yeah, so the capital Y's are ones that are commitments of the interpretation. The little y's are just are things that the interpretation doesn't particularly say anything about, but for which there's no reason that somebody holding that interpretation wouldn't believe it. Yeah. Yeah, and so typically quantum interpretations don't say anything about human-level artificial intelligence or universal quantum computing, but for example, Penrose does talk about human-level artificial intelligence and says that you can't have it. Yeah. Okay, so getting on to my conclusion. So the general idea of experimental metaphysics is that non-testable metaphysical assumptions can have falsifiable empirical consequences in conjunction. Okay? And in the case of Bell, we can say that these are falsified empirical consequences. And what I am talking about as a new frontier for experimental metaphysics will come from continued advances in AI and probably even more challengingly in quantum computing. And so specifically, if we have these advances, then sometime, maybe this century, we could rule out the conjunction of these 4 metaphysical assumptions of intervention as causation, which is like free choice, relativistic causal arrow, absoluteness of human thoughts, and friendliness to human-level AI. And as I said, each of these assumptions and these 2 here are all at present relevant to seriously proposed interpretations. Okay, I've got another slide about future directions, just saying that this direction for Wigner's friend in terms of human-level intelligence is a long-term vision. In the short term, there are many other interesting directions to explore, both theoretically and experimentally. But yeah, I'm not going to talk about that. And yeah, so having just sprayed that out there, I think I'll go back to my summary to leave that up there. Okay, thank you.
Yep. As you're probably aware, decades ago, David Deutsch wrote a paper called 3 Experiments on blah blah, in which he introduced a conscious quantum computer.
Yeah.
Of course, for anyone who knows David Deutsch's purpose was to prove many worlds, and I wonder how this relates to that.
Yeah. So so we obviously talk about David Deutsch's paper, and I recognize he was very seminal work that he did. Like the same year that he wrote that paper, he also introduced the concept of a quantum Turing machine, more or less. So yeah, it was a pretty amazing year. So yes, I think if so, for David Deutsch would where are we? Yeah, so we have the class of interpretations here, which we call relativist interpretations, which might look like strange bedfellows, but what they have in common is that they would all, so in particular, yeah, for the many worlds interpretation, would just reject the idea of absoluteness of human thoughts. So, and I'm pretty sure this is what David Deutsch would say. I guess, yeah, this is questionable here because different people have different opinions, but definitely in David Deutsch's case, yeah, he's perfectly willing to say that the computer has thoughts or even consciousness in the same way as a human, but that just that it's not absolute in the sense that if you have a splitting of worlds, then there's more than one happening inside that box. And that he also believes that that's happening to us all the time, because he believes in the many worlds interpretation.
I believe what he wanted to contradict is the idea of the collapse in general, and in particular that consciousness, that it is consciousness that caused the collapse.
Yes. So that's right. So if one did the experiment that he did, it would absolutely yeah. So it would prove that we can do. Yeah. Maybe I'll put it the other way. If consciousness really caused collapse, and you believe that machines can, well, let's put it this way: if thinking like a human could cause collapse, and if you really believe that the machines can think. And then you program a quantum computer to be that sort of machine, then that would follow that universal quantum computing is impossible. Because there's a program that you can't run because it's going to collapse, right? So therefore we can do an experiment and yeah, either get the result that it works according to quantum mechanics or it doesn't work according to quantum mechanics. And yeah, and I think that's absolutely... Yeah, I mean, and I think it's a very interesting experiment to do. I think I think it's very, very likely that it would just come out as we expect from quantum mechanics, but you never know. Right, but the point is that, yeah, David Deutsch, of course, is wrong in saying that the only other option is many worlds. Yes. Yeah. So I hope that answers the question, yeah.
So it seems to me, I'm not quite sure what the complication, bringing in the mind-body problem, bringing in the Turing test, piling a bunch of very controversial stuff on top of what's usually a pretty simple and clearly physical question, right? Question one, does the wave function collapse? Is there such a physical thing, right? Is that a physical thing? If there are collapses, that will have empirical consequences. Sometimes they're pretty hard to see, right, typically. Loss of interference effects in some cases, spontaneous emissions like they're looking for in Gran Sasso,
sure.
Right? If it does, then sure, none of this stuff can really be reversed, right? Non-unitary evolution.
No, I disagree with you on that.
You think you can reverse a collapse?
Yep.
How?
By using fault-tolerant quantum computing which corrects against local errors. So if we have a spontaneous collapse theory which produces a macroscopic world around us by having a slow rate of...
I'm not asking whether you can reverse a program. I mean a collapse. Is there a physical...
I'm saying that you can protect logical information from collapse.
Right.
That's
not
all
what
you
I'm
have
asking.
to do. But I'm interested in the question of whether you can reverse an artificial intelligence, a human-level artificial intelligence who has made an observation.
Okay, I mean,
that question is not answered by whether or not collapse theories are correct or not.
Sure, but it's not, I mean, the physics question ought to be all
right, so I'm talking about experimental metaphysics. So I guess that's the point, that the whole talk is about experimental metaphysics, not about testing particular physical theory. So that's why I said at the very beginning, this is, if you mind, not physics, it's experimental metaphysics. It's saying what can experiments tell us about the fundamental nature of the world without necessarily telling us what is the true physical theory. So none of these metaphysical assumptions mention quantum mechanics at all.
Right.
The same as Bell's theorem.
Yes, I mean, I'm not understanding some of the decisions you're making, but let me finish the question. Seems to me these are straightforward physical questions. Is there something like a collapse? Is the wave function complete, right? I mean, what upset Schrodinger, he thought the cat's alive or dead. if there's no collapse and the wave function is complete, the cat's not alive or dead. He thought that was absurd. Sure. Pretty much the same thing with Wigner, right? If the wave function never collapses, it's complete, then your friend, you know, doesn't see one thing or the other. He thought that was absurd.
Yeah.
Now, I'm not quite, you can then ask, okay, if you're gonna solve, you can solve this by not having the wave function be complete. We know that's a whole set of things. You could solve it by having collapses. That's another set of things. You could try to have neither. That gets you to many worlds. I'm not quite seeing, aside from bringing in a whole bunch of, it seems to me, extraneous questions about the nature of consciousness and Turing tests and blah, blah, blah. What, as physics, this is really helping us with, unless you're just worried about quantum computers. I mean, maybe it's about, are quantum computers reversible?
You could say the same, but I think you could say exactly the same thing about Bell's theorem. What does Bell's theorem tell us about quantum mechanics?
It tells you, what Bell's theorem tells us about, I would say, about the physical world is it's not causally local.
Right, and what an experiment like this would tell you about the physical world is that it can't satisfy all of these assumptions.
Thanks a lot for the talk. I mean, just in contrast to what was said, I think it's extremely natural to bring in these type of assumptions because, as you pointed out, Wigner had this thought that if something is like himself, and we have this perception that we see outcomes, and somehow this has to go into that theorem. So we have to think about consciousness in that sense because this is where the thought comes from. But now I have a question which is.
Although we were careful not to use the word consciousness.
Yes, right. Okay, this was not a careful formulation. Yeah, I think this,
no, I'm not saying you were uncareful, but just that we were,
My question is about the experiments that you mentioned, because I like this like separation into like these empirical facts, right, as the metaphysical ones. And however, if one now looks at concrete loophole-free Bell experiments, they have this ambiguity on the two sides on the choice, which is a kind of random number generator, and it's not so clear when is the randomness generated, and also on the side of the recording of the measurement outcome. When you actually talk to experimentalists, this is really still an issue because they have to artificially define now the outcome is there. Now you said, however, in 2015 this was clarified. So what would you now actually tell the next, or let's say, how does this ambiguity still play into this whole game?
Yeah, okay, that's a really, I'd really like that question because my answer would be that you're right, that things like the question of when was a random number generated or when did a measurement actually occur, those things cannot be answered empirically. So in a sense, those are also metaphysical assumptions, if you like, but they're also just, at some point we just have, the scientific community just accepts that this is good enough, okay? And there are these ambiguities, but you can't make progress unless we all just agree that, okay, we will say that, I mean, particularly to point out when a measurement occurs is particularly important because obviously that's exactly related to when do you actually have if you believe there are absolute measurement results, when do they occur? And so you can have different criteria. And so for example, like Adrian Kent has written about, we should do a Bell experiment, so not with, reversible quantum computers or anything, but just a Bell experiment, with 1 light second of separation so that humans can actually record the results. Because then you're having a weaker assumption about what it actually is that constitutes the absolute measurement result, that it's human thoughts essentially or human observations that constitute the absolute measurement result. So it's really important, I think, yes, that there are these. It is very hard to be absolute about these experiments. I mean, I think the community as a whole has just agreed that we have done loophole-free experiments, but when you get into the nitty-gritty, there are always little questions you can ask. And I guess the reason I like it is because, with the refereeing of this paper, I mean, there are all sorts of questions that the referees can ask, but what about this? But what about that? And I think the attitude you have to say is, well, yes, you can always ask questions, even in the Bell experiment. You can always question some implicit assumptions that you're making. But at some point, we just have to agree to be sensible as a community and not question absolutely everything. Does that make sense?
I mean, you had it on the previous slide, it's like different font for events and so on. So could
you mean the one at the end or something? Or?
No, in the assumption.
Oh, yeah.
This is just defined relative to the other assumptions. So you never say
Oh,
what
I
an
see.
event is.
Yes,
Couldn't
yes,
you, in that spirit, say whatever an event is, like you tell the next, like this is, so the metaphysical part is really in, like, it's just something that has to be defined.
Yeah.
And then in the experiment, it's whatever is meant in the first assumption,
Right.
so that you still have a clear separation.
Yeah, so that's right. So this is sort of what I was getting at the very end, saying that you can make other theorems where you replace assumptions like this with other criteria for something to be regarded as being absolute. Yeah, definitely, I agree with that. Yeah.
Okay.
Let's go for the.
So we move to the. Okay. So yes, let's move to the next one.
Okay.
Thank you. Let's
Can we move to the next talk?
No.
Oh, actually, yeah.
The online.
Però si vuole, tipo ieri quando diceva, perché crede Dio che non c'è senso. Cioè, ma forse sbagliamo, grazie. Va bene, poi per partire tu sei elementari.
Is plugged.
Sì, questo è veloce, lento e veloce.
Does it work?
Works.
Yes, but the laser pointer doesn't work. It's on the screen.
Comunque posso anche.
Well, it does work, but it doesn't.
You don't see it.
I don't see exactly. It's eaten by the screen.
Instead.
Okay, so next we have Caslav Brukner, who will tell us about localization and non-classical spacetimes.
Okay, good morning, everybody. Yesterday we heard about different notions of locality, signaling, well-known locality, non-locality, and non-locality, if I recall the talk from yesterday. So I decided to talk about another notion of locality or localizability and localization, just to increase the level of confusion. And this will be about locality of events, both in something which is ordinary classical space-time and something which we might expect as a non-classical space-time in some theory of gravity, quantum gravity. So let me start with noting that this is a work of joint work by many authors. Victoria, Anne, Catherine, Luca, and Carlo are PhD students in Vienna, and Enrique Gomez and Jeremy Butterfield are Oxford-based philosophers and also physicists. So let me start with what is an experimental effort by many groups worldwide, and this is to create macroscopic superpositions, a spatial superposition of large massive objects. And the question there is, what is the nature of gravitational field as sourced by such masses? And although we still expect an outcome to come, maybe in the next years or 10 years, or maybe a larger scale, there is no doubt that quite a substantial number of researchers believe that the gravitational field itself will be in some kind of superposition between, let's say, semi-classical solutions of the Einstein equations that corresponds to the, well, mass being left or mass being right. So what we expect is some space-time around these masses. I just want to tell you that it's not me. I'm not able to make this these slides. I stolen or borrowed from my students that they have done for their own talks. So and slightly adapted this. So so these are the two space-times. So you can think about branches in a superposition. And now you can think that this is a nice playground to investigate conceptual questions in this low energy limit of some future full complete quantum gravity theory. Now the particular game that I want to play here is related to how do we know in the first place that we created a superposition of spacetimes or superposition of any object. Because here I can put some kind of a label, so if you want some coordinate systems, and then in one branch I see that the masses is the coordinate 1, 2, and the other 3, 2. So obviously, one can understand this as a superposition of this object at different spatial locations. But coordinates are just abstract labels, and they are also arbitrary. And in particular, in gravity, we believe that the symmetry of the theory is actually arbitrariness under coordinate transformations. So there is nothing to prevent me to just reshuffle these labels such that in both branches I have actually the same coordinates, 3, 1 and 3, 1. So what's the answer now? Is this correct or the other one is correct? Or what does it even mean that the mass is in a superposition of locations? That's the question that I want to pose in this talk, and I hope we are confused enough that I can go on and try to resolve this. So here's the outline of my talk. I will first talk about the framework in which I want to describe the superpositions, and it will be related to symmetries of the problem in different sections. I will explain what I mean with this. And then we will recognize that this is just a framework in which is very nice to represent some other research field about quantum reference frames. We will see that quantum reference frames are instances of this framework. And then I will show an example that will, I hope, clarify these concepts on a practical basis. And then I move on the question that I posed at the beginning, namely quantum reference frames for space, times, and superposition, quantum coordinate fields, and some of the example that has some physical significance. So here's something which is very in line of the previous works by Gomez and Butterfield, who are also the co-authors of this work. However, they have developed this only in the classical framework. What you see here on the right-hand side is the space of models. Models is just any arbitrary physical system, which is equipped with a certain symmetry group. And so we will think about the space of all these models or configurations in this box, and they can be partitioned in different orbits. So the people who are familiar with gauge theories and fiber bundles understand that all models that are within one orbit are actually physically equivalent. There is nothing that physically distinguishes them. So there is a huge redundancy in the description of these models. I'll go on more specific examples. But you can think that if you don't have any external reference frames, all configurations that are related by the group of the symmetry group, by the group element, are actually physically equivalent. And then we can have, of course, different orbits that are physically inequivalent configurations of this physical system. Here's an example. Let's talk about translation group. Then we know that Newton's theory of gravitating particle is invariant under transformations. And here are two configurations, where on the left-hand side is a pro-particle, let's call it an atom, on the right-hand side the Earth. And they are related, these two configurations, by the rigid translations to the left, by some -a parameter, translation parameter. And they, if in absence of any external reference frame that can distinguish these two configurations, physically equivalent. On the right-hand side, I have something which is physically non-equivalent, given that there is orientability of my space. And on the right-hand side, the Earth is left and the pro-particle is right. So everything within the orbit is physically equivalent. Everything outside the orbits are physically non-equivalent situations. Now, what we need, an additional element that have been developed in these papers, is some representational conventions. Why? Because the symmetry introduces a huge redundancy in the description of physical situations, and then we want somehow to pick up, to get rid of this redundancy, and so we pick up always representatives in each orbit of the physical situation. And I can, for example, pick up this section, that's the notion of the sections, which I call sigma, that connects different representatives of this configuration in different orbits. And then I have this kind of a unique way how I can identify physically equivalent situations by picking up these representatives. But we should admit that this is just a convention, and it could be that I choose one convention and maybe you choose another convention. My convention is sigma and your convention is sigma tilde. And also this is absolutely arbitrary in both cases. So sometimes I want to see if your choice of the element is actually equivalent to my choice of element, but we have different conventions or different coordinate systems. So they could be either gauge fixing or some coordinate choice in a general relativity. And I just want to know if my element is equivalent to your element or it's not. And in order to compare then usually we have to see if they are connected by some group element or not within the orbit. And what is important, because of arbitrariness of the conventions, it could be that they are connected by the group element that are not the same in each orbit. So they could be actually orbit-dependent group elements. And that's important for what comes next. And here is again our example of the translation group. So what I here identify as one coordinate system, one set of coordinates, is, or choice of a section, is the choice of the origin of the coordinate system. And I pick up here explicitly that the pro-particle is at the origin of my coordinate system. That's what picks up this particular section. Now, of course, I can choose another section. So, and one possibility to choose another section is not to pick up the origin exactly at the point where the pro-particle is, but shift all configuration to the left. And then, for example, within this orbit, the coordinate origin will be in the mass, large mass, I mean the Earth, and the other one will be somewhere right from the particle. So these are different possible choices of the origins of coordinate systems. And one, when I want to choose from one to another, I can choose by, for example, rigid translation. That's usually what we do with the classical reference frames. For example, in this room, I can choose the corner when Sandu is standing over there as the origin of the coordinate system, and then describe all systems within this room with respect to this one, or I can move to the other corner of the room and then describe all the positions with respect to another origin. That's usually what we call as a classical, and the only one which we do in the textbooks, reference frames transformation, or the classical change of the coordinates, which is orbit independent. And I now want to go beyond that. And I want to say that this is not necessarily like that, and that we can really choose in every orbit a different group element to connect with the previous choice of the coordinate system, and then we will have symmetry under orbit-dependent translations. And that's exactly the point of where we meet with a subfield developed in the recent years about quantum reference frames transformations. There are many people working on that, and I will introduce it very briefly and with respect to the framework that I have developed, quantum reference frames, and I will mostly follow the paper by Flaminia and Esteban and myself, Flaminia sitting here, and to pick up the translation group as an example. But there are many other approaches that mostly agree on the main points, like perspective neutral approach by Kern et al. And so on. And I should also mention that quantum reference frames have been introduced very long time ago by Haranov and the colleagues, as Nicolas always underlines. But this is true indeed in this case as well. But it has been explored in the recent years. Now, what is the quantum reference frames? So, the idea is that instead of using the classical objects that are then localized, and with respect to choice of these localized classical reference frame, we can have global translations. to think about reference frame being a quantum mechanical system, no matter whether you think about them as a physically realized quantum mechanical system or just as a quantum coordinates. And then we can have a change between one or the other reference frame, and just a little bit ahead of the slides, what you see here is a situation that seemingly is physically different, but is actually just an artifact of the choice of the reference frames. In the first case, we have a large mass in a superposition and a localized pro-particle, but when we somehow choose this as a origin of reference frame, but if we jump on the large mass and choose this as the origin of reference frame, then we have the opposite situation, that the large mass is localized and the small system is in a superposition. And what will this be, and what has been introduced here back in 2019 is actually nothing else than quantum controlled translation or Orville dependent translation. And I will now show you that exactly it follows from the previous framework. So again, what we have here, now you should a little bit think about these orbits, not only as a classical configurations, but you can think about that as a possible configuration in the superposition. So you can think about the branch of the superposition. I'm not advocating many worlds, but it's useful to think about this framework in the many worlds language, in which you have different classical configuration, of course, superposed in a quantum superposition. And now, what we can think of is again to pick up one section. That will be a sigma section, which is identified, as introduced before, by the fact that the origin of the coordinate system is in the pro-particle. And now you have the superposition of the two different configurations, which I write here as a quantum state, in which the particle is an origin, and it's factorized out of this superposition, or this state. And what is left in the superposition is the position of the large object, the Earth, being in minus a or a with respect to the origin of the coordinate system. And as a picture, we can think about that. Now, what we can do next, we can choose a different coordinate system. And how we can do that? Well, we can, for example, apply some group element in one orbit that will be shifting everything to the left, such that the new origin of the coordinate system, that's where the flag is in a large mass. And in another orbit, we do the shift to the positive part of the axis by A, such that now, again, the coordinate system is moved to the large mass. So in both branches, in both orbits, the new coordinate system origin is in the large mass. And now we can again make identification of this. Namely, we can choose this coordinate system and write the quantum mechanical states from before in the new section with respect to the section sigma tilde, or with respect to the choice of the origin of the coordinate system being now placed at the Earth. And again, now the state has the form where now the large mass is in a superposition and the small particle is in, the large mass is factorized out in the origin and the small particle is now in the superposition. Now, we have these two possibilities, and one may ask oneself, well, how we identify position across the branches, and how with this identification we change the state. And my answer is that there is no absolute meaning in this superposition unless we choose our section. The section is arbitrary, and the states change its form depending on the choice of the coordinate system or the choice of the section. So, in a sense, the superposition, or even entanglement, in a more complicated situation between different systems depend on the choice of the reference frame. That's the essence of the quantum reference frames transformations. Now, why it could be interesting, useful? Well, usually it's useful when you have reference frames in which the physics is simple. That's one possible usage of the coordinate system. You choose the one in which you can perform your calculation in the easiest possible way. The other one is more fundamental. You may say that your physical laws should be independent of the choice of the coordinate systems. That's the spirit, for example, of the GR, that it's invariant under arbitrary coordinate transformation. But so far, people thought about this as a classical coordinate transformation. It's this global orbit independent coordinate transformation. One can go ahead and say, what if we think that the physical laws are invariant under orbit dependent coordinate transformation, under quantum reference frames transformation? And that's something which we coined under the name extended symmetry principle. That's invariance under not just classical branch independent, but also the quantum or branch dependent symmetry transformation. And funny enough, already some suggestions of how we can deal with situations of a typical quantum gravity situation distinguish between the theories that do obey this principle and that don't obey this principle. And here are two examples. Let's pick up the collapse models. We have these two situations which at the beginning of our investigation of analysis are just different points of view, different choice of the quantum reference frames. Now in the collapse models, if you have a small system in a superposition, it won't collapse, or the collapse time will be so long that you can finish your experiment before that and prove that you have a small system in a superposition. Whereas if you jump, so to say, in the coordinate system where the small system is in origin, the large mass will be in the superposition and you would collapse in the collapse model. So obviously these two effects are completely different depending on whether you choose one or the other coordinate systems, and therefore the collapse models do not obey extended symmetry principle. The same situation is for the semi-classical gravity, in which in semi-classical gravity, the gravity is sourced by the average gravitational field, average over the possible position of the large mass. So let's go again from the below. Here the mass is localized, so the average field is localized, points toward the large mass. So if I have a small particle in a superposition, these small amplitudes will evolve such that it fall towards the large mass. However, if I have this situation where the proparticle is exactly in the middle of the two possible amplitudes of the large mass, the average field is zero and it will stay there forever. And therefore, again, we have two physically non-equivalent effects, and we can say that semi-classical gravity also do not respect the extended symmetry principle. Okay, so how much time?
Around 10 minutes.
Around 10 minutes, yes.
Just ask at that point, if you go back to that picture, wouldn't the two Earths start falling towards each other? In the upper picture on your semi-classical gravity. So you have two large masses at some point. Yes. Yeah. So the particle, the small particle will be in the middle, and certainly, but wouldn't you expect the large masses to start collapsing in towards each other?
I don't know what would be the average field. How do you make an average field of the?
Would be half the mass of the Earth at each place of the Earth.
That just shows what a bad theory that is.
Yes. I mean, I agree that I'm not advocating the theory, but if this is the analysis you're doing, wouldn't you expect those two massive Earths to start moving together?
How would you define the self-gravitational of this one?
Expected stress energy tensor at that point, which is half the stress energy tensor of the Earth, sort of specified at that position.
Anyway, it's a superposition on a scale larger than the radius of curvature, which is exactly the point where semi-classical gravity is
sure.
supposed to occur anyway. So it's kind of
but that's somehow the point of the analysis, isn't it?
But I'm not sure if you have a pointwise here and you have a self-gravitational things, wouldn't this go to the singularities? How would you define this? Because now on this, it's not only the action of that, I have also the self-gravity.
So maybe if you can just add something.
Yes.
The point of what Caslav is saying is that even if they dynamically go one towards the other, then there is still an extended range of time where you will have the two masses are separate, similar quantum superposition, and then even in this time you would have a violation of this extended symmetry principle that Caslav is talking about.
Is the two time scales that this small coming at and these two bits are different.
So even if you collapse, you would still have it.
Thanks. Okay, so let me go further and try now to apply this on reference frames for spacetimes and the coordination of the spacetimes. So here I go now, instead of talking about the translation group, I'm talking about GR, I'm talking about diffeomorphisms as the group term transformation. And I will talk about vacuum GR. One can add also the mass fields of the matter on the top. It makes it more complicated, but I will not do that. And so the element in the space of models will be defined by the manifold and Lorentzian metric. And I will also add different sets of 4 scalar fields. So there are 4 chi 0, 1 to 3 fields that will allow me to make a comparison maps as before, where I have chosen just the Earth or the proparticle, and will play also the reference frame. In this talk, I will talk about Idala's set of scalar fields that neither the field, the gravitational field, nor they can back react on that. So you can think about that as do you have constraints through, for example, putting in the traps some material fields that will then serve as 4 scalar fields, and also that these traps are not so energetic that they have any influence on the background metric. One can go beyond that, and we did it in the paper. The concepts, the main message will remain the same, but there will be more realistic situation and more harder to fulfill our conditions, which I don't want to go now into details. Now, what will be now the model of possible models? That will be a tuple of the manifold, Lorentzian metric, and 2 4 scalar fields that I call chi and chi tilde, and they may live at different orbits, for example, at the beginning, so they can correspond to different 2 physical configurations. Now, next, what I want to say is that the symmetries, as I announced, is a diffeomorphism. So when I move within the orbits, I diffeomorphically change the metric and these chi fields. And now we think again about these different classical configurations as actually the branches in the superposition of the spacetimes. So I think about these 2 elements as actually representing the tuple, each in itself. So I will have something in the first branch of the superposition, which will be indicated by the index 1 for all these elements, and for the index 2 for the second branch. Now, what does it mean to go into the reference frame of chi fields? Once more, I remind you that we identify the points across the superposition in the case of the translation group, in a sense by sewing the points, identifying the points across 2 branches that corresponds to the same position of the mass, or that corresponds to the same position or localization of the proparticle. Here, similarly, we will do the same, but we will use the 4 scalar fields, either chi or chi tilde, to label the points and identify them across the branches in the superposition. And how we do that? Well, we need some comparison map. So one can identify the point P in the first manifold, in the first branch, with a point Q in the second branch, if and only if the chi fields that map these points to 4 numbers, because these are scalar fields in R4, to the same numbers, and let's say numbers C0 to C3, So if they correspond to the same value of these scalar fields, we will call the same points. In a sense, this is an operational way to identify space-time points, not ad hoc, but through the physical fields. And if these physical fields have the same values, then we'll say these correspond to the same point. Now, here is the expression for the comparison map. It takes the points from the manifold M1 and then make a composition, because this moves us here, and then we go back with the inverse of chi2, and we come to the point at the manifold M2. So that's a comparison map relative to the chi fields. And indeed then, just like in the previous case, we sew this and we say, okay, they correspond to the same point. Now, one possible comparison then between the different elements in different orbits or different branches of superposition now is that we identify through the same values across all models. So we identify points which has the same value of the chi field. Let's call this chi star. And with respect to this chi star value of the chi field, we can write the superposition of the space-time and the remaining fields, in that case only chi tilde field, such that chi star is in this reference frame factorized out state, and the rest is in a superposition, because with respect to this state, they do not correspond to the same point in the space-time. So we have a superposition, and I want to say that this is formally correct. What we here do are just superposition of semi-classical states. So each of these states corresponds to classically distinguishable solution of the Einstein equations. That's why they are orthogonal, and that's why we can linearly superimpose them. Of course, all this is just this semi-classical superposition approximation of some full theory in which we all, let's say, fluctuations around the classical values are ignored, like a Schrödinger-Cat states between the coherent states in which fluctuations around the coherent states are ignored, but nevertheless you can talk about superposition of coherent states. So that's the regime in which all this works. Now, we can also change the reference frame from chi to chi tilde. So we can choose to apply orbit-dependent diffeomorphisms, or in this language of branches, quantum control diffeomorphisms, different diffeomorphisms in orbit 1 and orbit 2. And so we find that we can then identify points. We change the respective chi tilde field to go to the one given chi tilde star value of these fields, and then identify again the points according to the new comparison map, namely sigma tilde. And then we can have 2 points now at manifold M1 and M2 to be the same if they have the same chi tilde value. So it's just the same story as before, but the reference frame is now taken over by the chi tilde and comparison map C chi tilde. Okay.
Including questions.
Including questions, thank you. Okay, I'll take a little bit of the questions as well. And now the same state can be written in this new reference frame in which chi tilde star is factorized out and the rest is in superposition, namely the chi field that was previously used as a reference frame is now a field that is not, which is in a superposition with respect to chi tilde, the field. And now this allows me to address some interesting physical situations. And in particular, I might ask myself, just like at the beginning, whether an event could be considered to be in a superposition of 2 different locations or not. And for that, we need first to define an element, an event. And I do this here just like people do that in GR, namely as a crossing point between 2 fields. So let's say we have a yellow and a black field. and we have a crossing point in one manifold or the other manifold. And let's also assume that we have one particular coordinate system, let's say coordinate system according to the chi field, and we may say that these 2 points are actually identical, in a sense that the chi field has the same value as these 2 points. Now, in that sense, then we will not say that this is a superposition of 2 locations with respect to the chi field, because the event happens at the same location with respect to the chi field. But nevertheless, we can then change comparison map, so we can change the different fields, tilde fields, and it could be, well, that although that one of those in the first manifold, when we identify this point with the chi tilde field, we do not come back to where we were before, but somewhere else. And then, in that respect, we will have a superposition of the locations of this event with respect to the chi tilde field, although we didn't have any with respect to the chi field. In other words, what we have here is, let's say, these two identified according to chi field. We do different diffeomorphisms in different branches of the superposition. We will, of course, through the diffeomorphisms, get back the same localization of the crossing point, but it could be that these 2 points are not anymore identified, because according to the chi T field, that point is maybe identified by some other point. And therefore, then we will say that this event is not anymore localized in the chi tilde field. So what we can conclude is, if you want, and if you're familiar with Einstein's whole argument, a kind of extension of that in the quantum framework, where identification of space-time points and localization of events are time-independent or coordinate-dependent and have no, therefore, absolute meaning. The usual Einstein's whole argument is that the space-time points have no meaning and should be equipped with coincidences, field coincidences. But here we also want to say that if we have a superposition of fields, we have to think about with respect to what coordinates we write them, such that they are real superpositions, namely superposition of different locations with respect to the background fields or not. And this, I will maybe just run over this, tell you that this has consequences in a serious discussion in the field of so-called indefinite causal structure and different causal order, where we basically have different implementations of that. The idea is that you have a superposition of the order between operations A, B, and B, A. And there is an ongoing discussion in the community whether the optical quantum switch, which we have done in the laboratory and involves 4 space-time points, is the genuine representation of indefinite causal order, or we need to go in the gravitational setting in which we can show that in certain coordinates these 4 points collapse into only 2 points. So the question is, how many events are there? And there are usually 2 answers to that. If you identify space-time points as the event, you would say there are 4 events in this optical quantum switch. There is another group that insists that although there are 4 space-time points, we should not count the space-time points, but we should count the complete positive maps that are performed on this object, which are still telling you that there are 2 points. And one way to resolve this issue, and not only the only one, is to understand that the change of the quantum reference frames change the number of space-time points, and that was what I showing in the previous slide. And therefore, so for example, although we can have superposition of the causal order, let's say there are 2 different events that maybe be in opposite causal order, if they are identified by chi-phi field to happen at the same point with respect to chi-phi field, and in that sense we will just have two space-time points related to these two events, in some other reference frame chi tilde, they may not be anymore identified, so here we have 4 points. So we see that the number of space-time points depends on the quantum reference frames, and therefore is not something which is invariant under quantum-controlled diffeomorphisms, and maybe should not be taken as the definition of the events if we want to have a number of events to be invariant. Okay, so let me go to the summary. What I wanted to argue in this talk, that really the choice of quantum reference frames determines how to compare configurations across the branches. There is no absolute notion of superposition entanglement, but only with respect to certain reference frames that are coordinates. Then I extend this into the quantum coordinate fields, which was important to define your comparison map when we talk about superposition of spacetimes. We saw that despite using coincidence of physical fields, there is still ambiguity in which quantum reference fields we choose to write this superposition, such that the superposition at the end may not be a superposition of different locations. And one lesson that I would say is that identification of space-time points and localization events have no absolute physical meaning, and this has implications for defining number of events in the quantum switch. And I conclude with, well, that apart from superposition, entanglement, subsystem structure, localization events, which other notion previously thought absolute are fundamentally relational? I think Howard's talk from the morning, we can add here maybe the absolute, the events in themselves, maybe add to the list, and maybe more concepts. With this, I would like to thank you for your attention.
We have a few minutes for questions.
Caslav, I'm trying to understand in your bundle picture how you distinguish the difference between gauge symmetry and global symmetry.
Yeah. We don't distinguish, and we think that it's not that one should not distinguish. As long as you don't have any external reference frames, there is no difference. They are all gauges, if you think. The only thing that if you impose on the top that there is external reference frame, you can then distinguish these global symmetries, but they are not. If there are no external reference frame, then they collapse together. And can be considered just like a gauge.
Okay, thank you. Interesting.
So it's a little hard for me to follow this, but it seems to me that the lesson out of GR is kind of the opposite of what you're using here. As far as I can say, there was a whole problem in GR of people putting down bad coordinates, right? And you get coordinate singularities. You got coordinate singularities at the event horizon that had no physical significance because they were bad coordinates. What do I mean by bad coordinates? Each point ought to get a unique coordinate assignment, right? You shouldn't have the same coordinates going to different points or different coordinates going to the same point. If you just use 4 fields, there is no guarantee whatever that each point will have a different assignment of those 4 fields, and so what you're going to get are dreadful things you're counting as coordinates.
You have a very nice, so you have to have a very inhomogeneous scalar fields to be able, and of course, also you might not be able to do it globally, but you have to do in the patches, which you have to then put them together. So it's not trivial that you can always satisfy this inhomogeneously, that you can recover the space-like structure from the 4 scalar fields. That's totally true, and I agree with this. And I would say that either you should choose better one, if they are available, and I will say something which you won't like it. I would say if there is no available, then you will not recover the space-like structure as we know it from the classical world. Because there is no operational way to make sense of it.
Thank you for the talk. And in the slide where you talked about collapse theory and semi-classical gravity, is there an assumption that you assume the wave function describing the system, like the particle or the Earth, they are ontic instead of epistemic, or the analysis is independent of whether you view
it's independent of the interpretation. It's purely what these theories predict on the level of phenomenology.
Okay, thanks.
But maybe this interpretation have in mind that the function is an ontic when they come up with this. I do think in both of these interpretations, especially for the collapse, I think, is the, or let's say for the Schrödinger-Newton equation, which is a little bit different, is this idea that these two superpositions are embedded in the same space-time, like they really think that there are two balls that then attract each other, instead of having, well, there's one ball, in many worlds we would say in one world or the other world, or there's no, I think in many worlds is the best way to explain what's the difference, although I do not subscribe to this interpretation.
So in the semi-classical gravity, I thought it's a theory of gravity, so there's no notion of whether a state is ontic or epistemic. But in your analysis, do you supplement it with the notion that in the semi-classical gravity theory, the quantum state ontic or epistemic?
As like the semi-classical gravity is mean field theory, if you want. Like you replace, so I guess one possibility would be that you have coexistence of these two balls in one space-time, not thinking about one ball, be it in superposition of two configurations. I don't want to say more because I don't know whether this connection with the ontic view can be established more rigorous.
Thanks. Maybe one more quick question.
It's only a terminology question. Why do you call quantum reference frame transformations quantum reference frame transformations? Because the way you explained it seems to be much more general and not really linked to quantum.
Absolutely good question. Okay, so so maybe just go back. I fully agree. So whatever picture we have with this orbit is good. Let's say something like that, where we have orbit dependent. So indeed, this is a very general approach. And I think, let's something like that. It's a very general approach. These lines, I said, they are orbits. And there are different configurations. But I didn't say anything more, and I even jumped in the middle of the talk, saying, oh, don't think about them as a classical configuration, or do think about them classical configuration that are branches of a superposition. Everything what I have said could be also applied to the classical mixture of classical configuration, in which I also applied orbit-dependent transformation. The only difference that one could then distinguish between classical mixture of orbit-dependent transformation and quantum is, of course, not in what I have explained, and namely that there is a measurement in which you can perform superposition, like in a double slit experiment, and prove that you have a rigorous superposition of these classical configurations, and not just mere classical configurations. And therefore, this measurement will make a difference. So I would say that this framework is very general to anything which has, let me put this, spirit of many worlds, which you can think about different configurations, but these different configurations maybe will be classical, quantum branches in the quantum superposition, or something in the GPTs, in general probabilistic theories as well. So I think it is more general, and it should be supplemented by the part that is maybe related for the switch and these experiments that where you can prove at the end that there is a superposition.
Unfortunately, we're running out of time, so let's thank the speaker again.
Did everybody feel the heat?
Summer to feel like it was great. I was like happy the summer I want.
That's why you have a cat. Advertising like
My Airbnb makes his eyes bigger the honor.
too many. Yeah, of course. Have a look. You may have a look. So there's this guy from like a bit more. He made a very nice list. Yeah, we'll have a meeting next soon to decide if we adopt this. It's very creative.
Our next speaker will tell us about the tension between relativity and quantum theory.
Okay, so let me just say something very quickly about this presentation. Nicolas said people like to hear, things they already understand. Everybody enjoys that. I actually wrote this for the Achenstein lecture of John Hopkins, and that was for a completely open audience. I was supposed to assume nothing. Okay, so there's not going to be anything technical. The problem is, it was hard for me to do this in 45 minutes. I'm supposed to do it in 30 minutes now, so I'm trying to think of what I can rush through. There's a little bit of technical stuff at the end I can rush through, because you all know that stuff. But I'm now beginning to think that it may not be the reaction of the audience that, oh, this is all stuff I know, but this may come across to people as wildly, controversial, in which case it's even more important that I give this talk. So take it either way. But everything is presented in a very basic way because it wasn't written for you guys, right? So don't feel insulted. There's this common picture. I just pulled this off the web. I knew I could find it. Modern physics rests on these two great pillars of relativity and quantum mechanics, but there's some problem there. Now, what I want to talk about, and this is going to be in great contrast to anybody who wants to say they want to be an operationist or something like that, is my understanding of what fundamental physics is. Fundamental physical theory is that part of physics, because there's physics that doesn't do this. Condensed matter physics isn't what I'm talking about here, where you really focus your attention on the basic, most fundamental constituents, physical constituents of the universe. That is, the ones that don't get analyzed in terms of anything else, right? So if I'm doing condensed matter physics, I kind of take for granted there's condensed matter. You think, at the end of the day, I'm going to analyze that, right? But that's somebody else's job. For the moment, I'm going to take a bunch of stuff for granted. Let's try to get down to the bottom of this whole thing. Well, what do I mean by physics? What is physics responsible for? Well, one of the ways of understanding this, maybe out of Galileo and so on, it's basically the theory of matter and motion. Let's just start with that as a kind of definition of physics. If you say that, then if you're a philosopher, you say, okay, now I've got two targets of inquiry. What's matter, right? You've got to answer that if you're going to do physics. And what's motion? Now we're already starting to see these two pillars emerge, right, from this very simple beginning. Then, once we have that, then there's the kind of really technical thing is what are the laws that govern all this or describe the motion of matter? Different physical theories, fundamental physical theories, can answer these questions in different ways. Here are some possible answers to the question, what is matter? Microscopic particles, that was already Democritus. That's also what Newton believed. He had a corpuscular theory. Once you get to Maxwellian electrodynamics, you have a new thing, right, introduced. Oh, maybe there are fields. Maybe there are these things, electric and magnetic fields. They're not particles. They have a different character. They're defined everywhere. What is the fundamental ontology, or what is the fundamental physical postulate of quantum field theory? Okay, that's not an easy. I can tell you more or less what Maxwell thought. I can't tell you more or less what this theory says. String theory, well, when they give everyday popular presentations, you think you understand what they're saying. Matter's made of little vibrating strings, right? Vibrates this way, it's an electron. Vibrates that way, it's a gluon. Vibrates this way, it's a photon. I mean, you at least understand what they're saying. Or maybe you say, well, you're trying to understand matter in terms of some conceptual categories that aren't appropriate anymore. This is kind of Bohr. It's something. Don't expect to understand it in any classical way. It's both and neither a particle and a wave. It's a wavicle. It's a kind of weird thing. You know, get your mind around it. That's a possible answer. I'm not objecting to that. You do have to tell me a little more about it before I know what you're saying. What about what is motion? Well, motion for Newton was very clear. Something was moving, if it was changing its location, this is locomotion, changing its location in absolute space. For Newton, absolute space persists through time. Individual points of space persist through time. A single object can be either in the same place or in a different place at different times. If it's in a different place, there was some direction it went, and over some amount of time, you get absolute velocities. That's Newton. People didn't like that too much because you couldn't observe the absolute places. One thing that happens is you say, no, I really want to think of motion as somehow the trajectory through space-time. And here I can specify this without talking about space persisting through time. I just need a space-time with some geometrical structure. And then I can say, well, when I talk about the motion of a particle, I'm really just talking about its trajectory through space-time. As soon as you say that, then that leads to the next question. Okay, what's the structure of space-time? What is the fundamental spatiotemporal structure of the world in the arena in which this kind of thing can take place? And then you can get, again, different answers. For Newton, there's a three-dimensional Euclidean space that persists through time. You could say in special relativity, it's a four-dimensional differentiable manifold with a flat Lorentzian metric. Or then you get to GR, it's a curved metric. These are all recognizably clear answers to these questions. Now, what is the relation of matter to time? So you see we've already separated it out. There's one part of this that's getting to the matter part. There's one part that's getting to the spatiotemporal arena part. The particles that Democritus postulated, that Newton postulated, these corpuscles, persist through time, right? You might not think that the individual points of space persist through time, but you can certainly believe that particles persist through time. That's why their motion then corresponds to a continuous curve, as it were, in this spatiotemporal structure. If you then go to a different ontology, like a field ontology, you just can't ask, how is the field moving, right? It doesn't locomote, because the field is always defined everywhere, right? It doesn't go from one place to another. The values at space-time points can change. And, you know, maybe you can then think of something like a lump in it moving, the way we talk about a water wave moving, even though the matter, right, the water itself isn't moving. I mean, it's basically moving up and down. It's really doing little circular things. But anyway, the water isn't going from here to there, but the wave is going from here to there. That's just a change in the state. And you can have these moving disturbances. Once you have the field ontology, then there are various choices available. All right, if I believe in the fields, are there particles in addition to the fields? That was certainly Maxwell's view. You have electromagnetic fields and you have charged matter. Or maybe you can reduce one to the other. There was this idea once you had the fields, maybe I can get rid of the particles and say there are vortices in the fields or there are singularities in the fields. So just tell me about the fields and somehow that's all there is. This is the kind of question you ask in fundamental physics, right? Now, again, the string theorists talk this way as if there are these one-dimensional objects that persist through time and wiggle, and then there are brains, and there are different brains, blah, 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 blah. Okay, you all know this stuff. So I want to say from this point of view, if you kind of step way back and have a kind of very general conceptual skeleton in which you can say, what do I need to provide you so that you've given me a comprehensible fundamental physical theory? At least unless you do something really weird, this is a pretty big skeleton. You say, well, give me a space-time structure. Could be all kinds of different possibilities there. Give me an account of what the local matter is, the local beables, in Bell's terminology, the stuff that is located at particular places in this space-time structure and can then be distributed over it, right? This is what Shelley Goldstein calls a decoration of space-time. So tell me what your space-time structure is, tell me what your local stuff is, and then tell me whatever the heck else you want to tell me to finish out so you can write down your equations. Now, one of the things, you can add whatever else you want here. What happens in quantum theory, of course, is you add this weird object, apparently, that is represented by the wave function, which is not a local beable, right? This is one of Bell's points. He says, look, you can't ask, pointing your finger, you know, the test is, can I point my finger and ask about, what about that thing? Then it's a local thing. And Bell says, look, you can't point your finger and say, what is the value of the wave function here? You know, what is the phase of it here? It's not defined on physical space. It's defined on configuration space. It doesn't have local values. It is nonetheless, you can think it's a real thing. It's a real physical thing, something that, you know, Aristotle and Democritus and Newton and Maxwell never thought of. It's a non-local thing. You might ask, why are you postulating this? And the answer is, because I need to write down some equations. At the end of the day, what I want to do is account for this motion of this local stuff. That's what gives me my empirical predictions. I complete my physics by adding whatever I care to add in order to write down equations that will then tell me how this local stuff moves. And once I have that, then I know what I should expect to see in my lab, right? So I put it as much in here as I need to write down the dynamical equations for the local matter and also the non-local stuff. And the kind of consistency constraint is that the only reference to space and time that I'm allowed to put into these dynamical equations is the stuff that I've already postulated here as actual space-time structure, right? So if I say I want it to be relativistic, all right, that puts a constraint on the kinds of equations I can write down. I have to only mention geometrical features that are well-defined, say in a Lorentzian, you know, a Lorentzian signature metric or something like that. Do you have, I mean, kind of standard big question here we're going to get into. What if I need some more space-time structure? If I have if I'm going relativistic, one thing I do not have is a preferred foliation of the space-time. So I can't write down equations, right? I should not honestly write down equations that are with respect to some foliation, because I have not postulated there is such a thing. Now, from this point of view, what we need at the end of the day is a theory of space-time structure and a theory of matter and a theory of whatever else where the dynamics are specified in terms of that space-time. And then you say, well, these two pillars that modern physics rests on, one is relativity, because that's the best theory of space-time structure we have, and the other is in some sense quantum theory, although there's all kinds of controversies about what it means. That's supposed to take care of the matter part, right? And then people say, but there's a tension between them, right? There's some tension between these two pillars. That's trouble. What's the tension? Well, here's something that can happen. Is you just say, well, the space-time part, the GR part, is framed in terms of a certain set of mathematical structures, and the quantum part is framed with a different set of mathematical structures, typically with an assumed flat, fixed background space-time. And those two mathematical structures don't play together well, right? They seem to have different mathematical elements to them. And then you'd say, well, of course, what we want at the end of the day is a single theory that covers everything and is written in one equation, in one mathematical formalism. And so the problem of this tension is just coming up with some single mathematical structure from which, in some appropriate sense, relativity emerges in one direction and quantum theory emerges in another direction. Now, if you present it that way, then you say, okay, that's kind of a technical mathematical issue, right? Maybe some really clever mathematician, maybe Ed Witten, is going to think of a new kind of mathematical structure that we hadn't thought of, and that, gee, you know, you can fit these things together once you rewrite each of them in terms of this new language. You might imagine this kind of tension going away tomorrow, right? You'll open up the newspaper. Mathematical genius solves problem. Okay? Now, what I want to say is so that kind of, if that were the problem, it would be amenable to a technical mathematical solution. What I want to say is no, the situation we have before us is a heck of a lot worse than that. And it ain't going to go away tomorrow by some, you know, by Ed Witten coming up with some new gadget. Why not? I want to claim there's really something pretty well close to a flat contradiction between relativity, at least as it is commonly understood, and quantum theory. And that is not going to be resolved merely by mathematics. What's the nub of the issue? Well, commonly it's said that relativity implies that nothing goes faster than light. Maybe all of you have heard this. Bell tells a wonderful story that he was once giving a talk at a university, and the title of the talk is What Can't Go Faster Than Light? And I guess there were all these posters, right, back all around, and he's walking to give the talk, and he noticed there's some graffiti on a poster. You know, so the title, What Can't Go Faster Than Light? And someone has written John Bell, for example. On the other hand, I claim the correct understanding of Bell's theorem is that certain observed correlations between experiments done far away from each other cannot be predicted or explained if no causes go faster than light. That's what I'm claiming the result of Bell is. And if that's the issue, then you see it's a flat contradiction, right? This understanding of relativity forbids something there must be in order to explain what we see in the lab. Right, and that, of course, goes through two steps. The first step is what Bell noticed, which is that quantum theory predicts violations of Bell's inequality, but that's not the real issue because quantum theory could make bad predictions, right? And some people, before any of the experiments were done, just came to the conclusion they expected the quantum predictions to fail because they saw the implications of them holding. But then the real point is this one, it's the observations, right? Throw quantum theory away, I don't care, you still have these experiments. They've been done, the results are in, the loopholes have been closed. Somehow or other, your physics better be able to account for what we actually see. Good. Now, as I said, it's commonly said that relativity implies or asserts or something that nothing goes faster than light. It's often commonly said that relativity asserts or implies that the speed of light is constant. I don't think that's certainly not the correct description, right? The correct description is that according to the space-time structure that relativity postulates, nothing has a speed. To talk about the speed of anything in an absolute sense is empty, right? There is no physical quantity that's the speed of anything, including light, right? if you want to have objective speeds, you can have them. Newton had them. But Newton had them by postulating this very particular persistent space in terms of which he could define how far something went in a certain amount of time and therefore attribute an absolute velocity to it. Now, Newton had nice arguments, the bucket argument, as to why he thought you needed to have absolute velocities, because he thought you could see the effects, again, in the lab. I mean, you think Newton was doing experimental metaphysics when he does the bucket experiment. He says, there's this big debate between me and Leibniz about the nature of space-time. You know how I'm going to win it? I'm going to put a bucket from the ceiling and spin it and see what happens. And see if Leibniz's account of space-time can explain that. Answer, it can't. Right? Or Aristotle's or Descartes' account of what you mean by the velocity of an object. It can't. I mean, I guess I need to go quickly through something. This is just the Newtonian account where you have a single space, individual points of space persist through time. You think of motions as changing those locations. Then you can ask how far have you gone and how much time in what direction. Then you can get an absolute velocity. I'm sorry, I do need to go through this. This is just explaining to people. So in a Newtonian picture, this kind of rectangle represents absolute space itself. P and Q are individual points in absolute space. The time index indicates that these are, as it were, successive snapshots, if you will, of the entire global state of the universe. A and B are two billiard balls. And at each time, there's a fact about where A and B are located in absolute space, right? So here you see A keeps getting further and further away from Q. B keeps getting further and further away to P. They collide. They bounce off each other. That all makes sense for Newton because he made this postulate that P and Q, the points of absolute space, persist through time. Notice, I'll just mention this. Notice there are no coordinates here. Right? Newton didn't have coordinates. Newton never used coordinates. Newton wouldn't know what a coordinate was. He still had a physical theory, right? Had perfectly good postulates. He understood what he was doing. Well, that Newtonian picture, you can then do a space-time diagram, a kind of four-dimensional model where you stack these instantaneous global states up, and you're careful to stack them up so that the points of absolute space lie above each other in the diagram, and then the motions of the billiard balls and them bouncing off each other become these world lines. That's just a visual presentation of what he's already postulated. Now, in relativity, of course, what do? We get rid of a bunch of that structure. We get rid of the absolute foliation. We get rid of the global moments of time. We replace the whole thing. Now, it's important to recognize that what happens in relativity is not taking what Newton believed and just subtracting from it. You certainly do subtract from it. You get rid of absolute time. But you also put stuff in that Newton didn't have, right? It's replacement. So, again, the replacement is such that after you're done, you can no longer define the speed of anything. Nothing has a speed, including light. So, what do you mean to say if there's no speed of light? What do you mean when you say nothing can go faster than light? It sounds like you can't even say that if you can't quantify speeds. Yes?
Yeah, what about the idea of fall velocity?
Yeah, that's fine. I'm just going to get
okay, right.
I'm just, again, this was for everyday audience. I'm trying to get them there without going through a lot of tensor calculus, right? Well, part of what is implicit in any relativistic space-time, whether curved or not, is a light cone structure. We call it conformal structure. And that's going to associate, right, this light cone structure. Again, we've gotten rid of the foliation, we've gotten rid of the slicing, but we've replaced it now with a conformal structure, the light cone structure, and that's objective in the theory, right? That's not coordinate dependent. It's out there in the world, right? And we can, of course, pictorially represent it. Again, I'll go through this very quickly. You all know this in a space-time diagram. So that's out of Sean Carroll's book. Now we say, all right, I haven't sliced it up this way, but now associated with every single point, I have a light cone. And then I've got these trajectories, and then I can distinguish the trajectories into the time-like ones and the null ones and the space-like ones. That's all well defined, yes? Now what Sean says here is that a space-like path is not allowed. So you say, well, here's something a particle could do, here's something a particle couldn't do. That's well defined without mentioning speeds. But now I understand what it means to say that particles can't go faster than light, because I've got a light cone structure. It means that the particle trajectories, as we say, have to thread the light cones. And so I've extended that one out. Here's something a particle cannot do if particles can't go faster than light. I now can indicate that restriction without talking about the speed of anything. Notice I can do the same thing for causation. Right here, I've got this trajectory. It can't pass through the light cone the way it does there. But I can say the same thing about causal relations. Suppose I say I've got a causal relation. There's some free variable, something that can be treated as a free variable here, a button that can be pushed or not pushed. And it has some effect, right? Whether or not that button is pushed will have a causal influence on something else. If causation can't go faster than light, here's something that can't happen. The button pushing event can't be there, and the effect of it at space-like separation. Right? So again, I can explain what I mean by saying causation can't go faster than light without talking about speeds or anything else in terms of the intrinsic geometrical structure of space-time according to relativity. Now we get to Bell. So Bell says, look, all right, that's a good causality condition. Causes can't go faster than light. All of the causes of an event have to lie in or on its past light cone, right? That's the Bell causality condition. The amazing thing is that just from that condition, which is stated in its extremely abstract general terms, Bell can say, well, if causation can't go faster than light, there are certain restrictions on what you could expect for physical, from the physics to be able to predict or see in the lab. That's Bell's fundamental assumption. It's not an assumption about determinism. It's not an assumption about hidden variables, which you don't even know what that means, right? All of this is stated in a language where the term hidden variables doesn't even have any meaning. Already, I think some people said Bell rules out local hidden variables theory. No. He rules out local theories, full stop. Adding hidden variables is adding something that does nothing but distract you from what's going on and suggests to your mind that if I just get rid of hidden variables, everything's okay. Absolutely not. So think of that as relativistic causation. What Bell proved, I would claim, is that any relativistically causal theory, there are constraints on the correlations you can see. Those constraints can be expressed in terms of various sorts of Bell inequalities depending on the exact situation. Now, yipe. Yeah, I know. Okay. It's important to understand here in the history that Bell, the title of his paper is on the Einstein-Podolsky-Rosen paradox. He is assuming the reader has read Einstein, Podolsky, and Rosen's paper and, more importantly, has understood it. That turned out to be a wildly optimistic assumption for Bell to make, but he made it. All this goes back to EPR. What's important about EPR? EPR, we're noticing also some correlations, but importantly, they were perfect correlations, right? They were perfect correlations. For Einstein, Podolsky, and Rosen, they were correlations between either position or momentum measurements done by Alice and Bob, such that, given the initial state they write down, even though at the beginning neither Alice or Bob could predict, or nobody could predict what either of them would see in their labs, and let's just do it, again, it doesn't matter that you can do it for both, just do it for momentum's sake. Nobody can predict from the initial wave function what they'll see, get out of their so-called momentum measurements. Nonetheless, you can predict for sure, 100%, they will get exactly opposite momentum, right? The net momentum will be 0. Therefore, once Alice sees her result, she now comes to be able to predict with certainty what Bob will see. which he couldn't do beforehand, which nobody could do beforehand. Bob couldn't do beforehand. Now, of course, you can violate Bell's inequalities without there being any perfect correlations. That's CHSH. But for the structure of this argument, it's nice to just do the case with perfect correlations. They are predicted by quantum mechanics, and with an epsilon, they're observed in the lab. So those are the EPR correlations. Now, this is just about spin. All right, you all know this. This is the actual data from the first Stern-Gerlach, if you've never seen it, on a postcard. And this is Stern writing to Bohr, showing. Anyway, this is all explaining spin experiments. You guys know all this stuff. You know about how to do entangled states, blah, blah, blah. Okay, you understand that thing, so I got to go over something. But what EPR notices is, look, if I've got these perfect correlations, and I don't want spooky action at a distance, I don't want this weird effect of Alice's experiment on Bob's particle, the only way to avoid spooky action at a distance is to predetermine the outcomes on both sides, right? They're predetermined at the source. That was the point of Bertelsmann's socks example. It is not a surprise that Bertelsmann can have perfectly anti-correlated sock colors, right? That's not a shock. There's nothing spooky. There's nothing spooky about being able to see that one of Bertelsmann's socks is pink and then do a Bayesian update and say, I now know, which I didn't know before, his other sock isn't pink. Big deal. So what? That is trivial. That is not interesting because you can explain it locally. But you can only explain it locally in a deterministic theory. Only in a deterministic theory. Right? As Bell says in Bertelsmann's socks, if you don't think it's a deterministic theory, if you think the sock didn't have a color until you looked at it, that's already kind of weird, right? That the sock that suddenly decides to be pink all of a sudden when you look. But even weirder is that the other sock somehow knows that this sock decided to be pink because it always manages to be not pink. That's the perfect EPR correlation. And quite reasonably, Einstein thought that's insane. That's the result you get if you take the wave function to be complete. I mean, the whole point of the EPR paper was to argue the wave function is not complete. And then in a completed theory, you get rid of the probabilities. And you would restore local causation. Good. So this is how, a local theory can easily account for the EPR correlations. That's what they thought any reasonable person would do. And said, but that's not what's done according to Bohr, right? That's not what's going on according to Copenhagen, all the worse for Copenhagen, right? Bohr's on the wrong foot. Because, why? Because they were insisting in the completeness of the wave function. They were insisting the wave function is complete. And because you can't predict, say, the outcomes of the momentum experiment from the wave function, then it can't be predetermined. Good. So this is what I'm saying. If you want to restore local causality in the face of the EPR correlations, you're forced to determinism. And this is what Bell insisted over and over. He couldn't get through people's heads. It's not that you assume determinism so that by just denying determinism, you're out of the woods. You assume locality, you notice the perfect correlations, and then you infer determinism. It's the only way to preserve locality, right? Bell complained over and over he couldn't get people to understand that. There can't be, if you have these perfect correlations and it's a local theory, there can't be anything fundamentally random and indeterministic. So you say, all right, I need a theory where these results are predetermined, or else I need to accept spooky action at a distance, which seems to go against relativity and certainly seems to go against common sense. I mean, when you say it's spooky action at a distance, you don't have to believe in relativity to find that spooky, right? To think that Alice doing something way the hell over there in her lab is having a physical effect on Bob's particle way the hell over there in his lab, right? That's spooky even even for Newton, right? Good. So you say, I want to preserve local causality, I'm forced into local determinism, and now what Bell notices is that you can't do it. It's not just a matter of going to, trying to get a deterministic theory. No local theory can do the job. Now, the last part of this, which I'm just going to show, because I did this actually in front of Sean Carroll, he said he hadn't seen the particular argument. It's a nice argument. I don't know, maybe not everybody has seen it, the GHZ example. And so the last part of this is just going through it. So here's our setup. We have our source. We're going to have 3 Stern-Gerlach magnets. We're going to assume Alice, Bob, and Charlie can set however they like their magnets in one of 2 directions, call them X and Z. Z that way and X that way, for example. And of course, they will get outcomes that can be characterized as either up or down, binary outcomes. That's the setup. We all know for a particular initial state which can be produced, what are the relevant quantum predictions? All right, because Alice, Bob, and Charlie can each set their apparatus in one of 2 ways on each run of the experiment. There are 8 possible global experimental configurations, which we specify by saying who set what way. The predictions we care about are only about 4 of those global configurations. So if they're just setting them at random, as it were, half the time it won't be a relevant setting, but we don't care, right? I mean, there are predictions about that, but they don't come into the argument. What do we care about? Well, these are surefire, 100% non-probabilistic, absolute predictions. If they all happen to set their devices in the X direction, there will certainly be an odd number of up outcomes. That's not it could be 1, it could be 3, right? There are probabilities for that. We don't care. What we care is that for sure, 100%, you'll always get an odd number of up outcomes when they all set in X. The other case we care about is when one sets in X and the other 2 set in Z, which can obviously happen in 3 different ways. In that case, 100% surefire, non-statistical prediction, there'll be an even number of up outcomes. Could be 0, could be 2, can't be 1, can't be 3. That's all you need to know. Right? That's all you need to know. Claim. No local theory can make these predictions. Why not? First conclusion. If there's no way that the setting of one device can influence the other 2 labs, right? Then we have the same EPR argument that if this is a causally local theory, all the results must be predetermined. Why? Well, if Alice's result is not predetermined, how is it that what she gets somehow manages to constrain what Bob and Charlie get, right? The point again is that from any 2 of the outcomes, you can predict with certainty the 3rd one. That's what allows EPR to use their so-called criterion of reality in this argument. That's correct here because of these perfect correlations. So first conclusion is if you want to explain this locally, you've got to predetermine the outcomes in all the labs already at the source. Nothing can happen by chance. Okay, fine. And now we're at the end of this, and again, maybe you haven't seen this. It's really, this is a diagram that's due to David Mermin. And I'm going to give you the explanation is, the argument is the way David Mermin said it. I said, Sean Perry hadn't heard it. Beautiful, right? You say, okay, Alice, 1, she's either set as X or she's set as Z, right? So the circles represent the 6 possible individual experimental settings, X and Z for each of our 3 parties, 1, 2, and 3, Alice, Charlie, and Bob. But you just do the diagram this way, has this nice symmetry, and this dotted line represents the global situation where they've all picked X. And the 3 solid lines represent the global situations where one has picked X and the other 2 have picked Z. Okay, so it's just a nice graphic representation. Question. Can I predetermine these outcomes in such a way that no matter which of the 4 possible experimental global situations is chosen, the result will obey the predictions? That is, all x's odd, 1x and 2z's even. Can it be done? Now we've got a mathematical question. The thing is, it's so nice, right? So, first of all, let's just try. Can I predetermine? So what do I need to do? I need to write u or d in each of these 6 circles in such a way that all of the constraints are satisfied. One constraint is that along this row, there have to be an odd number of u's. Could be 1 or 3. Let's just put in 3 because it's easier. U. Okay, so I predetermined those. Now, if they happen to all pick x, I'm okay. What about this one? No. Pick something. I've got enough u's. I'll pick a d. What the heck? Now the other constraint starts to bite. You say, I need an even number of u's along this row. All right? I'm forced this way to put a u there. 5 out of 6, almost done. But now you're screwed, right? There's no way I can put anything in here that will satisfy all the constraints. This one requires it to be a u. This one forbids it to be a u. Can't be done. Now you might think, okay, you made a bad choice. You know, you started with 3 u's, start with something else. And that's where you get this very nice argument, right? This lovely argument of Merman. So Merman says, it's argument by reductio. Suppose it could be done. Suppose there was any way at all to put u's and d's in these circles that satisfy all the constraints. Fine. Now, pick up these 3 disks, throw them in a hat. I put in an odd number of u's. Pick up these 3 and throw them in the hat. Even. These 3, even. These 3, even. So, what's in the hat? Odd, even. There are an odd number of u's in the hat, but I picked up every disk twice because every disk lies on the intersection of 2 of these lines. So you can't do it. Period. End of story. No local theory can make these predictions. Quantum theory does make those predictions. That's an interesting fact about quantum theory. But the world does that. That's the more interesting part. Again, throw away quantum theory tomorrow, the world will still continue doing this. So you can't have a locally causal theory. No locally causal theory can be the correct theory of physics. Now we're at the end, right? Now we really have a conflict between relativity understood in terms of Bell relativistic causality, right? If you understand relativity as implying no superluminal causation, no locally causal theory can predict or explain the sorts of outcomes in this situation that quantum mechanics predicts. Further, they've actually been confirmed. As we know, the Nobel Prize was given for that work, finally recognized, unfortunately too late for Bell. So no locally causal theory can be correct. But violations of local causality seem to contradict relativity, at least if you understand relativity in a certain way. Again, this is the last thing, so I really am done. There's no obvious way a theory can admit of non-local causal connections without adverting to space-time structure that relativity does not contain. Maybe a preferred foliation. When I say no obvious, okay, there's a reason for saying that. In particular, it seems like to really make sense of this, you have to put a preferred foliation back in. At least you ought to consider it. I think it's the right thing to do. Not a conflict between relativity and quantum theory, it's a conflict between relativity and the actual outcomes of laboratory experiments. And until you really resolve that problem, you are not going to have a completed physics. End of story.
Maybe one quick question. Yeah.
I don't really understand the assertion that Bell, the violation of Bell inequality implies somehow causation at a distance. I mean, like the correlations, for example, predicted by quantum mechanics. I mean, this is a well-known fact. I feel like I'm saying something everybody knows, so this is where my confusion comes from. They don't allow any causal influence
Of
between
course
A and
they
B. They do. What do you mean?
I mean, of course they do. I can tell you where your confusion is. You're confusing signaling with causation. There are theorems that suggest, for certain theories, these causal connections cannot be used to send signals. Bell himself realized that, right? The first of these was the so-called no-Bell telephone theorem that he himself proves, but also says, of course, I can only prove this under certain assumptions about what the transmitter is able to manipulate and what the receiver is able to observe. But you can have causation that cannot be used for sending signals. In a collapse theory, where you have absolutely random collapses, but they're non-local, right? Alice does a measurement. She collapses the wave function. Because of that collapse, the physical state of Bob's particle over here changes. Yes? That's causation. Can she use that to send signals? No, because she can't control which way it collapses.
So the local state doesn't change.
Well, I don't know what you mean by the local state. Again, in every theory, we've got a wave function. The wave function's not a local thing. Right? But it's a thing. It's a physical thing.
Can I rephrase it? Wouldn't such a contradiction between the two imply that you can't encode a Bell experiment in quantum field theory, which contains both quantum theory and is the relativistic causality?
No, the standard techniques of making predictions in quantum field theory predict these violations.
But they also respect relativity. So the violations don't contradict.
Because the operators that are associated with space-like separated regions in quantum field theory commute. And if you assume things about what you can do that are associated with the permission operators, you can prove you can't signal. That doesn't show there isn't causation. Put it this way. Everybody agrees in Bohm's theory, okay? In Bohm's theory, there's obviously spooky action at a distance. That's why Einstein didn't like it. He knew about the theory. And he played with similar theories. And when Bohm rediscovers de Broglie's theory in 1952, he also says, gosh, the non-locality of this theory is there in your face. And Bell's whole point when he goes to write his paper is say, I wonder if I can get rid of the non-locality out of a theory that's like Bohm's. What he finds out is he can't for these reasons. Nobody disagrees that Bohm's theory is wildly non-local, but you can't use it to signal. You absolutely cannot use it to build a signaling device. Why? It makes the same predictions as standard quantum. Right? So no signaling isn't no causation. That's just a complete mistake. We have counterexamples. A manifestly non-locally causal theory where you can't signal.
But if we can violate Bell's inequality in a quantum field theory, and a quantum field theory respects relativistic causality, doesn't that contradict the...
I'm going around in circles.
Me too.
Quantum field theory, because it's a quantum theory, right, does not and predicts violations of Bell's inequality, no matter how you end up interpreting it, allows for superluminal causation. It doesn't allow, need not allow for superluminal signals.
So it doesn't respect relativity is what you're saying.
Now we have to say, what does relativity say? What is the content? Yes? You can answer that different ways. One way to answer it is to say, no superluminal causation. One way to answer it is, no superluminal signaling. Those are different, as I just showed you. One way to answer it is, the theory has to be Lorentz invariant, which is a little tricky because in GR you don't even have the Lorentz transformations, okay. One way to say it is, the only space-time structure you can appeal to in writing down your equations is a Lorentzian signature metric on a four-dimensional differentiable manifold. That doesn't say anything about whether things can be done superluminally. It says nothing about it. The classical tachyon theory is a relativistically invariant theory of particles that go faster than light. Is that a relativistic theory? Well, it can be written down using only a Lorentz signature metric on a four-dimensional differentiable manifold. It's relativistic in that sense. You have to decide what you think relativity says before I can answer the question, does this violate relativity?
Okay, so your assertion is really that it violates the spirit of relativity.
This is now a mature discussion, I think.
Yeah, maybe two more comments or quick questions and we move on.
Yeah. So I think, this is very relevant to the question you're asking. And I think one way to try to reconcile these different ideas is the formulation that I put up in my talk, which is to say that local causality is not what Tim said, which is just that causes are in the past light cone of an event. But as I said, I call that relativistic causal error. There is another ingredient in what Bell called local causality, which is this idea that correlations have to be explained, which I call Reichenbach's principle of common cause. And if you don't adopt that, in quantum theory, we don't have that. That's not part of quantum theory. So if your notion of causation is just that causes have to be in the past light cone, but you don't ascribe to the idea that correlations have to be explained, then you don't have to conclude from Bell's theorem that there is a violation of
I didn't talk about
causality. Yeah,
I didn't talk about explanation here. And of course, we could.
You did in a quote, in the very last quote. You did actually had explained in there, but yeah.
If you say, look, quantum theory doesn't explain. I'm sort of wondering what you think quantum theory does explain.
Well, you could say that it's
supposed to explain to be a decent. They do get these correlations, right? Alice and Bob do get these correlations. That's a physical fact, right?
Yeah. But you could take the point of view that it's not that. Yeah, well, you could take the point of view. No, you could take the point of view.
What's the job of physics if not to explain things like these sorts of?
Some people just say to make predictions.
Okay, you can be an operationist and say, I don't care about the physical world. I just care about making predictions. I'm not going to get into a fight with you and say, I care about the physical world. That's why I'm in this business. I don't really care much about predictions at all, except insofar as they provide evidence for or against a theory. What I care about is the
Isn't it the only way to interact with the physical world is through predictions, which you then measure?
Predictions give you evidence. Evidence are important because they give you grounds to accept or reject theories. They're not that important on their own. You think, why did they go to all this trouble to build CERN? Why? Oh, to get some stuff I can predict? Who cares? You care about those predictions because you think those predictions have a certain evidential status with respect to different theories. Physics isn't about predictions, it's about the world. We care about what we can observe because that provides us the evidence that we have that various theories might or might not be correct. If someone says, all I care about is making predictions, okay, fine, I don't know why you're doing this. I don't care. I care about which theories could work and what evidence do we have for or against different theories.
Is it quick? Okay.
Yes, but these are used to kind of string them together. This one to be used to contrast benzene the reality.
Well, but together they can see the necessary value. So obviously that this one.
An meiner Ferse, wenn ich gehe. In der Wanderung. Meine Schuhe sind relativ neu. Aber ich 8 Stunden zu.
Ah, yeah, right. Reality something.
I'll give you this, and then you can decide if you want to, how much time you want to leave there for questions.
Yes.
What, you don't think that knowing the observations are absolute? How does that actually work?
It's an attitude or take the one.
Surely that actually, surely that must play into the time.
Yes, but it doesn't imply that any agents of information are absolute. It just says I treat the so it's not
But then how does the knowledge change the way? Like, what if they did?
Some people write down if you observe
io che hanno scritto oggi è
Another agent cannot
hanno scritto
statement. This statement is made by it can be relative to.
Okay, so I guess we can start. We'll start with the talk from Renato Renner about many worlds. So I guess we can go.
Okay, thanks a lot. I would like to thank the organizers, which I belong to myself. But in particular, the main organizer, which are people who do all the work here, and of course also Nicolas, who got all the sponsoring, as we learned. Okay, so this is a talk about a problem with many worlds, and I already got complaints that there are many problems in many worlds, but I will only talk about one problem. And I'm glad people actually came to this talk, because this topic is so controversial that some people got a bit tired of it and don't want to hear more about many worlds. And actually, this is maybe nicely reflected by this citation. Chris Fuchs was not so recently, 5 years ago, asked why he's so critical about many worlds. And his answer was, he was really specifically asked, what are its main shortcomings? And then his answer was, its main shortcoming is simply this: the interpretation is completely contentless. Now, actually, I communicated with Chris Fuchs before the talk, because he actually was one complaining about this, that there's only one problem. And also with others, in particular also with the proponents like Les Wiseman. And if you, some of you here in this audience, at least I see 2 or 3 people have been to a nice workshop that Les Wiseman organized in Tel Aviv a little bit more than a year ago. And this was, and he now is writing an introduction to a textbook, or to a little book, a collection of works that arose in this workshop. And what he wrote in this introduction is actually something you could also read at the beginning before the conference started. He was very optimistic, and he writes that here: I was optimistic about bringing the many worlds interpretation closer to consensus. So he brought all these people together who were working on many worlds. And then he now writes, after the year after the conference, I was very wrong about it. There are so many radically different understandings of the concept of a world, even among the most enthusiastic proponents of the many worlds interpretation. Okay, and then he cites a few people like Deutsch, Wallace, Soucers, and so on. So maybe before I continue, because I want this to be slightly provocative, I want to take a survey. Because, okay, this is not a representative audience for physicists, because otherwise you wouldn't be here at the Bell workshop, probably, but in some solid-state workshop. So who of you thinks it's who thinks it's not unreasonable to assign a wave function to the whole universe? So you would in principle do that. It's not unreasonable to do that.
You mean believe there is one, or actually assign one?
Let's say believe there is one. Okay. So these people would think that it makes sense to somehow, maybe you wouldn't do it or wouldn't know how to choose it, but you do it. And who of you thinks it's there is a kind of collapse of the wave function inherently? Okay. Now, those who think that it's at least reasonable to assign a wave function to the universe and have answered the second question with no, so there is no collapse, must kind of have some view on the world where we have this wave function of the universe that evolves unitarily in some way.
Well, can I, sorry, just in the sense that the first question you just asked, who thought it was reasonable to do this?
Yes, right, it's reasonable.
Second question you asked, who believes that there is collapse?
Now,
which is sort of a...
Yes, now if the answer to the first question was yes, and the second was no. So if you find it reasonable to assign a state to the world, And if you don't think there's a collapse.
Okay, you're not committed to there being a collapse, say.
Yes.
Okay, so you have to leave that there has to be some other way that you could make sense of it.
Yes.
Okay.
Then you have to somehow proceed and still, I mean, there's now a kind of realist picture in a certain sense. Okay, I don't want to go too far with interpretations, but you assign a wave function universe and you think this wave function doesn't collapse, it just evolves unitarily. Okay, that's a view that now refers to another citation. I will later come back to that, which is also in this introduction that Les Wiseman is writing. And I think it's not yet actually published, it's just submitted. And he says, there's this interesting statement that someone else said, Michael Huber, but Les Wiseman cites that the majority of the physics community in fact preferred an unmodified realist interpretation. And if you read further, this is at least somewhat connected. You assign a wave function to the universe and think this is kind of an ontic state, or at least something real. And there is no collapse. And then he concludes that in order for these people to make sense of everything, the majority may already subconsciously be many-worlders. So those who said yes to the first question, no to the second, according to that, would somehow subconsciously be many-worlders. Maybe you have never thought about it, but I don't know.
Can I do this now?
Yes. I think this is why I said at the beginning we made this disclaimer. This is not a typical audience. And I think the point is that most people, if you ask them in the right way, like, okay, people don't want to agree that there is a fundamental collapse. So that's why I asked this question in that way. Like, do you think it's reasonable to have a collapse? And of course, I knew Nicolas will raise his hand, but not many others. And then the alternative is maybe unitary. And if you find it reasonable to assign a wave function to the universe, then you are in principle, if you now don't think further, and I think this is the exception here, people here think further, you would somehow be forced to now make sense of that universal wave function. And if you're now forced to connect that to the experiences we have, you may go into that many-world terrain. Okay, I'm not claiming you are doing that, but the majority of physicists is maybe many-worlders. And so this talk is actually, one purpose of this talk is to maybe, I mean, I guess most of you are not many-worlders. Or who is actually a many-worlder here? Okay. Okay, so
take him out.
No, the talk will only be directed to him. And everyone else who has friends who are many-worlders.
Well, I think you should allow for undecideds who may be influenced by your talk.
That's okay. I can extend my audience. I'm glad about it. Now, okay, that's the situation. Okay, I said it's a bit provocative. One could phrase it like that. So the opponents claim it has no content. The proponents don't agree on the content. But most physicists are subconsciously still many-worlders. So that's a very interesting situation. Yes?
Maybe you should ask, in addition, how many physicists believe there are many worlds, and if not many people raise their hands, that conclusion is not true. So yeah, I guess the fair conclusion
in this audience
is not completely true.
So in this audience, you have a non-employed of physicists that belong to that category.
Do you take into account the answers in all worlds or in only the
Okay, now, okay, that was the citation and introductory part of my thing. So the actual question, I want to be now, if you take it from that, if you start from the viewpoint it's contentless, I want to be much more generous and say, let's suppose we add content to whatever this is supposed to be. Can we do it in a consistent way? And I will explain, like the rest of the talk will, or most part of the talk will explain what I mean by that much more precisely. But I just want to like return to, I just said many worlders don't agree on the picture. And whatever I'm now saying is most likely if there were many worlders here, they would disagree with it, at least in that world where I give the talk.
Zero information content.
I'm taking here this thing of Everett. Sorry?
That's zero information content. They disagree with everything among themselves. So,
with themselves.
Okay.
But I think that's a picture that Everett, a drawing he had in one of the early versions of his article. And okay, I just want you here to take the message. So it has something to do with trees. So whatever content we invent and assign, add to quantum mechanics to get to many worlds, somewhere we want to have something that reflects this tree structure. So what does this mean more precisely? So what I would like to do is to follow. I will have many slides where on the left-hand side will be what I call unitary quantum mechanics. So that's the thing if you believe basically what I asked at the beginning, and if you answered the first question with yes and the second with no. So if you think there is really a state of the universe and it evolves unitarily. Let's just assume that. So that's the pure quantum theory point of view. There's just a standard unitary evolution, nothing added to it. And now, of course, one could say Chris Fuchs' position would be, if you now just have words about that and tell stories, that's basically not a good content. We want to be able to add something that we can kind of capture, maybe, and that's the thing I want to do, to even get into some at least more or less precise mathematical frame. So let's suppose you could say we want to add to the mathematical structure of bare quantum theory, unitary quantum theory, some additional structure that somehow reflects the idea of many worlds. And the question is, can we do that? And so the way I want to do that, I want this structure to somehow reflect this idea of the branching into worlds, because we talk about many worlds. So what is that more precisely? So in order to do that, I will use one word which is admittedly not a standard expression. I just use it because I think it's intuitive, that of an instantaneous world. And what I mean by that is in this branching of worlds. So in many worlds, we have at any point in time different worlds. And so in these diagrams, we have time going upwards. So in quantum theory, time going upwards means the state just evolves unitarily. There's one initial state, psi 0, at the Big Bang, let's say, and then it evolves. Now, in this additional mathematical structure, we have worlds. So these are the red dots. And maybe at the beginning it was only one world and then split into two worlds. But when I talk about worlds, it's not so clear whether I mean something that is continuous in time. So I use this word instantaneous worlds for really one dot at a time. So this is a time slice, this is a time slice, and this is one world. So in one world, intuitively, we really have a state of the system. Yes?
You are already committed with the fact that in this situation you have two worlds independent on alpha and beta?
Yes, I will comment on that.
Under some...
Yes. So, okay, here, of course, typically what I would say is whenever alpha and beta are not 0 or 1, then we have a non-trivial branching, and then the worlds have some weight and so on. I will not talk about this
not
weight.
Many according to the weight.
Yeah, so I will not, okay, this is the part of, there are many problems with many worlds. I will not at all talk about the weights of the world. I will just assume that usually I have a branching if the weight is not 0. I mean, the weight 0 is easy to understand. This world shouldn't exist in the sense, but I will also come to that. So indeed, here you see something about the world. Normally what people would do is to assign some amplitude or then a weight later to the world. And the typical relation between the quantum theory picture and the many worlds picture is that if you add up the different states in the different instantaneous worlds with the corresponding amplitudes, you get the state you have quantum mechanically according to the unitary evolution. But as I said, I will not go further into the meaning of this alpha and beta. It's just that this is the typical picture I think you will find in many articles about many worlds. I haven't yet said something I want to try to make this more precise. So one thing that I think is important for this talk is the following. If the worlds, the instantaneous worlds alone would not give a very interesting structure, because that would basically mean I'm just saying at any point in time there are different worlds, but there's no continuum in time. And what we expect from a physical theory is at least to say something continuously. We want to say, if I now have the memory of me standing here a minute ago, that's still somehow the same world, or something in that direction. So what I want is to have on this many world part of my mathematical framework, the thing I add to quantum theory, some structure that gives me at least some information about time continuity. Otherwise, it's as if I would randomly be in any world and so on. And I will make precise what I mean by that. But roughly, it's motivated by this tree I showed at the beginning that Everett drew. So Everett has drawn these branches, and what I want at least is that these legs here, the branch, have some meaning, some well-defined meaning. So one could say, like the intuition, if you read Everett's thing, is that these branches actually define the past. If I'm in an instantaneous world here, and then I go back in this tree, then what I can say is that this was in my past. Or that's kind of the terminology that is used. And then we can go back to the very beginning, and this Big Bang, I just mean it's kind of the origin. If you take a many-world viewpoint and you have a wave function of the universe, it makes sense that you have some initial thing where no branching has occurred somehow. This is usually not made explicit, but it will have some meaning here. Okay, now just to illustrate the many-world or the things that come up in an interesting example, which is, of course, Wigner's friend.
Just ask you, do you say something about under which circumstances I can draw a line?
Yes, I will say yes. Okay. So the goal will be to make all these notions now more precise. So we'll, in 2 or 3 slides, come to the more well-defined part. So this is still to get intuition of what I want to do. Now, I have hearing Howard's talk this morning, I realized this slide only makes sense. I want this to be a Wigner's friend slice. So I have to make the assumption that if I was the cat, I would have the same perception as I have now. This is a reasonable assumption. Okay. So that's, I think, the spirit of what you're saying. So this is a Wigner's friend experiment where the cat is the friend. And now, how would you model that in this tree language? And this is pretty straightforward. So this is the initial state of the cat is some superposition, or not of the cat. Sorry, the cat is in a ready state. She hasn't looked at the system. Okay, maybe I should remind you. The cat observes a spin, and the spin is in some superposition state, alpha up plus beta down. Now the cat observes it, and this is the usual thing you read in the many worlds literature. Now the world splits, and there's a cat that has seen spin up and one that has seen spin down, and the cat knows that. So that's the thing in quotation mark, that's the knowledge. And now Wigner, who is outside, hasn't yet observed the cat. Now, if Wigner measures the cat as indicated on the previous slide, just in the up-down basis, which just means he opens the box and asks the cat, did you see up and down? Then, of course, he will all still split in the same. I mean, there will be no further splitting, so that's why this is grayed out. So if you are in this branch, you will just see the cat up, and here you will see that the cat has seen down, and you will see the spin down. The more interesting situation is if Wigner measures in this basis, in the superposition basis. That's the Deutsch extension of Wigner's friend experiment that was mentioned several times, and I think Caslav has written a lot about it in the literature. I think so. The friend now measures the cat in the superposition basis. And let's assume alpha and beta are equally large in this case. So there's this equal amplitude. How would the tree now look like? And here you can already have a kind of argument how it should correctly look like. Because you can say, okay, the first part is clear. The cat just observed the spin. Now in the second part, what happens is Wigner observes the cat in this superposition basis. So how should we now connect this outcome? What we know from quantum theory is that at the very end, if everything is unitary, what Wigner will observe is he will see in this plus state, which was defined as the positive superposition of the cat that has seen up and down, basically of the state this plus this state, and he will not see it with a minus phase. If I draw it in that way, there are two instantaneous worlds with the same state inside, and now people could argue, no, okay, maybe it makes more sense to actually re-merge the two. There's not only branching, but also merging. And there are discussions about that. What is clear is that these branches here have weight 0, because according to quantum theory, they don't occur. Now, it's important, because I just said, many worlds don't agree on how to do many things. And here, I think this is the first point of disagreement. When you talk to them, it's not clear whether they would now do the merging or not. Some do not.
Oh, sorry, that L is...
Yes, the L is now, I didn't want, yes. So this was, yeah, I forgot to make you emphasize this. So I don't want to write this superposition state all the time. I just called it the plus state of the whole lab. Okay, so this already shows it's not so clear how to draw these trees.
Sorry. Go back, please.
Yeah.
Go back.
Yes?
I don't know, why is weight zero? Why is minus impossible?
Why is minus impossible? Yeah. So actually what I say here is that this and this together have weight 0. So indeed one could somehow say maybe if I would have started everything from here, then this would just be an unequal superposition. But I know from quantum theory that these things don't occur. But as I said, here is already some potential ambiguity. And I don't want to claim that there's a unique way to do it. Now, the technical question I would like to ask is it always possible when I have an experiment to draw a corresponding many worlds tree which makes sense? And making sense, I want to define in terms of certain minimum, I mean, that's only a personal thing, but some minimum assumptions that should be satisfied. So in other words, I want to take a more axiomatic approach and say, okay, at the end I want to describe additional mathematical structure that we add to pure quantum theory, to bare quantum theory, which will have the form of a kind of graph. So a mathematical graph somehow reflects this branching structure. The vertices are these instantaneous worlds, and they are labeled by the states that are in these worlds. I will also make this more precise. And these edges are defining the past of the worlds. So that's the idea. So the question is, can we make this precise? And now come the more precise slides in a sense. I mean, I'm not claiming I'm on a completely mathematical rigorous level, but now we are going into a more precise treatment. So this is a kind of definition which is already bringing in an element which, I mean, of course, if I add structure to quantum theory, I need to take something that is not already there. And so what I mean now by a many-world representation of a quantum mechanical experiment is the following. So the quantum mechanical experiment in pure quantum theory is just described by a sequence of unitaries. And with that, I cannot draw a tree. So what I at least need is some criterion to say, when do I draw a different world or a different vertex? So now the idea of many worlds is, of course, to capture the fact that we have different perceptions. Like if I'm this cat and I see up, then there should be a world in which I've seen up. So this is now, if I'm this cat here, then I've seen up. There should be a corresponding vertex in this thing that shows me up. So by definition, what I'm now defining is the many-world structure belonging to a quantum mechanical experiment is a graph, in the graph theoretical sense. So it's a set of vertices and a set of connections, of edges. And this graph has the additional property that each vertex, should be intuitively understood as an instantaneous world, has as a label a time, which is the time of that world, and a state which describes the world in a state that some observer has perceived. Yes?
So far, all your graphs were trees. Will you have non-tree graphs later?
So I haven't, that's a good question. I haven't required that it's a tree at this.
That's right, yes.
So it's just a graph. But now there will be additional assumptions. So basically this definition it's some graph where the labels correspond to perceptions that some observers have. And what are the observers? I leave open. I mean, someone who translates or who wants to add structure to an experiment, of course, has to decide whether a cat counts as an observer. And I cannot give a criterion for that, but for me, it's an observer. Okay. So in this particular case, we could say, okay, there is, we have these labels. So far I've just said there is a graph with such labels at the vertices. Each label is always a time and a state of the world. So the previous thing was a bit incomplete. So you see, it's always the state of the whole world. Here the world only consists of the spin and the cat. And now there will be 3 criteria that I want to introduce. The first I call T, for time continuity. And this means the following. Okay, this picture is maybe, one has to always see them, it's always a condition only in one direction. So what I'm requiring is the following. You're only allowed to draw an edge here between vertices at subsequent times. Now this is a bit what I here assume for simplicity is that we have a discretization of time. Of course, one could do everything continuously. I think that's not, I mean, mathematically it's probably much harder to do, but because then I have a graph with a continuum of vertices and so on. But let's simplify that and assume there is a discretization of time just for the purpose of making this presentation simple. And now I can, the only vertices, the only edges that exist are such that connect two subsequent times. So I cannot jump in time to the past. So that already restricts the graphs. So the graphs now they're not yet trees. They will never be trees necessarily, but they are something that has these level structure. Maybe there's a term for that in graph theory, I don't know. So this basically means the graphs, you see this is already implemented here, but now there is a second criterion. As I said, there will be three. The second one is the criterion that I call P, because it has to do with something with past. And this is not yet the criterion, this is a definition I need. I call something a many worlds past if there is a path to that vertex. So if I say V, the vertex V, which is an instantaneous world, lies in the many world path of this instantaneous world if there is a directed graph. So still the idea is you can still draw any graph you like as long as you satisfy this criterion. So you may in particular draw a graph that has basically no connections. So up to now I didn't require that you make a connection between time ti and ti plus 1. I just said you can only make a connection if there's a. So in particular it could still be an empty graph. And that's still true. And now this criterion P still restricts the vertices I'm allowed to draw. And so what I'm requiring is that if there is a many-world past, then there should also be a quantum past. What do I mean by a quantum past? I mean, if this vertex here lies in the many-world past of this, which just means there's a path here in this representation, then there should be at least some non-trivial overlap between here and here. So this somehow, okay, I mean, one could now ask, why are these good criteria? Let's discuss that later. It's just somehow wants to say that if the many worlds past is somehow connected to what past means in quantum theory, this is the only way I can say this is an allowed past, that if I go back or if I reverse or time revert from the present with the U inverse, do I have overlap with that thing? Then it can lie in my past, quantum mechanically. So criterion P just asks that I only draw, if for any path that is in this graph, it has to be quantum mechanically allowed. So now it's still possible to draw a completely empty graph. I mean, empty in the sense it only has vertices and no edges, and it would still satisfy all criteria. Now I have one last criterion that will enforce that one draws at least some edges. And this is that everything that is possible quantum mechanically, and I call that non-empty worlds, should have a path to the root. I mean, root is just defined, it's not the graph theoretic root, actually it's just the time, there is a time zero. So assume that there's an earliest time, and let's call that vertex the Big Bang for simplicity. It doesn't have to be the real Big Bang, but there's an earliest time in this consideration where, actually I don't necessarily assume the world has not branched there, but there has to be some earliest time. And now the requirement is that if there is a world here which has non-empty weight quantum mechanically, which is well defined, it just means if I evolve from the Big Bang to that world, it has a non-zero amplitude, so it's a non-empty world, then it should have some path to the past. So if there's a quantum mechanical connection to the origin of everything, then, or if the state is possible at all, it should be connected to the Big Bang. So this is how this is written. So more precisely, so if this overlap is non-zero, which just means the state has a non-zero weight. So this is the only place where the weight actually comes in of the state. So I'm saying if a world with a non-zero weight should be rooted somewhere in the Big Bang.
Yes. Was there, maybe I missed it, was there a requirement that the states that you write down be macroscopically distinct from other states or anything like that?
Yeah, so that's implicit by the assumption. So I said, okay, that's this definition of what is a many worlds graph, where I said the labels correspond to observations different observations an observer could have. So typically I would, of course, say observations that are different observations are orthogonal and are typically macroscopic. But you could, in principle, say you call, for example, a Wigner's friend that is only a qubit. I mean, you don't do that. A qubit is, and that would not contradict. You could still use that whole thing just with that definition.
But you don't require that each node at the same time has a distinct
Oh,
state.
no. There could be nodes with the same label even, because actually there was, yes, maybe I can briefly return to that example of the cat. So here I'm allowed to draw, so that would not contradict any of the postulates I had, despite the fact that this thing has the same label as this one.
But it has a different past, and that's why it's allowed to.
So one could say, maybe I mean, I'm just leaving this possibility open. I'm not saying you have to do that, but I'm saying maybe a many-worlder wants to say that if the many-worlds past was different, even though the state we see is now again the same, it's maybe a different world. Some do that, and that's why I said here, some people say this should be merged again, which is also a valid graph, or not. Yeah, thanks. Okay. Now I have, okay, these are the criteria, and now the question is, can we fulfill these criteria? And of course, that depends on the experiment. I just showed some where this criterion is fulfilled. But, of course, I mean, this is probably not a surprise. I want to have a no-go theorem. So the goal is to say there may exist experiments for which it's impossible to draw any such many-world graph that satisfies the three criteria that I have. And what is a candidate for such an experiment? It's one that we have basically seen already as well in Howard's talk, and it's based on this, I mean, I base it on the work I have with Daniela Frauchiger, but one could equally well do that with these initially entangled Wigner's friend, who are then measured by their individual Wigners that Caslav proposed. So the idea is really to do a Wigner's friend experiment and combine it with a Bell experiment in a sense. So that's also the connection to this workshop, if you want. And I will now not go into the details. That would take too much time. I'll just show the idea. So it's the experiment that was proposed. Now here time goes from left to right. So there are two friends who are somehow doing some experiment together, and later they will be measured by some super observers individually. And now all these observers, so I will now assume in this experiment, whenever one of these observers sees something, then that's a label of a vertex. So here it comes in there. So I'm already going beyond pure quantum theory, because pure quantum theory wouldn't care whether this is a cat or not. But now I'm saying the vertices have to be labeled by observations that some observer makes here, and this is, for example, the cat sees here up or down and so on. And now, in this case, the whole thing is more complicated because there are so many observers. So I could say, if I now look at the time slices, there are now the different worlds. Like at the beginning, that's time 0, there's just one world. Now the universe is only this experiment. And then later, one cat has made an observation, then the second one has made one, this gives 4 worlds. And then come these measurements from Wigner, and they could split the world again more, where some labels are now identical, again, as before, potentially, and then the other Wigner measures as well. And now you can invoke the different assumptions. So the first assumption is, I want to say I can only connect vertices that are at subsequent times. So these blue things are now possible edges. So I cannot draw any additional edges in this graph, because then I would violate this time continuity. I cannot draw it from here directly to here, for example. So the blue ones are now just the ones that are not excluded by t, by the time continuity. Now comes an additional assumption, which is this p, the past assumption, that if there is a many worlds past, so if there is a path, for example, if there is a path, let's say from here to here, then there should be an overlap quantum mechanically from here to here, but here there is no overlap quantum mechanically, so therefore I put here this red thing to indicate it's not allowed to draw an edge here. And also here there's no allowed one, and here. Okay, and the idea is just I work myself through these assumptions. And actually there are more, because remember the past is not only by individual vertices. For example, I know that there is no overlap between here and here. I mean, I don't show that now, but that's something you can calculate quantum mechanically. That's straightforward. And then you know there should be no path from here to here. So, however I fill up these blue ones, which are possible edges, I have to avoid constructing a path from here to here, because otherwise I violate assumption P. But now there's the last assumption, B, which says non-empty worlds have to be connected to the root. And here I have a non-empty world, which is actually here two possibilities of the same label. So at least one of these two, that one or that, has to be connected with the root. But now you see this is impossible, because here clearly there is no connection to the root. And here I already know if there's a connection to the root, it has to go through this, but it should not be connected to that by a path. So I cannot fulfill the thing. So that was very fast. It was only to give you an idea of how the proof works. It's very graphical. You just take this graph and try to enforce the criteria, and then you find there is no possibility left. And by the way, if you have questions on the proof, my co-author, Katrin Gerhard, is also here and knows all the details of the proof that we worked out in last minute. Okay, so this brings us to the theorem, which is basically saying, okay, there's already a definition here. So the many worlds graph is already, so you could say there is an additional assumption, which is what do we mean by a many worlds graph? Namely, that it's even a graph and that it has these labels that are words. But I think otherwise it's really no content if you don't assume that. And then there are three assumptions which you may think are reasonable. I mean, I think they are reasonable, but we know they cannot be satisfied at the same, I mean, they cannot all hold generally. There are experiments such that there's always at least one violated. And I think this explains somehow why it's so difficult to fill many worlds with content. So, because somehow when you want to fill it with content, clearly you want to be continuous in time. That seems to be undisputed when you talk to many worlds. There are some extreme positions which say many worlds is just instantaneously, there are always all these worlds. But then you run the risk of, again, being like in this realm that Chris Fuchs criticizes, which is basically, now you say nothing, you just say at any point in time, anything can happen. So you want to at least have some maybe time continuity to say something. And then there are, of course, the other assumptions that you're compatible with the quantum fast. And so apparently this is difficult to do. And yes, that's all I wanted to tell you.
Oh, thanks, Renato. It's very interesting. So there is one paper by Veronique, Philippe, Flavio, and myself that I want somehow to understand the connection if you see any.
Okay.
And this paper is a variant of the Wigner's friend, in which, if I may, the usual Wigner's friend can, one interpretation is that you can't assign the joint probabilities for Wigner and the friend at the same time. In this variant, we have only friends' outcomes at different times. And the outcome is, again, the same. You cannot make a joint probability between different outcomes at different times. So there is no, let's say, classical story, if you want, that this history exists.
Yes.
Do you see, I see that it's a completely different, it's also tailored for many worlds. Do you see some connection? Could this past hypothesis be related by the hidden assumption that there is some kind of a classical history, in a sense?
Yes. Yes. Okay. I mean, it's difficult to now say something because I haven't studied that paper, but I would say, yeah. In print, so what is maybe special for this particular thought experiment is kind of at the end there are not quantitative assumptions. It's only about, is there something zero or not, which makes the assumptions kind of weaker. I mean, we're just saying if there is a world, it has to have some overlap. And for example, the overlap could be different from the viewpoint of different, let's say, agent in different worlds, so to speak. If you would renormalize, like one agent just sees that outcome and renormalizes all the probabilities conditioned on being in that world. Then, of course, he gets different values for the probabilities, like conditioning can change that. So we want to be kind of stable towards such changes. So I could imagine that if one now requires really joint probability distribution, this is somewhat a bit more rigid, because you're saying it's also quantitatively something everyone agrees in a sense.
No, I understand that the argument is deterministic, but that flavor, whether this
yes, I think from the flavor, it's similar, because I think if you introduce a joint probability distribution, then you somehow, I guess it's a joint over all times. So it's not a joint distribution over one time. Then you make a connection between the different times by saying these results that were earlier there still exist later in the probability distribution, although the friend may have been measured. So I think, yes, I would say this probably via that requirement you also introduce the notion of a compatibility with the past. Yeah, that's a good point. I have to think about that. But yes, almost certain it gives a condition on the past because it talks about an earlier variable connected with a newer one. So it is some consistency. Yes, now the many worlds first.
So I like the attempted separation into many worlders and non-many worlders. But now I have a more serious question about trying to understand some of the conclusions from what you presented. So in such a, say, extended Wigner's friend scenario, which I think could be imaginable, somehow given the initial question, can you describe the universe with one wave function? So I guess based on the answers, most people could imagine assigning one wave function and unitary evolution to that, say, extended Wigner's friend lab, which is, by the way, what I would understand under many worlds, but is contentless yet. But somehow, if you take such a description, so now based on what you say, this is somehow not compatible with these relative notions of me myself being in such a situation, I have made an observation that I want to describe it consistently with quantum mechanics. So you're saying that somehow the branching explanation does not work, but does such an argument say that somehow the description of that system as a quantum state that only unitarily evolves is in itself inconsistent?
Yeah, no, I would say I'm not saying anything about the unitary evolution. So I'm only here saying that there is an inconsistency if we add structure. So without, like, as long as we stay just in the unitary picture, which is for me the contentless thing. So if you just say you believe in unitary quantum mechanics, but don't add anything.
So I'm a many worlder
without content. Yeah, because what I want to do is to say if these people have something to say, it should be somehow possible. Some framework, and of course they could disagree with the framework, and that would already be interesting because I don't usually understand what they mean. So I just try to say what are the minimal things they can all agree on, and that's in the sense I try to be minimal. But one additional point, you now use the word if you know the state. So there's also this concept of world. So what is really important for this to even make sense is that this is kind of a realist picture in the sense that the branching has to be something absolute in some way. So if you have a relative branching relative to you, which is probably against the spirit of many worlds, then you are more in the context of the framework that Gilles Brassard will or is proposing, where you have parallel lives. That's a completely different thing. So here it's important that this is a kind of supposed to be a realist picture. We have this wave function of the universe, and also the branching structure is not for every observer different, because then otherwise in the Wigner's friend experiment you could say every agent just sees one little piece of it, and as long as you don't put them together you see no problem. Yeah. So in that sense, the subjective many worlds interpretation, which I think is the parallel lives interpretation of Gilles Brassard, doesn't run into this problem.
Okay, there's still like 3 questions, so if you can keep your questions and your answers short.
Yes,
in the back first.
So, first of all, just a simple technicality. Like in one of the first slides, when they measure the lab and 2 things, essentially, if you merge together, they have 0 weight.
Somewhere here, probably, or something.
No, much earlier. Oh, yes, this is one. So did you continue with this? Did you allow in that your final proof to have the zero weight and take them away? Or
yes, so so if this here continues in a way, so at the end the criterion just says you shouldn't, I mean, you can keep that vertex. So technically you can always keep the vertex. At the end the statement is just about a path. At the very end you have, so what I want to exclude is, so for example, this one has no overlap with this. So what the criterion forces me to do, or let's suppose, okay, it's the opposite. So if we talk about the past thing, so this thing has an overlap with the initial. Yes. So therefore, this is a possible world.
Yes.
So the criterion applies to those that don't have weight zero. So what I'm saying is this has to have a path to the past.
No, but in your proof, how do you deal with those that have weight zero? Do you eliminate them? Or
they are not relevant because there's no condition on them, in a sense. So the condition, like the criteria that it has to have a path, only applies to those that don't have weight zero. So nothing is asked for them, about them. So they can roll them or not, and this doesn't affect the criteria. Sorry, this was not the short answer.
Only combine those two things. Yes, not each of them.
I mean, each one has, as a quantum mechanical thing, has weight zero, so therefore I don't require anything about them. You can, for them, draw whatever paths or not paths you like, because this has just no overlap with that.
So the time is up. So let's thank Renato one more time. Small announcement for the glacier excursion tomorrow. So the weather is too bad. It's not going to happen. And if still you want to have your lunches packed, so you can go on a walk somewhere, whatever, you have to say it yourself at the reception before 7 p.m. The piece of paper we gave before is thrown away. If you didn't.
But the two evening talks are officially moved to end of afternoon, right?
Right. Yes.
Yes. So what time? At 4?
At 7:15. Huh?
No.
It's 17:15. Sorry. At 5:15. 5:15. 5:15. Yes.
Will you update us on the schedule downstairs?
Yeah, I will. We will do that.
Yeah.
We will do that. Okay. So now coffee break.
Also ich finde das ziemlich cool.
Try, but would not use it.
Yeah, what is left? Yeah.
They wouldn't. I'm just guessing.
I'm sure. I mean, I would be really interested whether is it actually yes. Anyone?
One guy.
Not here, but I mean, in the world. Like it was you had a conference full of people. Like the guys actually.
So I give you a list.
Yes, the experiment. Too busy.
Yeah.
You can spin it.
You took my space.
I'll move on.
Sì, ho provato già. So, okay, let's start this next session. But before that, Max has an announcement for tomorrow.
So, the big glacier hike is, of course, not possible, but there is a sort of smaller, not so far up the mountains, stroll around the lake that with the... Louder, please. Sorry. So in place of the glacier hike tomorrow, one could instead have a more relaxed stroll around the lake, starting at a town just down the road called the Pion. So if you'd like to do this, it looks like we can go there with a bus. Walk around should take about an hour and a half, probably longer with a group, and then get the bus back. The bus is 20 minutes. But the timing-wise, and because of the times of the bus, it looks like we would have to get packed lunches. So if you want to do this, there's 15 minutes between the end of the session and the deadline for talking about packed lunches. I'm happy to sort of, vaguely speaking, organize things. But if you want to come, one, let me know, and two, tell them downstairs that you want to pack lunch.
Immediately after.
Immediately after the session, within 15 minutes of the session.
Yeah, by 7 p.m.
And if the weather's bad.
Oh, sorry. There is some risk that the weather is so bad that even that is not possible. I don't know. In which case, you'll be stuck with a packed lunch. That's your risk to take.
So now the next two speakers will be via Zoom. And we start with Markus Aspelmeyer on quantum surfaces of gravity. So Markus, you can start.
Thank you very much. I hope you can all hear me well.
Yes.
Okay. So first of all, I have to sincerely apologize that I was not able to make it, and but thanks a lot for providing this opportunity. I hope you find it less annoying than I do when I have to sit in an audience and listen to a video lecture. So the topic is here. It's in the title, quantum sources of gravity, and the background is that over the last 20 years there has emerged really a new opportunity for probing gravity in a quantum regime, and I would like to briefly sketch what it is about and where we are experimentally. So what it is about is very simple. We ask the question, what if? We would be able in the lab to have quantum sources of gravity? And what I mean by that is something very specific. Namely, that we have, like here, is a Boxer mask configuration that comprises a superposition of states of a single system that are gravitationally distinct, which means they can be distinguished through gravity experiment. That means, in particular, that if you have an outside observer who can interact with the system, that gravitationally, that over some time of interaction, this observer becomes entangled with our gravitational source. To give you a specific example, if our mass is, for example, a superposition of macroscopically distinct center of masses of a massive object, and our observer is a clock, then through gravitational time dilation, we will have the clock interacting with the two different mass configurations. So the clock is separated with two different distances now of the two states, which leads to the gravitational time dilation, and hence after some time to entanglement of the clock with the mass. And if you just take the typical time dilation, so the difference in gravitational potential over c squared, which corresponds to a frequency shift that you would have to be able to resolve with your clock. And if you assume, let's say, typical values, meaning, let's say, Planck mass for the mass, superposition size of a few hundred nanometers, and separation of the clock to our superposed mass of a few micrometers, so all of which you could imagine in a state-of-the-art experiment, then you would need to resolve a frequency difference of 10 to the relative frequency difference of 10 to the minus 32 in order to generate gravitational entanglement. Now, where are we with experiments today? If you look in the literature, the latest experiments, for example, in the Niels group at Schiller, and another independent experiment, they are now at the level of relative frequency stability of 10 to the minus 21. So there are 11 orders of magnitude missing. So right now, it's not realistic to perform such an experiment in the lab. This is, of course, put in a much broader context and goes back to at least the famous Chapel Hill conference in the late 50s, where this question was already discussed quite in detail. And I quote here an Austrian physicist who was present at this meeting also, and I think he posed this question in a very nice way. Namely, he asked, can we have phenomena which the classical theory of gravity, so meaning gravity of quantization, is unable to explain? And back then, Feynman also tended in this innovative way of addressing these things. This was his answer, yes. And what he explicitly proposed back then was to design an experiment that has some sort of quantum interference in combination with gravity. And what he proposed was, what about if we have an object, a massive object, and some sort of Stern-Gerlach device that if there's a spin inside this mass, we can create a superposition of the center of mass degree of freedom of this massive object. Once we have that, we can actually take a second mass, a test mass, gravitationally coupled to this object, and then we have a situation very reminiscent to my first example in the beginning, namely a mass in a superposition of two macroscopically distinct center of mass stays gravitationally coupled to a test mass, which after a certain amount of time will evolve into an entangled state. Now, the relevance of that experiment, this Gedanken experiment, is of course that no classical source mass configuration would be able to produce entanglement. If you think about it in terms of just relativity theory, any source mass configuration will result in a fixed spacetime metric within which the test mass follows the geodesic motion. So if at any time in the beginning of the experiment the two masses were separable, geodesic free motion along a geodesic will always result again in a separable state. So what you require in order to generate entanglement is a superposition of the spacetimes that actually creates the geodesics, and this is not a valid solution of a classical field theory. Hence, we do have an experiment. So entanglement observing entanglement in such an experiment is something that classical field theory of gravity is not able to explain. So this is what all of that is about. There was another person at the meeting, Louis Witten, the father of Ed Witten, and he asked a relevant question for this talk, namely, what prevents this from becoming a practical experiment? And so basically back in the 50s and 60s, this was of course beyond any experimental capabilities. As time progressed, so whenever new experimental methods became available, there have been then proposals how to possibly create quantum sources of gravity in the sense that it introduced in the beginning, such that you have states in superpositions that are gravitationally distinct. So, for example, when BECs came up and the insight that in principle you should be able to create a superposition of a BEC with all atoms in one location and in another location, it was Asha Perez who wrote the first paper on how to actually use such a superposition to create a gravitational field in a superposition and possibly test that. Also there the numbers were quite, let's say, daunting. When solid-state systems emerged in the field of, let's say, quantum-controlled objects, like 10, 20 years ago, these ideas were then also transferred to solid-state objects, and then starting in the mid-2000s, several proposals then emerged how to realize this Gedanken experiment using quantum-controlled solids. I show you just two examples here. So this was the work of Bose et al. And Maletta Medral et al. In 2017, who followed really the original path of Feynman, having a mass with a spin degree of freedom. And their approach was, well, use one mass in a initial superposition of center of mass states and gravitationally couple this mass configuration to another mass that is in a superposition of center of mass states. What happens is that the mass here, for example, sees the gravitational field of that mass, and what happens is that this mass here picks up a dynamic phase due to the evolution in the gravitational field of that one. The same happens, of course, for the other states. So what happens now is that conditions on the position of this mass picks up a dynamic phase, and over the time evolution, the initially separate state of the two superposed sets of mass states evolves into an entangled state. And this is, of course, very reminiscent of a conditional phase gate, where basically your target and your control bit, qubit R, start out in superpositions, and then after you see phase operation, they become entangled. The other possibility is that you have two harmonic oscillators. So here a mass here in an harmonic oscillator state, the mass here in a harmonic oscillator state, and they also couple now gravitationally, just via a 1 over r gravitational potential. If you Taylor expand that 1 over r interaction, then the first non-trivial interaction term between the two masses is an XX coupling, and this is of course the famous two-mode squeezing operator that you know from quantum optics that entangles the center of mass degrees of freedom of those two harmonic oscillators into an ETR space. Now, the interesting thing is, of course, you can, for both cases now, you can compute the rate at which entanglement is generated between those two systems. In that case, you have a delocalized coherent state twice that is coupled via gravity. Here you have a center of mass in a superposition separated by an amount delta x. And if you now compute the rate of entanglement, even though those two experimental configurations look quite different, the rate at which entanglement is generated is actually the same. So the expression for the rate. Namely, the rate at which entanglement is generated is case with the ratio of Newton's constant and Planck's constant, the mass square because of gravitational coupling, the delocalization square, and 1 over dq, simply because this is the first non-trivial distance relation configuration here, delta x, is now the spatial separation of your initial center of mass superposition, and for the two Gaussian states, the delta x is the delocalization of your single mass wave packet. Now, in order to generate entanglement, this rate here needs to be larger than all the decoherence rates in your system. And now, instead of using decoherence rates, I use coherence time for these, simply for reasons of practicality, and I can rewrite now this expression here in the following way. I can write that as the condition that the mass square, the delocalization square, times the coherence time, times the distance cubed, so 1 over the distance cubed. This factor here has to be larger than h bar over g. So this is a necessary precondition for all experiments that want to generate entanglement via gravity in the in one of the two configurations that I showed you before. The nice thing about this expression, I already indicated it here, is that you can separate it into two parts. You can separate it into this part here, the mass square, the delocalization square times the coherence time, that you can now try to maximize in independent quantum experiments. So just if you take a single massive quantum object and you try to come up with an experiment that maximizes this expression. At the same time, you want to have 1 over d cubed in a gravity experiment as large as possible, meaning you want to make the distance between two gravitating objects as small as possible. And this is clearly something that you can establish independently in gravity experiments. And this is what I want to show you. That we basically now need to focus on quantum experiments where we maximize this value, and on gravity experiments where we maximize this value. And at the end of the day, we need to combine them and hopefully are significantly larger than h bar over g. Now, this is the most, let's say, simple requirement that sums up. Let me now give you a few more requirements from an experimental perspective. Okay? Namely, what I'm trying to do now is I try to add some experimental constraints and then modify this expression a little bit more. So here are the constraints. Constraint number 1 is vibration. So you see, with our expression here, you could say, oh, I just make an experiment that lasts very long. Right? So basically, if I have a macroscopic object and I have coherence over tens of seconds, then obviously I can make this expression very long. Well, the problem is the longer you make the coherence time, the more sensitive your experiment is to low frequency fluctuation. Now, the problem that comes with that, I plot here. So this is a graph that Rana Adhikari from the LIGO community likes to show. Namely, that shows how low frequency seismic noise scales with frequency. So the point is, when you have constant seismic noise, or constant acceleration noise, if you have wide acceleration noise over the whole frequency band, then your displacement noise scales with 1 over omega squared. And this is exactly what you can see here. The lower the frequencies, the larger are the amplitude fluctuations due to seismic noise. So this is why, and so we have done experiments at ultra low frequencies, and this is a mess. So the lesson that we have learned the hard way, I will show you later an example, is stay away from low frequencies. So here is working assumption 1. We need to avoid noise at low frequencies, because this noise is always much larger than noise at higher frequencies. This is why we choose, it sounds quite random, but it's actually quite reasonable if you look at the numbers. We now want our experiment to be done within 10 milliseconds. Okay? Which means that we only have to take care of vibrations that are larger than 100 Hz. Which already puts us, back here in this regime where the space noise is already small. And just to give you a perspective, when you do an atom experiment, so you can now you can trap it with a laser, with a magnetic trap, and you can prepare a pure state wave packet of that atom. So typically, the pure state wave packet extension we can prepare in the lab is in the order of 100 nanometers. And this is because this is the harmonic oscillator ground state. The mass is very small, the frequency is around a few megahertz, and then the ground state, the wave packet extension, the 0-point motion of an harmonic trap scales with h bar divided by mass and the trap frequency. If the mass is very low, this is where the large ground state uncertainty comes from. If this atom physics experiment is now oscillating, vibrating by a nanometer or so, it just doesn't matter because your pure state wave packet is 100 nanometers, so a 1 nanometer fluctuation in the experiment is simply irrelevant for your experiment. If now, instead of having one atom, you suddenly have 10 to the 9 atoms, or maybe even 10 to the 12 atoms in solid state object, you see that suddenly your ground state extension shrinks by many orders of magnitude. So instead of having 100 nanometers, we in our experiments, where we have at least 10 to the 9 atoms in a solid state object, suddenly have a wave packet extension of a picometer. If now my experiment fluctuates by a nanometer, all hell breaks loose. So that already shows you that experiments with macroscopic solids, so with solid state particles, have completely different experimental requirements when it comes to displacement. So this is why, number one, let's seriously avoid displacement noise and only work at high frequency. So 10 milliseconds, we don't want the experiment to last long. The second working assumption, we want gravitational coupling between two objects. So the point is, gravity is by large the weakest force, the weakest interaction between two particles. Electromagnetic forces kick in very brutally when you start bringing them together. So there is no way around some sort of electromagnetic shielding between the two masses. So every gravitational experiment that needs shielding in the form of a Faraday shield between the gravitating masses. So what the Faraday shield does is it creates mirror images of the charge distribution of each mass here in the Faraday shield, which leads to overall electromagnetic field on the other side of the shield that is not any longer dependent on the position of the charge on the other side. So you do get some DC electric field on the other side that has no position dependence anymore. So that means that there's no direct charge coupling, a position-dependent charge coupling between the two masses. So in that way, you cannot entangle it anymore. Now, the point is now, if you look at the literature today, the smallest distance that people have managed to do gravity experiments is 50 micrometers between the surfaces of the two masses. So the most famous experiments are the experiments by the group around Eric Edelberger in Washington, the Earthwash group. The last experiment that set the new world record of 50 micrometers, they used a 10 micrometer thick conducting shield between the two masses. What we are trying to do right now in Vienna, we are setting up a new experiment in collaboration with Eric Edelberger, and we're trying to go to 10 micrometers, okay, and possibly below, who knows, but 10 micrometers is our goal. And so this is why the second working assumption is that whatever you do, the d here, the distance between the surface of the two masses will never be smaller than 10 micrometers. This is a conservative working assumption. We will see. Maybe we manage to go to, who knows, 5 microns and still shield all electromagnetic forces. We don't know. We think we are on the safe side with 10 micrometer, and experiments will tell. But here, working assumption is we need a Faraday shield, and we will be able to use it to shield electromagnetic interaction such that only gravity remains as interacting force between the two masses down to a distance of around 10 microns. So, and now comes the third working assumption. We now have, let me just mention, this is just mentioned in passing. Now that we test gravity at the 10 micrometer level, we sort of got significant attention from the high energy community, because it turns out that there are several proposals out there shield all electromagnetic interactions between them. Okay. So the last working assumption is that one that now relates to the coherence. Now, you see, when you have what we need is we need some delocalized state on top of, in front of a Faraday shield. So what's going to happen? Any sort of charge distribution here will induce Milnor charges here. And if there's even just a faint level of dissipation in the Faraday shield, you will get coherence. Information about the position will be deposited, and that's it. So here, next working assumption is that any form of decoherence due to dissipating mirror charges will scale with some order of delocalization over distance. Okay, and obviously what we want is to have that ratio delocalization over distance much smaller than 1. So now we have everything together. So these are three working assumptions that come purely from an experimental perspective. And if you put all of that together, I just told you that we now have additional restrictions on delta x and d, on d, and on the coherence time. So that leaves the mass unaffected, but it gives you now a new bound on the mass. So if those three numbers are bounded, this will only work if the mass is actually larger than this expression number. So this is a new additional bound that we have. We demand that the mass in those experiments needs to be larger than around 10 to the minus 6 times the plasma. Okay. So then obviously we need to compute the coherence. I don't go into the detail here. I just want to tell you that obviously we have decoherence from gas collisions because we still have some background gas. Typical de Broglie wavelength of the background gas is on the order of a nanometer. So it means a single gas collision will already localize our state. We have decoherence from blackbody radiation. We have decoherence from thread fluctuations, and so on and so on. So these are all things we need to take into account, and that adds up then at the end of the day in the following list here. So don't worry, I made that. I just picked out one. So what you see here is actually a list of requirements. I guide you through it. Here's the mass. So let's say we have a mass that is 10 to the minus 3 times the Planck mass. So it means like 10 to the 15 atoms approximately. That would mean that we need a delocalization of delta x on the order of 100 nanometers. Okay? And a temperature on the order of 10 Kelvin of both the particle and the environment. When we manage these numbers, then on a time scale of 10 milliseconds with a typical solid state density and a separation of two masses of 10 micrometer, we will generate entanglement on a 10 millisecond scale. Because the particle is then already on the level of some 10 micrometer, we of course have to have we have severe constraints on the gas. So we need to have a background pressure on the order of 10 to the minus 14, 10 to the minus 15 millibar, which is something that one can achieve today with cryogenic vacuum vessels. So this is the theory. So now the question is, where are we with experiments? And I briefly would like to touch on the gravity side and then on the quantum side. On the gravity side, when we started out, we realized that the smallest source mass that was used in gravity experiments back then was on the order of a gram. And so a tabletop gravity experiment. And we thought, well, let's see how well we can do, and let's aim for an order of magnitude improvement to start off with, and then learn what the challenges for gravity experiments are. So we basically set out to do a small-scale Cavendish experiment. So here is a torsional pendulum as we use for Cavendish. There's a small gold mass here and here, 90 milligram, and there's a source mass on this side, also 90 milligram, that we simply just move back and forth by a few millimeters. So by doing so, you modulate the gravitational field at the location of the test mass. So you have a modulated gravitational acceleration, and this thing should start to ring up. We shield electromagnetic interactions by using a Faraday shield to get a gold-coated aluminum membrane here. And if you do now a sinusoidal modulation, then for a 90 milligram source mass and a few millimeter of movement, you expect acceleration modulations on the order of 10 to the minus 10 meters per second squared, so 10 to the minus 11 g. And this corresponds to displacement of a few nanometers of this torsion balance fold mass. Well, it sounds quite simple. The problem is, of course, measuring nanometer displacement on a torsional pendulum that operates at a frequency of a few millihertz turns out to be difficult in a Vienna city environment. So here's an example. This is a real-time plot of our data, so the position fluctuations of our pendulum. And when you see it, it's quite shaky all the time. And you see the variance of the signal becomes smaller here. And this is actually during the night. So there's a significant improvement during the night. And then you see those bumps here, right? So these bumps are night buses. So this is a night bus that stops like a few like 100 meters away from our lab. And I don't know if you can see that. So this is a late night bus, right? So in the Austrian press, they called us the most expensive traffic monitoring system in Vienna. But basically for us, the message was we need to work at night and we need to work when it's silent. And basically what we did then was we used Christmas time to do our experiment. And what you see here is we just look at the red-yellow line here. The yellow are the force residuals, the red is the actual signal. So you see very nicely now, again, oversighting Christmas nights, a gravitational signal here of the size we expect. The noise residuals are actually flat. And we even see a modulation at twice the frequency because we modulate an anharmonic potential. And therefore the response of the pendulum also has the higher order contributions in the response. And what you see is we resolve this acceleration modulation of 10 to the minus 11 g with a precision of 1%. So we actually have a sensitivity of 10 to the minus 13 g in this experiment, and the accuracy is 10%, which means that we know for sure that 90% of the interaction is actually gravitational. Now, this was a first start. Again, we wanted to have an order of magnitude improvement to understand what the problems are, and problems are, for example, as we learned, environmental noise. So, for example, the gravitational pull of a Vienna city tram that passes our lab in a 100-meter distance is the same magnitude of the gravitational pull of our source mass that is 2 millimeters away of our test mass. So that meant for us we really need to go away from the city, and in order to actually go to much smaller masses. So you see, this is our current mass, and what we want to do now is we want to measure the gravitational pull of a mass the size of the Planck mass. And it was clear we cannot do that in the city lab, so we now moved to an underground facility 70 kilometers southwest of Vienna. You see here Hans. Hans is setting up right now the experiment. You see he's wearing a cap because it's very cold in there, but so the temperature is constant at 7 degrees Celsius, both in the winter and the summer. So it's ultra-stable conditions. You see here, this is our source mass for the next run. Actually, the experiment is running right now as we speak. So this is a small silicon disk with the size of the Planck mass. And it sits on a larger disk. You see there are 5 of these small Planck masses. They're rotating and should modulate now our Cavendish torsion balance. So this is where we are on the gravity side. So basically we improved now to our 90 milligram mass, and soon we want to push down to the Planck mass regime. Now, what about the quantum side? On the quantum side, as I said, we want to increase mass, delocalization, and coherence time. With delocalization, I restrict myself now purely to the position space, because any effect momentum space will be scaled down by c squared. So we want to be delocalized in position for the center of mass. So where are we now experimentally? Here are my 2 highlight experiments that I want to point out. The one is the well-known by Markus, his superposition of macromolecules. Here you have 2,000 atoms being in a superposition of a few hundred nanometers. So you have now a mass of 2,000 atoms. Delocalization is huge, a few hundred nanometers, and coherence time is on the order of seconds because they're just really evolving. And if you now hypothetically cast that in a situation where you have two molecules gravitationally interacting at a distance of 10 microns, again, this is just completely hypothetical, and you scale it you scale it to h bar over g, then you would have to, this thing here would have to be 1 in order to generate gravitational entanglement, and you see we are 18 orders of magnitude away. So obviously molecules are not sufficient. Then there's another opportunity, namely go to solid state oscillators. So here's a famous experiment by Andrew Cleland's group where they had here a aluminum nitride slab that was sandwiched here between two aluminum sheets. They form a capacitor, and they were looking at thickness oscillations of this aluminum nitride slab. So you now have you have an harmonic oscillator, and you can quantum control it because this was capacitively coupled to a superconducting qubit. So they were able now to generate superposition states between two energy eigenstates of these thickness oscillations. They could demonstrate random interference, and so on. So they really show that there was a superposition of two different center of mass states of this macroscopic object that contains, so this is actually, you can see that with the bare eye, you see that it's tens of micrometers, and it contains 10 to the 13 atoms. So now we have a 10 orders of magnitude jump in the amount of atoms compared to the molecules. However, the superposition size, the delocalization, is tiny compared to the aim of the. So we have here superpositions on the order of 10 to the minus 16 meters. Right? So if you put now the numbers again and hypothetically have two of those coupled gravitationally, the coupling is even worse. Right? It's 10 to the minus 24. There's a recent work by Yivan Zhu at ETH, which is a significant upgrade of the Cleland experiment, and they improved it and are now at the range of the amount of molecules in the order of 10 to the minus 17. But still, there are 17 orders of magnitude actually missing. Now, what can you do? The way that we have been proposing some time ago is actually go to levitated systems. Because the problem with clamped solid-state oscillators is they are attached very strongly here to the environment, so coherence time will always be an issue, and the harmonic potentiality has obviously a drawback for experiments. And use the ideas of like three-fold atomic physics experiments. Now, how to do that? Well, just take a solid-state object, remove the constraints of this support, and levitate it in an external potential. The way this is being done, this uses tricks from quantum optics and from regular optics that have been out there since the 70s. Anikin pioneered the idea of trapping individual solid-state particles in the focus of a laser beam. The idea is very simple. You have an object with a dielectric object where you can use a dipole moment with an external field. The external field is the laser, so the potential landscape that the particle sees is actually dipole moment times electric field. The dipole moment is induced by the external electric field, such that the overall potential landscape is then just polarizability times E squared, where E squared is the intensity of the light that the particle sees. If the intensity is now a Gaussian beam, then the potential landscape that the particle sees is just the inverted Gaussian, and for small displacements, this is just an harmonic potential. So this is why a focused laser beam for a dielectric object just acts like a 3D harmonic confinement for the particle. This is how you can trap now particles, solid-state particles in 3D by using a focused laser. And so this is how it looks like. Normally you see here the micro-projective. The light comes out, is strongly focused here, and the particle is then trapped close to the focus. Now what you can do is you can play tricks again from atomic physics. You have the particle here. You have now two cavity mirrors such that light that is scattered off the particle actually experiences, due to the motion of the particle, inelastic scattering. So you now have red and blue Stokes and anti-Stokes scattered light contributions. The anti-Stokes scattered light contribution carries away energy of the motion of the particle. So if you detune now your cavity resonance on resonance to the anti-Stokes scattered light, this process is amplified, and the photons leak out through the cavity, and you have now cavity enhanced and so resonantly enhanced anti-Stokes scattering processes that allow you to cool the motion of this particle down to its quantum ground state. So this is something we did in collaboration with center of mass motion of such a massive object with 10 to the 9 atoms, the solid state object, to its quantum ground state. So again, think of it now as a pure state wave packet with a wave packet expansion of a few picometers. And the whole thing sitting in the lab in a room temperature environment. So I can show you here, this is a picture now. This is a picture of our particle sitting in room temperature while it is being cooled to the while it is being kept in its quantum ground state of motion. We have devised some other methods. We can actually now monitor in real time the quantum trajectory of the particle and also use that to stabilize the particle motion into its ground state. So we can basically also now do pure state preparation without having a cavity at work, which makes the experiment much more simple. And now you see the point is, now that we have the particle trap, we can just switch off the trap, for example. We switch off the trap, we have a free expansion of the wave packet, and we can generate large wave packet sizes. Or what you could also do is, you could actually you could switch on an inverted potential instead, and have the particle wave, have the wave packet actually exponentially start to increase in size on the back of this inverted potential. So these are things that we are doing right now in order to increase the wave packet size. And now then the big question is, how do we go from our 0-point motion to some large quantum superposition states? This is the topic of a synergy grant I have with these with my colleagues here, both from ETH and from Innsbruck. Oriol Merisat, Lucas Nawati, and Roma Kidor. We have been thinking about it quite a lot. There are many methods. I don't go into the detail here. Let me just point out, Ron Coleman has now increased his activities. He's moving from BEC to actually solid state particles with infinite spin. So maybe there will be a Stein-Geller experiment at some point in order to that will start to generate superpositions. We are following a different route. We are actually looking at a protocol where we modify the potential landscape that the particle sees. I don't go into the details here. I just would like to tell you the underlying idea. That is, if you have a dielectric particle and it interacts with a pulse of light with an intensity profile along your wave packet, along the wave of the particle, then the pulse imprints the intensity profile as a phase profile on your particle. So that means what you can engineer now is a phase grading on the particle wave packet just by applying a pulse with an x-dependent intensity profile. And once you have a phase grading, of course, a phase grading in position space is nothing else than a modulation in momentum space. And by doing so what we do is we apply an x to the 3. We apply an x to the 3 potential to the particle. This acts like a phase grading on the wave packet, and after time evolution, this will result in interference fringes in position. And this, in principle, if there would be no coherence, decoherence would, of course, allow you here to separate out two branches that are now in a superposition. On the other hand, actually, it will also allow you to test whether you have coherent delocalization by just the presence of these interference fringes. That's something we are building right now, and amazingly, we think that we can actually have interference fringes at 300 Kelvin at ultra-high vacuum only within a few milliseconds, sort of supporting our view that short-scale experiments will be possible in the quantum regime. Just to give you now the perspective, if we take that now, we have now a large delocalization, the mass is rather large, you see, and if we would have these two close like 10 micrometer gravitationally, we are only 10 orders of magnitude away. So you see that we're getting closer and closer. The question is, how do we bridge the last 10 orders of magnitude? And basically the secret lies in the m squared. Okay, if I manage to increase the mass now by 5 orders of magnitude, then I have my 10 orders of magnitude from my gravity experiment. How do I do that? I go from dielectric particles to superconducting particles. And here's an experiment that we have done recently. This is a Planck mass superconducting object that we levitate here at 20 millikelvin, so already ultra-cold temperatures, here between two coils. This is a configuration of anti-Helmholtz coils. We levitate at 200 hertz. We read out the motion by looking at the flux modulation through a we actually see quite promisingly extremely small dissipation. So we see phasing times in the order of tens of seconds. And obviously, if we now would be able to do exactly the same type of quantum control here in the superconducting regime, then we would be at the regime where our parameter scale would allow us to do a gravity experiment on the level of milliseconds. Okay, so let me sum up. What I showed you is that quantum control of levitated solids is a promising platform for achieving strong delocalization with large coherence times. That in combination with shielding of electromagnetic interaction could lead to an experiment that should be able to generate entanglement through gravitational interaction alone. So, because I get this question always, I address it right now. This is my last slide. The question is always, so how long will it take? My typical answer is, well, it has to be done in 15 years because of mandatory retirement in the European academic way of doing things. And I brought a timeline. So when we started looking into quantum control of mechanical systems around 2004, then it took us like 10 years to achieve quantum control of those objects, and we started going into levitation. It took us around 10 years to basically now have quantum control of levitated solids. We do have a first gravity experiment, and starting from now, the next 10 years, we have a clear roadmap. We want to delocalize first small masses, then cold small masses, and then cold large masses. And this is then combined with actually gravity experiments at the 10 micron scale, and then with Planck source masses. And so let's see if the 10-year time scale holds. So with that, I thank you very much, and I thank, of course, my team and all my collaborators for joining me in that quite funny endeavor.
So very little time for questions. If anyone has some quick question about for Markus. Then I'll go with a very quick one. Maybe you mentioned it briefly at some point, but what is the distance in orders of magnitude between the largest mass we can put in a superposition and with the same technique, the smallest mass we can we can detect its gravitational field of?
You mean currently?
Currently, yeah.
So currently, the smallest mass we can detect the gravitational field of is like 10 to the 4 times the Planck mass. And in the quantum regime where we need to go is 10 to the minus 3 times the Planck mass, so there's 7 orders of magnitude missing in the mass. And delocalization-wise, the largest delocalization at the moment is essentially ground state. And I mean, there has been some squeezing, but the squeezing is in the order of 3 or 5 dB. So basically, it's a negligible factor of 2. Okay. So there we are in the regime of picometers, so 10 to the minus 12, and we need to go to the regime of at least tens of nanometers. That's 100 nanometers, so 10 to the minus 7. So there's another 5 orders of magnitude missing. So we're missing 5 orders of magnitude in delocalization and 7 orders of magnitude in mass.
Thank you. So let's thank Markus one more time. So now to Markus Huber this time. Let you share your screen. Yes. Then I'll let you start.
Okay, so I'll start with the same apology as Markus. I would have loved to be there. It was a long time to say to join me. We'll miss out on all the beautiful discussions. I was usually very annoyed to sit in the lecture hall and listen to a sweet talk. I'll try to make it as short mainly used my talk to set up the first day talk of Max with a little bit of motivation and precursors to it. If you at any point have any questions, don't hesitate to ask. So, maybe before I come to the papers, the main question that has been following me for a while, I actually believe it started in Geneva when Nicolas Sangouard confronted me with a topic concerning projective measurements and energy along a spin chain. I don't know if you remember.
I remember.
Yeah, and so later on, I kept wondering about the thermodynamics. But let's see what, and it took me a while to fully understand the quantum origin of the laws of thermodynamics. Since this is maybe not the main focus of any system foundation, let me just reiterate a very rough version of what could be seen as thermodynamic laws, and then think about what this means in terms of measurement. So, there's often the first law of thermodynamics, which roughly translates in a change of energy essentially can always be decomposed in a component of work and a component of heat. And like in a closed system, it should be reasonably close to zero. Like, so energy is a conserved quantity, and there's long debates about what exactly separates work from heat at the quantum scale, and what context, what the various knowledge and agents and so forth is. It's something we've been working on, but at least we can take away that energy should be conserved. And in fact, for the dynamical equations of quantum mechanics, this is almost trivial, as the Hamiltonian, whose expectation value determines the average energy, is of course the generator of the dynamics. The second law, well, famously, let's just write it as the change in entropy of a closed system is positive semi-definite, or in other words, entropy can only increase spontaneously. And this, again, we will get back to a little bit later. I think this is one of the most profound questions in the relation of the quantum mechanics and the foundations, namely how unitary time evolution can actually be used to explain the second law of thermodynamics. And the third, and paradoxically, it's the one I always had the most trouble with, but it's also the one that I believe is the easiest to understand and prove. There are many versions that you can take. I'm going to use the simplest one. This kind of goes back to unattainability theorem. So if you want to, let's put it this way. If you want to go from any thermal state to the ground state, then you need some resource to be put into that needs to diverge. So you could say, for instance, a thermal machine cooling a finite temperature state to the ground state requires an infinite amount of energy or work to do so. But in fact, we know from considerations surrounding things like lambda or erasure and other things that you can also do so with a finite amount of energy, like kT-2, but at the expense of taking an infinite amount of time. Or there's further nuances to this, but this is maybe not the topic of today's talk. So now let's think about what happens when it comes to measurement. Well, let's first do something pictorial. This will say I have a quantum system, and then I have a measurement apparatus. The quantum part of it, like the thing that predominantly interacts with it, and then the remainder of the measurement apparatus. And I will dub the correlating interaction between system and, let me call it probe maybe, as pre-measurement, and then we'll of what these projectors are, or how the measurement works. Well, say I measure an energy eigenbasis, so I have some energy eigenstates of the system, and I measure the quantum system in this eigenbasis, then I will essentially get the following post-measurement state, rho I, being equal to, well, EI divided by trace rho EI. Of course, we can generalize the whole thing to arbitrary POVMs, but it doesn't change anything for the argument. So, because if you think about it, let's say I have a quantum system prepared in some superposition of some energy eigenstate plus another energy eigenstate. Then post-measurement, there are two probabilities, right? I mean, there's a probability of A squared that I end up in with the state E0, or probability B squared that I end up with E1, which is all well, but if you think about it, the state pre-measurement and the state post-measurement definitely have different energies. So what's actually happening to the first law? It seems, well, the textbook description doesn't really violate it, it just doesn't make a big statement about it, because in some sense we now have a choice to either say, well, the quantum measurement energy is not conserved, or whatever this fuzzy thing is happening here, somehow the finite amount of energy difference must be compensated. So in some sense, the measurement apparatus needs to supply the amount of energy that is needed to save the first law from being violated. Well, okay, so there's a bit of a choice here, but the foundations of quantum mechanics isn't actually clear on what happens to energy in the measurement process. Continuing on, if I say I have a state which is some p times E0 plus 1 minus p times E1, and we could now interpret this as the marginal of an entangled state for which there is no true decomposition, so we have somehow a mixture we cannot really get rid of. And if we measure, again, the probability P, we get E0, and with probability 1 minus P, we get E1. And here, I start from a finite entropy state, and I end with a zero entropy state, IOJ state. Well, fair enough. It's a rather large system, and the second law only talks about closed systems. So if we believe the second law to be true, the measurement apparatus must increase its entropy to compensate for this. And now, again, this is a bit ad hoc because we don't exactly know the law to be true, but I think it's a very bad bet. It's a bet against the second law of thermodynamics, as many famous physicist quotes have done or said so before. Okay, so somehow this magic interaction or whatever is happening must compensate for the energy change and the entropy change. But what else? Well, here, if this is now a qubit and P and 1 minus P are the probabilities of the typical thermal state, and I end up with 100% probability in a chip state, I could then, for instance, apply a protocol that rotates this to the ground state, where a simple unitary takes a finite amount of energy, meaning via measurement I can deterministically move to the ground state. And now I'm in trouble again, because it means that technically whatever this process is, or the measurement needs to compensate for an infinite amount of work if it is to happen in a finite amount of time. And troublesome, especially since the third law of thermodynamics is actually quite easy to derive from unitary quantum mechanics. So there seems to be a tension. And in fact, we don't even have to yet go to the constantly classical transitions. We already see much of the tension in the pre-measurement space. And how is that? Well, I mean, instead of just using projection postulates, we can basically use a von Neumann type, or you often see this in many worlds type ideas, right? When you can write down a system which is some psi in some superposition, and a detector that is kind of event ready. So the detector in this usual story would be, say, the mature state, and then I have some unitary interaction between the detector and the system that leaves me with A times E0, 0 with B times E1, 1. In some sense now, I have entangled the two, and the detector is a perfect reflection of the system state, and I can then do this with this whole formalism of the Darwinism. I can now have another detector, and this detector, and another, and another, and another. But what is important here is that essentially I create correlations in such a way that the detector system is perfectly correlated with the system I aim to measure in one basis, which, fair enough, I can do, but what I can assume here, or what I can usually assume here, is that the detector already is in a perfectly pure state, i.e. something akin to a ground state of absolute zero. But what happens if the detector instead could be rather cold, but it could be a thermal state, i.e. something that would say e to the minus p to h over z, where z is the partition function. And the main property here is that whatever thermal state I have, in fact, whatever state in any experiment anywhere in the universe I always have some mixed states. I cannot get away from it, and they're all full rank. So what if I want to try the very same story? So I have a system coming in, I have a probe also coming in a thermal state, and now I try to make them interact such that the state rho system probe tilde is correlated in a way that this reflects the properties of the perfect measurement. So there are three properties that a measurement has that I would like to preserve. So unbiased is the first one that we call. So now let's start with the first call is faithful. Spells a nice acronym. So first of all, I would want the trace of II tensor some projector, some rank D POVM of rho system pointer tilde sum over I to be 1. Where pi I are now projections onto different subspaces of my pointer system, which should correspond to reading of the value I. And then this faithful just means that if the detector tells me I, the system is in state I. So this is kind of a codification of Lüder's rule or projection postulate. And in particular, we also want more, because you could have this property, and yet that only means the post-measurement state and the state of your detector correspond really well, but it doesn't really mean that the state before you measure it corresponds to what you read off the detector. So here this I want to be unbiased. So I want trace rho s I to be equal to the trace assumption we saw here is that I come in with a finite temperature thermal state. Of course, what I could do is I could pull this system down to a pure state and then recover perfect measurements or idealized measurements. But unless the third law of thermodynamics tells us we need an infinite amount of resources to do so. So in the end, thermodynamics quite simply and almost quite clearly limits our ability to accurately correlate the system with the quantity. Of course, this has implications also for the first law and for the notion of work, because, well, essentially, it's kind of odd in the sense that work, if interpreted as observable as a random variable, essentially is limited by the amount of work we put in measurement. So microscopic or quantum work, part of the problem with it is that we need a lot of work to measure it, which seems almost tautological or paradoxical, and only once the preparation costs or the measurement costs are very small compared to the actual scale of the energy changes, we can recover as a limit classical mechanical notions of work. But okay. So far, this is really about the notion of free measurement. But now the second step, we thought, well, of course, it's nice that a single probe is well correlated, but in order to do this whole quantum Darwinism dance of going to the so-called state broadcast structure, some of you might have heard, or reach a notion of objectivity, what I actually need is, I would need to model this big classical detector as a form of any-body system, and in some way, and if you follow the literature on quantum Darwinism, I would need to essentially correlate in whatever way my quantum system state with the state of a very large fraction of the environment, such that any fraction of the environment, even a smaller one, so if I look at a little window of my environment, I essentially can read off the state of the system. And no matter which fraction I take, they intersubjectively, or in that sense, objectively agree on the state of the system. This is this notion of objectivity that I can, in some sense, demand that there is the so-called spectrum broadcast structure, which is essentially, if I come in with my system initially to be sum over I, I would like my system state plus the environment state to be somehow in a conditional state where I here have a big tensor product, so one to big N, rho Ki, so such that essentially all these N fractions of my environment, which in themselves become many-body systems, accurately reflect my system state in the sense that they're all perfectly symmetrical. Okay, but that is now an even stronger requirement than we had before, because in what I had before, the so-called bound conditions, all I needed was a single pointer system to be correlated. But now I basically want to add another point to the bound condition, namely I want to add broadcasting, or in other words, I want to have these three properties with all the end parts of system, but unfortunately, it changes the system. So in that sense, it's invasive. So once I correlate the second system, well, this one can no longer be unbiased. So it's neither faithful nor unbiased, nor, well, not invasive. So in that sense, it's actually quite non-trivial to extend this to more and more pointer systems, because we will lose all the fun. There is no more preservation of any of the free conditions that is possible. And of course, there's another choice. We could choose all of them to be non-invasive, and then we can have an overall biased measurement, and the bias is somewhat unavoidable. But you may ask, well, but is it really so bad? Because, I mean, if you take any reasonable temperature and put in some energy estimates, this will seem to tell you that it's actually excruciatingly expensive and almost impossible to do a quantum measurement, and for any macroscopic system to reflect your system state. Well, that is true if the dimension of these pointer systems is all comparable to the dimension of your system. So in other words, if you want subsequent unitary interactions to sequentially or globally correlate your system state with every constituent of the environment, no matter how small, this is going to be an impossible task. It's going to be impossibly expensive, and even so, it's going to be horribly biased, so it will not lead to an objective agreement of facts.
Recording in progress.
But this may also be maybe too much to ask. I mean, in some sense, objective facts, if we think about them, they may not be reflected in every tiniest fraction of the environment, right? If I measure photon polarization, usually by a polarizing beam splitter, I go left to right, so I measure the position, I measure flicker and no flick. I will probably not be able to read off whether it flicked or not, i.e. Two-level dichotomic value. I will not be able to read it off in every spin of every electron of every atom in the room. That's just too much to ask. What I really want is, I want roughly the macro states of regions of the room to be able to tell me whether the detector flicked or not. And now, since I'm coming to my end, and I promise to be short, I really wanted to tell the message that there is a little bit of a tension between an axiomatic approach to projective quantum measurements and the fundamentals of thermodynamics. And those are things you should not met again. And here, the next step would be, well, I mean, there's still a very much agent-based picture, right? I mean, this is incredibly complex. Usually, a measurement is not done via a controlled interaction between a system and individual constituents of my environment. I mean, I may write it down as such, I will be able to reproduce the measurement postulates as a kind of emergent property in large enough system dimensions, but it doesn't actually go along well with any reasonable physical picture we have of how a measurement actually works. Because in the end, no experiment that goes and slowly and in a controlled fashion correlates the polarization of a single photon to every little constituent in the room by subsequent very well controlled and very well timed Hamiltonian interaction between that system and everything else. In fact, it should be a spontaneous and irreversible process. So what we would really want is a system and a gigantic environment that consists of many different constituents of different species or whatever, to be a closed system, to have the natural unitary evolution to be really just the what Sheldon talked on Thursday. I think this is what Max will be talking about.
Okay, thank you. So, any questions? It's been a long day. So the question I had in mind, they just said that Max will answer it on Thursday. So what else? Nicolas, maybe you have a question?
So what does it tell us about the spin chain and the energy conservation or non-local?
Well, it depends what stance we take. Indeed, we're not there yet. But indeed, at least we now have a model that we could use to check, in a sense, the assumption that the energy would have to be compensated by the measurement of the outside. Or it's actually okay to have in a relative state version of this, the energy actually change without the measurement apparatus having to compensate. But I don't think we're there yet. But I think this is the goal, and I think Max will happily discuss this entire idea of the program much more. But our idea would be, once we have a self-contained dynamical model of measurement that is thermodynamically consistent, we can then start revisiting paradoxes of measurement, such as your beautiful spin chain example, and see what it tells us.
Thank you.
So, any other questions? We can thank Markus again. So this concludes the Tuesday session, and we have free time for the next 50 minutes.
I have slides at the
But I was not the, because they were the online. Okay, yes. And the last two is actually around.
The real person of
Okay,
This is I think it's snowing down this morning. The speaker has to concentrate on the
Okay, yeah. Okay, who's
Sandu.
Okay, then I will tell Sandu that it's very important.
You guys explaining to this new professor how to become a chair, because for Sandu we need a special one. Okay, so welcome back for this special day. Special because we have only 2 lectures in the morning and 2 in the afternoon. Because you know with 96 and indeed it's very windy there, so please don't go. What you see from the window, so we also cancelled, we didn't cancel, but we had no coffee break because we are supposed to go to the excursion. And I think it's a good idea because I really encourage everyone after the second talk, so after Nicolas' talk, just to walk out of the hotel and walk along the river. And you walk until you feel completely wet. At that point, you turn around, come back and take a shower. But you can walk really for hours if you really enjoy it. But of course, you can turn around whenever you want. It's a beautiful walk, and you have all the forest and the snow, and if you are even lucky, some snow will fall on you, so you get a bit of the experience that you are supposed to have. Okay, and now I turn to the chairman, who has just been instructed how to behave on the young kids. And yes, please, Renato.
So then it's a big pleasure to introduce Sandu, and I think I should just give him all the time he has, because we need to be strict today.
Thank you very much. Yes. So Nicolas informed the chairman, reinforced me, so that I would start right away. My talk today would be about conservation laws in quantum mechanics. And let me start in a more unusual way. Let me start with a little piece of mathematics. Okay, so here's the following thing. I would like you to consider so I would like to consider this function. F of x equals 1 plus alpha over 2 e to the I x over n plus 1 minus alpha over 2 e minus I x over n all to the power n. Okay. So what can I say about this function? First of all, please note that this is of the form of a binomial. A plus b to the power n, this being a, that being b. So that is sum over k from 0 to n choose k, a to the k, b to the n minus k. So let me try and apply that thing here. So this would be sum over k from 0 to n, some coefficients, n choose k. I have 1 plus alpha over 2 to the power k. I would have that term, let me put here, e to the I kx over n. And from here I have 1 minus alpha over 2 n minus k e minus I n minus k x over. So far so good. And I would like to put these things together. You see you have kx, and then with minus 2 minuses is a plus. So I can reabsorb this thing here. So it is n minus 2k over nx. All right. K goes from 0 to n. So if I look here, these are like some frequencies in a Fourier transform of that function. And they go, when k is 0, then what I have here is from -1, and when k is n, it will be from +1. So all these frequencies there are between 1 and -1. Okay, so far so good. Now, let me, however, look at this thing for small x. Let me put here for small x. How small x would be, it will become clear pretty soon. So if I go and look at that formula over there, for small x, I can approximate the terms in first order of approximation. That is the simplest thing. So f of x would be 1 plus alpha over 2, and the exponential is 1 plus I x over n. The first term, plus 1 minus alpha over 2, 1 minus I x over n, all to the power n. Equal 1 over 2 times 1 plus 1 over 2 times 1, I have a 1. 1 over 2 times I x over n, 1 over 2 minus I x over n, these two terms disappear. Alpha over 2 times 1 minus alpha over 2 times 1, they are the same up to a minus sign, they disappear. The only one that survives is plus I alpha x over n, everything to the power n. Which you see that is in the first order of approximation e to the I alpha x. Okay? And this is valid as long as x over n is small. So if I take x, the largest value of x, some fixed number, and I increase n, this approximation becomes the better and better. In fact, if you really want to stretch mathematics a bit more, you will see that this is valid as long as x over n is smaller than square root of n. In fact, n to the power half minus epsilon. So what does this mean? Well, let me put here. F of x for small x is e to the I alpha x. Well, I never told you what alpha is. Alpha is just a number. But suppose alpha is larger than 1. In fact, I can make alpha much, much larger than 1. Okay? Everything works. The only thing for this approximation to hold any alpha fixed, any x largest number, and increase n. Everything works. So what do we have here? We have that I superpose them states with very low frequencies, important in no frequency larger than 1. And suddenly, for small x, I have very, very large frequencies. So, if I look in wavelengths, suppose I have something with a long wavelength, something else, say kilometer long wavelength if you think of radio waves, and perhaps the smallest wavelength is this. And you know that, well, that's what you were told, that the smallest resolution you can have is of the order of the smallest wavelength. And that is rubbish. That is not actually what happens. I don't know. They brainwash generation of students with this criteria, which holds in most of the cases, but not always. Here I can pick alpha such that in some region here, I oscillate extraordinarily fast on a scale that is much, much smaller than the smallest wavelength. Of course, if I continue to look at this, it may increase and it in fact will become a function much, much bigger outside. But here, if I'm looking at this region, that I can make as long as I want by increasing n, and to contain as many oscillations here as I want. Okay. Does it break the Fourier transform theorem that says that, you cannot get one frequency by composing the others? No, it doesn't. This is an explicit way. I have all the frequencies between 1 and minus 1, and I get one faster, but not over the entire range. Okay? This range, as I told you, might be finite or might actually be up to square root of n, where, say, the longest wavelength here is of the order n. And this square root of n is there. So from this point of view, it doesn't break the Fourier transform theorem. Okay. So long is just an interesting piece of mathematics. So, yes, please.
Small clarification. So, since you're interested in large alpha,
The range of x does not depend on alpha in your approximation. If alpha becomes
it doesn't really matter. You want the range of alpha x to be smaller than s. To be, you could take it constant, or you could take it up, strictly speaking, alpha x to be the range n half minus epsilon. Okay. Right. So let's do some physics now, and that is the important thing here. If I look at this function, f of x, that is a, a sum of all these oscillations with these interesting coefficients here. By the way, these coefficients are quite interesting. They explode because of the exponent of the n choose k there. And here, if I take alpha larger than 1, this is a negative term. So it changes sign as I modify k. For even and odd, some of them come positive, some of them come negative. So you start seeing a little bit why all these very mad things appear. Now, let me get to physics. So let me imagine I have here a box of length roughly n, or better say it is between, say, pi n minus pi n to pi n. So it's 2 pi and the length of the box. And let me suppose I put a quantum particle in a wave function psi of x, that is f of x minus fx complex conjugate, because if I take that and I look at the decomposition, that would be 0 at the two ends. That is the only thing I do. But the same way as f of x was with bounded frequencies, also the complex conjugate is. So I put a particle here. Suppose it's a photon or any particle. So the wave function here will be extraordinarily highly oscillating, and then here the wave function might be much, much bigger. All right. Now, this means that this particular particle is not in an energy eigenstate. Yes, because it is a superposition, as we had here, as we had there, of plane waves. Each of them has a different energy. So I take this as the initial wave function in the box. It will evolve, but I'm interested at what happens now when I prepared it. And what I want to do, I want to open a little window in this box. And I want to extract the particle. So imagine that I put it a tiny mirror in. Perhaps this will remind you of the mirror that your dentist inserts into you. Not the best way of starting it. So put a mirror, keep it there for some time, take it out. Now, I want to do that for a time. If this length here, where the super oscillations occur, I will call them super oscillation, is some length L. And we know that that L has to be smaller equal to square root of n. I want such that Ct should be smaller than L. So I would like to sample only. So what will happen in that situation? Speed of light. Speed of light. Thank you.
You're a scientist.
Yeah.
coming from a computer scientist, that is impressive. Right.
I thought it was one.
Yes, for you it's one. So two things may happen when I do this. If the photon was anywhere near in this region, will come out. And as always, when it bounces light from a mirror, it comes with the same frequency as it entered. So it will come out like this. It is possible that it was not around that region, that it was somewhere far away, and in that case, nothing will come out from your box. Okay? Then I close, I take out the mirror, I close the thing. So suppose in this particular instance, the photon came out. What is the energy of the photon? Well, the energy of the photon is given by the frequency that it is there. That is not an eigenstate because I cut a finite wave train. It's not an entire wave. But basically, it would be like a Gaussian modulated by maybe a sinc function around this high frequency. Yes, sir.
So how do you know that that's what will come out? Because you haven't solved the time-dependent equation. Well, you're just appealing to our intuition that this is what will...
Intuition is good. If you want, you can read a paper where it's solved.
Okay.
Trust me that is what.
Okay, trust you, fine.
There are many other models you can do. Instead of putting that thing, you may imagine that you put two walls here and you just cut that thing. So, what happens in this situation as far as energy is concerned? What happens is the following. So I started with energy, that all the energies are lower than some value, 1. This is the initial, so this is the probability of energy, which is the energy. And now, so some sort of spectrums of energy there. And now, in some cases, I get an energy much, much larger, of the order alpha squared. Or alpha if it is a photon. Yes?
Is it clear that you start with an energy which is below 1? It will be like fine with...
Because the frequencies are small.
For an infinite box, yes, but now there is some...
Well, if it is... No, because if you put it in a box, you have the sign functions. And it goes exactly these things. Right. It is an exact solution. Okay. Because there it's not a free particle, it's a particle with in a potential. And when you solve the equation, you find that these are the exact solutions. Right. So suddenly you have, in that event, you have a particle coming out with much, much, much larger energy than you have. So now to come to Howard's question, now I need to solve something that is not the initial particle in the box, but is a time-dependent Hamiltonian, because I open, I put something in, I take it out. So you may imagine that it comes out from the fact that it is a time-dependent Hamiltonian, and that does not conserve energy. Good. That's fact. So in order to avoid that, I would transform this problem into a time-independent problem by adding the mechanism that takes the particle out. So that would be, in the simplest way to do it. Let's see, there are plenty of colors here. The bad thing is that I'm colorblind. So suppose I have here something I will call an extractor, another particle that moves along and interacts with this when it comes towards the box. You can model that, you can do toy models for that thing. And now it is an independent situation. And I have to look what happens in this particular situation. So in this particular situation, the spectrum of energy, this was the spectrum of energy of the particle inside. Let me call this was a photon. I put a gamma. It might have been here infrared, it comes out like a gamma ray. I can arrange the frequencies. But on top of that, I also have to look at the probability of the energies of the extractor. So this is the energy of the extractor, that was the energy of the photon. What can I say about that? Well, it was important for me that I open and close this thing such that I only sample a piece around. So I only open and close during a finite time t. In order for this opener to come into the interaction region, it has to have a large spectrum of energy because the state needs to evolve considerably in time. And you will find out that it has a very, very large spectrum of energy. It has, in fact, energies larger than alpha squared. So it has a lot of energy inside this extractor. So then you ask, how could it be that the particle, the photon, emerged out with an energy much bigger than the maximum it had? Well, obviously, it borrowed from the extractor. Now, the extractor didn't have a well-defined energy, but what I expect is the following thing. Let me come here. I expect the following thing to happen. So if the energy of the extractor was like this, I have now two categories of events. The events in which the photon came out, and in that case, what I imagine is that the energy went down by how much? Exactly by this alpha squared minus 1, roughly. I don't know exactly whether it was at 1 or at one of these small things, but at least something of that order, has to be lost. In other cases, this is when the photon went out. And there will be other cases when the photon remains in. I open the box, I close it, nothing came out. We'll discuss how that looks. But it would be a very simple and trivial energy conservation. The particle came out, it gained a lot of energy, the extractor gained.
Sandu?
Yes.
So this extractor electron intuitively has only to have an energy such that the resolution is as much as this width that you open, this L thing. But this L, as I understand, is still much larger than the wavelengths within the region.
Indeed. So if you would do only that, you may only perhaps do it up to here. In order to make sure, I will come back to that. I will come back exactly to that. It's a very important. But let me now claim, if this would be the case, that the extractor gave it energy, it would be a waste of my time to be here. All right? So let's try to understand. Let me look back at this problem and let me consider a second problem here. Let me suppose that actually I have a box here. And the photon, I prepare it in an eigenstate of this extremely high energy. And I do exactly the same things. I extract it. So the photon will come out in that way. Here locally, this looks identical to that. I put a mirror in, I have something with this energy, it will come out with this energy. So in this case, it's clear that the photon didn't gain any energy by coming out. There will be slight changes because here I had an eigenstate, here I have a finite train, but that would mean that instead of being sharp, is a Gaussian around that. But it might lose a little bit for deviation from the central energy that is alpha squared. Right. But in this case, the extractor didn't give it any energy whatsoever. If there the extractor would give the energy, it means that just by making a short time thing and sampling only this region, I know how the state looks far apart. And I will violate special. So since here nothing is given by the extractor, there nothing is given by the extractor. Yes, please.
And you were, I think, implicitly suggesting the Schrödinger equation is being used. Can you do this also for the Dirac equation, when it would in fact be relativistic?
I can do in many different models, whichever. If I do with Dirac equations, it's a bit more complicated. But what is important that even with Schrödinger equation, this thing works, because although signals may propagate with superluminal velocity, that the amount of the signal propagation is nevertheless bounded. And one can, you have Lieb-Robinson bounds, all kinds of things. But you can map this problem into a problem where it's not directed by time evolution, but do the same thing, for example, on a circle and look at angular momentum states. I don't care about time evolution because I can take, for example, the moment of inertia to be infinite. I will not look at the energy, but at angular momentum. So one can do all kinds of models. That is, in fact, the strength of the result. It doesn't rely on some tiny details specific. So, because here, I understand from relativity, I cannot. If here it doesn't give, there it will not give. So, in fact, this thing here does not happen. What happens is that it remains in the same wave function, the same spectrum of energy as initially. When the photon remains in, they didn't collide, it still remains the same thing for the opener. So the opener, the extractor, doesn't give the energy. The photon comes out with much higher energy than that. Thank you. I have to, right. Let's put that for the talks, because they will cut me short. So, what is going on? So one thing you say, and here I come to the standard way of discussing about conservation. The standard way in which conservation laws are described in quantum mechanics is statistical. You see, classically, you start a system, you measure the quantity of inputs, say energy, you let things evolve, and you measure the quantity at the end, and you see that you get the same number. Quantum mechanically, you can do that. You can measure the energy at the beginning, you measure at the end, and you see it's conserved. But suppose I want a situation in which I do not start with an eigenstate of energy. I start with a superposition. So if I want to measure it at the beginning, I destroy the experiment. The particle may enter places where it wouldn't enter in my experiment. So how do we do conservation laws in quantum mechanics? Basically, we do it in a convoluted way. We start with many, many copies of our system, and we measure the quantity of interest at the beginning. We will not get a given value, like here. We'll have different energies. Okay, so I sample the entire energy distribution at the beginning. Then I take, again, a large number of copies. I prepare in the same initial state. I don't measure the energy at the beginning. I just let them go, and I measure it at the end. And I see that the distribution of this conserved quantity is the same as at the end as it was at the beginning. And that is the conservation. And that follows directly from Schrödinger equation, and that is true all the time. How did I have a non-conservation here? Is because I didn't look at the entire ensemble. I look at what happened when the photon comes out. But there are cases when the photon remains in. And if you put all of them together, you'll find out that this statistics distribution didn't change. However, you may stop there and say, well, that is the conservation law in quantum mechanics. Not only that, that is the only consequence of conservation laws. I want to find what happened in these individual cases when the photon came out. You see, even the statistic one is not very pleasing. Because what do I mean? In some cases, I gain energy. In some cases, I lose energy. So do you mean that the photons that came out here borrowed the energy from another photon, from another experiment that perhaps has not yet been done? So thinking of the statistical thing is not satisfactory. So now you want to think, what happened here? And if you imagine that you put there a photon with an energy, I don't know, like an infrared, and comes out like an atomic bomb, you really have a case to discuss. So this was part one of our study. There are many, many interesting things. The way in which the statistical thing works here is actually very intricate and beautiful. I don't have time to do that. But although the statistical one works, it is very unpleasant that at the individual level it doesn't. So you may stop there and say, look, individual levels, individual events, that's quantum mechanics. It's surprising, bad luck. Well, we were not satisfied with that, and we tried to see what is going on. So after some time, I think about 30-something years, maybe 30 years, we found a resolution, which is interesting. And it says the following. Everything was correct here. But the point was that this function psi of x doesn't exist in nature. Doesn't exist in nature. Well, yeah, it doesn't. Why not? Look, imagine how I built this thing here. So you may have a laser out. You know, that was a cavity, and you injected a photon into this cavity. But when you did that, you borrowed some energy from the laser. Okay? So now I have to take the preparer into account. Okay? So I have to start, say, with a vacuum in the box with a laser, and then the laser delivers it with different amplitudes of different frequencies. So it will get entangled with the laser. That seems to be bad, because then I'm very far from this thing. But the laser, if it has a very large spectrum of energies, I can, although in every single case the laser delivers a bit of energy, the energy distribution of the laser will remain almost the same. So if I have the laser with some distribution, E of the laser, and sometimes it gives this energy, sometimes that, sometimes that, sometimes that. It will go down in energy just a little bit, and down in energy just a little bit. But if this is very large, all these states are almost identical. So although I will have an entanglement between this state and the one shifted a little bit, that state and the one shifted a little bit more, that is almost a pure state. Almost nothing happens there. So I can approximate this function as well as I want by making the laser's initial distribution of energy as large as I want. This, in fact, you are used with, like in a two-slit experiment, and an electron goes like this or like that, but whenever it collides with the slits, it gives momentum to the slits. How it comes that I still have interference? Because the distribution of momentum of the slits is very large, so it doesn't matter. And how much did it give? So you see, if I go and measure, not by allowing it to come out, I just measure the energies inside, whenever I have this thing, I will see that the laser gave exactly that value. So whatever the laser gives is always between 1 and 0. The frequencies are 1 and minus 1, energies are between 1 and 0. So that is very well understood. The question is, and I will finish, what happens if I don't measure the energy directly, but I first extract them? If you do that, and you look what happened with a laser, you'll find those are fewer cases. And you will find how much? Well, alpha square. 1 minus alpha square. You'll find alpha square minus. So you find that in those cases, the laser actually gave a lot of energy. So we have at the individual level 2 non-conservation events. The measuring device didn't give anything. So it's non-conservation. The laser gave a lot, but I don't see it in the state of the photon. The state of the photon never has energies larger, only when it came out. So it is a global thing, and on this global thing, the energy is conserved. And if I want to conserve my life, I will finish here, otherwise Renato. Okay.
Okay, thanks a lot for finishing on time. Yes. Then we even have time for questions. And yeah, let me start with Howard.
Got my hand up first. I'm suspicious about the fact that the curve for the extractor doesn't seem to be going to 0 at some finite upper. You've drawn it smooth and perhaps tending to infinity exponentially or something like that. Can you really say that the energy therefore does not come from the extractor?
Yes. So after all the solutions, it took some time to do all the calculations precisely exact in that sense. Yes.
With the bounded energy of the extractor? Okay.
No, well, the extent. At a certain, you need, there is an entire issue here that has to do with analyticity. It's an interplay. You just want this thing to be large enough. If it at a certain moment goes you know, for much, much, much higher energies that are way out of this region. There you put a cut, it doesn't matter. What is important is the spectrum of the extractor within at least this region to be smooth. You can, the main thing is not the energies. The main thing is you want to limit the time of interaction. That is the key element. You want to limit the time of interaction such that information doesn't come in from the outer region. When the time of interaction is limited, then what the spectrum of energy is, that comes out in a wash.
Sorry, but if the time of interaction is limited, isn't there an energy time uncertainty relation
Then
that says you need
the
a...
energy of the extractor should have K's going up to infinity. Right. However, you may want to say, I don't want it really limited, but I want not to allow too much from the outside thing. And if I'm allowing myself a little bit of perturbation to come, I can cut those things.
Okay.
And I have that under control.
You can trust Sandu's calculations.
This may be a slightly nasty question, but so I understood, I think, that the resolution at the end was due to an entanglement between the laser and that photon in the box.
Yes, well, to put it like that, yes, but the photon in the box, although there was that entanglement, never had any term in that entanglement having high energies.
I understood that. Now my question is the entanglement in the resolution the only connection between your talk and Bell's theorem?
Well, I wouldn't say it is any, but it is one. Because what happens here, if you were to look at the beginning of the experiment and check what energy is given by the laser, you would find this entire spectrum. You wouldn't know which one corresponds with which. The measuring device that comes here just gives an umbrella that covers, if you want statistical-wise, what happens. You will only see that there is something funny going on when you finish the experiment and you measure the energies out. So exactly the same way as in Bell's case, when you look locally and everything is random, is that randomness that gives you an umbrella to have, if you want action at a distance, or if you want things happening at the end, but you need an umbrella that will cover you for some time, and you will not see. The same way here is some sort of Bell connection between these two times, but of a different kind, because it consists in passing conserved quantities, not just numbers or information or something like that.
Okay, I think due to time, we have only time for the last short question and the short answer. Caslav.
So if I interpret this as some kind of a limitation of assigning the pure states existence, would you agree with this?
Well, there is always a limitation in assigning pure states. When there is no limitation, I can make them as pure as I want, yes, but not fully pure.
So, but the question is...
Which is a question of frames of reference at the end of the day. All of these things that refer to the laser can be asked, but how do I know that I have a laser? Perhaps somebody would have given me this state already at the beginning. Yeah. Well, no, because if this text doesn't have a meaning by itself.
So what I wanted to ask is, can you put this argument in regression? Because for the argument to resolve, you said, oh, the laser and the system were in the pure state. I said, oh, maybe you made a mistake again.
Okay, that paper will appear on the Quant PH in the next 3
Yes. Okay, let's thank Sandu again. technical support from the.
Finally.
Well, this one is, but the one for
Exactly.
It took a while.
Or do you know how to do it? You know how it works. I don't like everything you think you know on the project or somehow. It usually takes a bit longer, but it's okay.
Suggested that you should have more
like you wanted to know what's going. Turn this on the time, and you can just. Okay, so it's a pleasure to introduce the next speaker of the section, Nicolas Sangouard, speaker and co-author, I should say, and I'm looking forward to the talk about how this conference connects to experiments and applications.
Thank you very much, Renato. Yes, thank you very much for having me here. So we are celebrating 16 years of Bell's theorem, and in this talk I would like to discuss the impact that John Bell has had on quantum communication, and in particular in setting properly security proof for device for quantum key distribution. This is something that we call device-independent quantum key distribution. And well, in this talk, I would like to introduce the concept and mostly talk about the motivation, the way we construct a security proof in this way with the key ingredient of the Bell inequality. But I will also show you an experimental demonstration of device-independent quantum key distribution. And this experimental demonstration has been performed in the group located in Oxford, the group of David Lucas and Chris Balance. And the theoretical groundwork that was needed to make this experiment possible was made actually in collaboration with the group of Renato in Zurich, the group of Rüdiger Urbanke in Lausanne, the Geneva group as well with Pavel Sekatsky, and our group in Paris. And let me emphasize, by the way, that Jean-Daniel Bancal, who's actually not here this week, contributed very significantly to this work. So here's the outlook of my talk. I will spend some time talking about the motivation for going to setting where data transmission are secure with quantum principles. And then I will quickly tell you how we build up a protocol associated with this quantum key distribution, the way we quantify the security and we guarantee the security of this protocol. And we'll conclude with a few words about this experimental demonstration I was talking about before. And eventually, if I have time, I will talk a bit more about ongoing efforts to try to transition towards kind of more practical prototypes than the one that we people developed in Oxford. So let's start with the motivations, and the motivation starts with the issue of trying to secure data transfer, and to do that, you can eventually use classical algorithm. And the security of this classical algorithm rely on computational problems that are supposed to be hard to solve. So the famous computational problem is the factorization problem, which is used in an algorithm called RSA. And it turns out that exactly 60 years ago, Peter Shor came in with a quantum solution for this problem. Sorry?
30 years ago.
30, sorry. I'm confused by your contribution here. So 30 years ago, it was in 1994 exact, Peter Shor came on with a quantum algorithm that actually solve this factorization problem efficiently. So this means that this kind of classical algorithms are actually not secure against an adversary having access to a quantum computer. And when this is said, well, a natural question is, well, what kind of quantum computer do we actually need to be able to hack RSA? And well, this is a question that really depends on the platform that you are developing to get your quantum computer. And for example, if you say, well, I'm interested in developing a platform using superconducting circuits, which are driven by an error correction code called a surface code, and under some assumptions saying, for example, that all the operation, the physical operation can be performed with an error of at the level of 10 to the minus 3, and the stabilizer can be measured on the timescale of 1 microsecond, then you estimate that at the end of the day, it takes 20 million qubits and roughly 10 hours to factor a 2048 RSA integer. So this is a lot, but to tell you how big is this computer, you can say, well, if you look at the code distance of the surface code that is needed to be able to factor these large integers, it turns out that you can essentially do 10 to the 10 operation with a negligible failure probability of 10 to the minus 3. So 10 to the 10 operation is huge. And for example, if you say I want to get a GHZ state, it turns out that a GHZ state only takes a linear number of operations with respect to the number of qubits within the GHZ state. So it means that with such a surface code, you would be able to implement a GHZ state with essentially 10 billion qubits. So it's a really huge and really big machines, right? And we clearly don't yet have such a machine. But however, I would like to emphasize that this resource estimate strongly depends on the platform. And for example, if you say, well, I'm not really interested in this superconducting qubits, but I do prefer having a platform using CAD qubits. So these CAD qubits has the very nice property that they can be stabilized actively, so that at the end of the day, they exhibit a noise bias. So that you can get a quantum computer, a fault-tolerant quantum computer, by essentially using a classical error correction code. And in this case, you can very significantly reduce the resource that is needed to make this factorization problem by essentially a factor of 60. So you need 60 less qubits to do this factorization with such an architecture, for example. And you can also do similar estimate with other problems like computing elliptic curve logarithm, and it turns out that this is also slightly easier to do that than factoring RSA integers. In all these cases, you know, the resources is going down and down. And the question is, do we actually need to prepare already against this quantum threat? It might be the case in case you are dealing with high value information that you want to make, you want to have a very long-term confidentiality. And if this is the case, then you essentially have two possibilities. The first one is keep focusing on classical algorithm, but choose computational problem that you believe are difficult to tackle even when having access to a quantum computer. But the spirit is the same. At the end of the day, we'll have a security proof that rely on an assumption about the computational power of the ETH Zurich. So a way to get rid of this assumption is to go to a quantum setting called quantum key distribution. And here you actually have access to a true mathematical proof under a limited number of assumptions, and again, without the need to assume that you can bound the computational power of the ETH Zurich. So this is the topic of this goal, and let me quickly introduce the principle of quantum key distribution. So it essentially works in two steps. So the first step is a step where the two protagonists who want to exchange data in a secure way at the end of the day, Alice on the left, Bob on the right, they are in closed labs, but they're actually sharing a quantum channel, and they want to use this channel to get identical random bits that are unknown to the eavesdropper who might be able to fully control the quantum channel. And once they get this random bit string, which is known by them and them only, then they can use it to essentially encrypt and decrypt messages in a secure way. So the hard point is actually to get this key, and one way to get this key is to use a quantum principle that basically states that if Alice and Bob do appropriate Pauli measurement on a 2-qubit maximally entangled state, this yields results that are fundamentally unpredictable, although they are perfectly identical on Alice and Bob places. So this means that by repeating this measurement on 2-qubit maximally entangled state, they can keep the result and get the key. So now, how do you prove the security? Well, this is the point where Bell's work enter into the game. Because now, setting the security proof essentially rely in proving that Alice and Bob are actually sharing 2-qubit maximally entangled state. And it turns out that when focusing on the CHSH inequality, this inequality has a property called rigidity, stating that the only way to achieve the Tyrrell-Salt bound, the maximum winning probability of this game, is to have a quantum model where a particular state, a single state, can provide this maximum value, which is exactly a 2-qubit maximally entangled state with appropriate measurement. So the idea is to say, well, I'm going to construct my security proof with a Bell inequality violation, and if it's high enough, then at the end of the day, I will get a secure key. So this is probably the point where, I need to emphasize first that things have been formalized precisely by Nicolas and people around Nicolas already in 2009, where they succeeded to exactly quantify the entropy that Eve has on Alice outcomes as a function of the CHSH winning probability. And for example, in case of the Tyrrell-Salt bound, you see that Eve has full uncertainty about Alice outcome. So at this point, you may say, well, but look at this experimental implementation, which is represented in this slide. You say, well, what Alice is doing is that I'm here considering the case where the source is located at Alice place. And what Alice does, she actually measures half of the state produced by this source with different settings. So the result is that she's actually preparing various qubit states. And then these qubit states goes to the receiver, and Bob's measure these qubit states according to different settings. So an engineer would say, well, no need to have this source producing entangled particle. And you can certainly simplify this scheme by simply having a source that produces various qubit states that Alice will send to Bob, that then Bob will measure according to different settings, and then you will get access to a qubit way. So it was actually the exact protocol that Charlie Bennett and Gilles Brassard proposed 40 years ago. It's also the birthday of this fantastic work. And it is actually true that in this case, things would work as well, and you would be able to set a security proof under a number of assumptions that are all written here. I don't want to comment on all of them, but I just want to talk quickly about the last one. And the last one tells you that, yes, you can derive a security proof, but in this security proof, you do assume that actually Alice produce states, produce qubits in a well-defined state, and Bob actually measured these qubit states with well-defined measurement settings. So this means that, for this security proof to hold, well, you need an experiment that can guarantee that indeed what is produced in practice, what is measured in practice, is actually what is supposed to be produced, what is supposed to be measured. And this is where the interest of Bell's work comes in the sense that when the key generation is produced by means of an entanglement, then you can actually use a CHSH inequality and the CHSH rigidity I was talking before to essentially guarantee that actually the source is producing the desired state and the measurement apparatus are performing the desired measurement instead of assuming that this is actually the case. Okay? So this is the whole idea of device-independent quantum key distribution, where at the end of the day you get rid of this last assumption. So let me quickly discuss the protocol in a bit more detail. So how does, so it's made of two steps. A first step where you generate a raw key, and then you do apply various classical post-processing to extract a secure key from this raw data generation. So here is a scheme of the experimental realization. We still have a source, and ideally this source produces 2-qubit maximally entangled state, but this is not an assumption anymore. You just consider a source that produces pair of particles, pair of signals, one going to Alice Bob and the other one going to Bob's lab. And now the only thing that you want is that this source has a signal that let Alice and Bob knows that actually a signal at the, or two signals have been produced. And then in the next step, Alice and Bob, they close the lab, and then with measurement apparatus, they can choose settings, and for each setting choice, they get an outcome, which I consider to be a binary outcome. So in this particular setting, Alice have the choice in between two measurement settings that I call 0 and 1, and Bob have access to 3 possible measurement settings, 0, 1, 2. And the choice in the settings depend on whether they want to perform what we call a test round or a generation round. In the test round, Alice and Bob are going to choose setting 0 and 1 to perform a CHSH game. And at the end of the day, the CHSH score will help them to estimate essentially the quality of their device in the parameter estimation step. I'll be back on that in a moment. If this is a generation round or a correlation round, then they choose settings 0 and 2, which are supposedly settings that provide the maximum correlation in between the outcomes. Now, let me emphasize that when x equals 0, then Alice's device does not know whether it's a generation round or a test round. And this is actually very important because you could actually consider apparatus behaving properly in case of a test round and producing deterministic outcomes, outcomes known to the eavesdropper, in case of a correlation round. So this is actually not the case here, because we make sure that for setting 0, the apparatus themselves do not distinguish in between these two cases. And then this process is repeated n times to get access to essentially n measurement results that are kept to form the raw key. And then we come up with a series of post-processing. The first one is a post-processing which ensures that in case it passes, Alice and Bob has essentially the same outcomes. So it's called error correction. There is a validation step where we check that the devices are as good as expected. They produce a CHSH score as good as expected. And then there is a privacy amplification step where at the end of the day, Eve has essentially no information about the outcomes. And then you get security. So how do we more precisely build a security proof out of this? Well, what's nice in quantum key distribution is that the notion of security is precisely defined and quantized. And in particular, you want two things to be satisfied. One thing is what we call correctness. So you want that at the end of the day, the key of Alice and the key of Bob are the same. More precisely, we want that the probability for the key to be different and that the protocol succeed to be small. And I call epsilon correctness the upper bound on this quantity. But you also want the key to be secret. So you essentially want that the state that, the classical quantum state that Alice and Eve share is essentially an ideal state where Alice's outcome is uniformly random, and the state of Alice is a tensor product with this state, so that Alice can actually not do anything to gain information about Alice's outcome. And precisely you want this, the distance in between these two states, the actual state and the ideal state, to be small when it's multiplied by the the probability of the system not upvoting. In my talk, I will talk about the sumness parameter. The sumness parameter is an upper bound of the sum of epsilon secrecy and epsilon correctness, which also means that it's an upper bound on each individual parameter. Okay, now it turns out that you can prove correctness and secrecy separately. And how do we prove correctness? Well, we use an error correction code. How do we promise, how do we prove secrecy? We use a randomness extractor. So let me comment quickly on these two classical post-processing. The error correction first. Well, in error correction, things works as described on this slide. So Alice, she basically prepared a syndrome of a row key that she essentially gets by measuring the parity of some of her bits. And then she also encodes her string using a hash function. And she sends both the syndrome and the hash to Bob, which he used the syndrome to actually get a guess of Alice's string, given his knowledge about his outcomes and the knowledge of the syndrome. And then he computes the hash of the guess and compare the hash of the guess and the one of Alice. And the protocol aborts in case the two hash are different. So in practice, you have the choice, in choosing the error correction code that you want to use for doing this task. In the experiment I'm going to show you, we use code that has been provided by our partners in Lausanne, having several nice properties. And one of them is that the syndrome length is kind of minimum, not only in the asymptotic limit, where the syndrome length is essentially given by n times the entropy that Bob has on Alice bits, but even when you look at the statistical correction, they are of the order of root n. So it's really a frugal error correction code. Now for the secrecy, well, we use, as I was saying, a randomness extractor, which helps you to prove secrecy. This randomness extractor takes a seed, a uniformly random seed, a short one, and Alice string, and provide essentially a string on which Eve has no information. But it takes a quantity that is the smooth main entropy, the conditional one, of Eve on Alice string. And we're actually in a very general settings where we allow the eavesdropper to basically make global operation on her side information. We allow correlation in between the states that Alice and Bob share. We allow memory effects, into the measurement, so that the measurement can operate differently depending on previous result, for example. So we're not in the ID settings. And to bound this quantity, what we use is a tool that has been developed in Zurich called entropy accumulation theorem, which essentially tells us that this smooth mean entropy can be bounded by n time the entropy that pair round that Eve has on Alice, which is compatible with the CHSH core, plus a correction of the order of root n. And as I was saying in the introduction, thanks to Nicolas and his collaborator, we actually know how to bound the van Neumann entropy per round as a function of the conserved CHSH core. So this means that we get access to a lower bound on this quantity, and therefore we can use a randomness extractor as a way to amplify to this. So if you want to know the detail of the experiment that we were performing, we use what is called a Tention extractor. It also has several nice properties, and in particular the seed it takes is smaller than, say, others extractors. Now here comes a quick description of the experiment itself. This is, again, an experiment that has been developed by colleagues from Oxford. It is using two trapped ions platforms that are actually separated by 2 meters. The ions are trapped, cooled down essentially to the ground state before being excited by laser light, so that they emit photons with a polarization which is entangled with the internal degree of freedom of the atoms, of the ions. And then the photons are coupled into fiber to be combined at the local station where a Bell state measurement is performed. And the result of this Bell state measurement is that it projects the 2 atoms in a maximally 2-qubit entangled state ideally. So it's like an entanglement swapping operation where you start with 2 atom photon entanglement, you perform a Bell state measurement on the 2 photon, and this actually projects the 2 atoms into a maximally 2-qubit entangled state. Once this is done, then the experimentalists move on the ions by few micrometers once they get this signal telling us that the Bell state measurement was successful. They move on the ion by several micrometers to essentially disconnect them from the outside. And then they choose a measurement settings and they record the measurement result. What is the performance of this 2 platform? Well, it's shown on these 2 graphs. So here you have the CHSH core as a function of the number of friends, which here goes up to essentially 2 millions. Each point is an average over 100,000 points. And you see that the CHSH core is very high, 2.67, corresponding to a winning probability of almost 83%. And if you want to find out about the quantum bit error rate, the probability that the results are different given that the settings are the same, it's also very low, around 1.54%, and very stable, you know, among this over the ranks themselves. So with this in mind, we have a characterization of the setup itself so that we can set the parameter of the security proof. And by fixing the soundness parameter to 10 to the minus 10, we predicted a key rate that is represented here. And in particular, we look at what we would get by taking 1.5 million rands. We would have a key rate slightly lower than 10%, corresponding to a secure key at the end of the day, whose length is basically 100,000 bits. So this was realized experimentally. And here are the results. So the experimentalists took 1.5 million rands. We succeeded to... How long does it take to take this million? About 10 hours. Yes, so they essentially get 1 bit per second. And the post-processing is extremely quick. It takes about 5 minutes. So once they get this 1.5 millions run, we apply the post-processing I was describing before. We succeeded to essentially certify the secrecy of almost 400,000 bits. And from this 4,000 bits, we have to use almost 3,000 bits for error correction. So we were left with almost 10,000 bits, which is much higher than the number of bits that we needed to consume to perform the classical post-processing. So it's a successful demonstration of a key extension. Yes?
I'm surprised you have 1.4% error rate.
Yes.
Too bad. You still need 3/4 of the bits for error correction, but the error rate is not large.
Yeah, it turns out that what we corrected is the whole string that we get, including the one that we actually took for the test round. So, you know, this includes, yeah, and the reason...
Why would you do that? You don't need to do
well,
that.
the reason is that essentially the entropy accumulation protocol for applying the entropy accumulation theorem works this way. At some point we can maybe improve that, but this is actually the way the protocol works.
Okay.
Also, this is quite a lot, but we also make sure that the error correction that we used was, you know, made cleverly. It was really frugal in terms of the length of the bits that we were actually using. Okay, so at the end of the day, we were having this 100,000 bits, and we actually used them to encode an image at Alice's location, send it to Bob through a public network, which he decoded to essentially discover that the image was, of course, a picture of John Gale. So the details are published in this paper. Let me mention that colleagues from Munich, the group of Harald Weinfurter, together with Valerio Scarani and Charles Lim, also implemented a similar experiment reporting on device-independent quantum key distribution. In their case, they were using a different platform, neutral atoms, but the settings were essentially the same. The distance was larger. It was about 400 meters. However, in their case, the violation and the number of runs was not high enough to basically extract a key at the end of the day. So this essentially tells us, you know, the kind of challenge that we currently have in trying to set better security proof, you know, to essentially go to longer distances, so essentially to achieve better key rates. And I would also like to mention efforts from the group of Jan Wei Han to make such an experiment, but with photonic devices. I'll be back on this point in a second. Now, actually. So you might have heard that, you know, to perform a Bell test properly, then you can also use photonic devices. And in particular, you can simply use a source producing entangled photon pair in polarization and say simple polarization measurement. And, well, several groups succeeded to perform even loophole-free Bell test in this setting. And I feel, or I think it's fair to say that these kind of experiments are way simpler than experiments involving trapped ions or neutral atoms that you need to cool down very efficiently, to trap efficiently, and so on and so forth. So one of our goals is to try to make a device-independent quantum key distribution with what I do consider are kind of more practical prototypes. This is actually challenging for several reasons. One of the reasons is that actually the tools that are currently available in quantum optics lab are not sources producing 2-qubit maximally entangled state. The statistics is more complicated than this, and when you actually account for the real statistics, you see that the maximum CHSH core is really limited even when you optimize everything, even when you have essentially no noise in your experiment. So this is going to be challenging, and what we are essentially doing is to try to find tricks, to try to see whether it would be possible to implement device-independent QKD in this setting. I would say that so far it is still challenging. So for example, in this graph, we account for a detector inefficiency here. We also account for finite number of runs in specific settings associated to collective attack, and we included errors that we here quantify as the visibility of the non-local interference that you can get in this photonic device. And I don't know, for points where you would have access to an overall detection efficiency around 88% and a visibility of higher than 99%, you would essentially need 10 to the 12 runs, and I'm not aware of any experiment that can essentially achieve this parameter yet. So there's still a lot of work ahead, I think, before we can implement an experimental realization of device-independent quantum distribution. So here comes the end of my talk. Yes, I was celebrating Bell's contribution to QKD, and at the same time mentioning also the birthday of several important papers in this field. Of course, your paper, Gilles, the paper of Peter Shaw, who kind of helping very much in selling QKD devices. And yes, with this, thank you very much.
Thanks a lot, Nicolas, for the very nice presentation. Gilles.
Well, first of all, let me say it's totally amazing. It was a really, really fantastic work and talk, both of them. I have one comment to it. One comment is that it may seem that at the moment, at least, the distance between Alice and Bob is not so great. However, the very first experimental BB-84, which I did with Terry Bennett and 3 students in 1989, the distance was 30 centimeters.
Right.
So we went from that, not us, of course, who are not experimentalists, but from our ridiculously small distance, the world went from there to 1,000 kilometers. So there's hope for you as well, from this point of view. The other remark I want to make is a bit more historical. Could you show us again the slide in which you compared BB-84 with Eckert?
Yes.
Yep, this one, that's right. So indeed, in response to Eckert 1991 paper, Bennett and me with David Merman wrote a response the year after in 92, in which we explained that Eckert's idea of using entanglement in Bell's theorem was, in a sense, not true, because we could do it with Alice making the entanglement, and when Alice measures entanglement, she prepares photons, and she might just as well prepare them and send them to Bob without any need for entanglement. So the fact that entanglement is not needed is not so dramatic, but at the same time, Bell's theorem is not needed either in Eckert's original version. Now, the remark I want to make about this is that Eckert's version 1991 is not exactly BB-84, because he used 3 bases, 3 different measurements on both Alice and Bob's side. And if you want to, whereas BB-84 is only 2 bases, but if you want to use Bell's theorem, even whether it's true or not, but if you want to use Bell's theorem, you cannot do it with sigma x, sigma z. So on this slide where you have sigma x, sigma z, that does not give rise to Bell's theorem. You really need to have other measurements.
I have a comment on the fact that you implemented this. I'm also not an experimentalist, but I'm sure I could have hacked your scheme.
Oh! Our original implementation was so-called provably secure against any eavesdropper who's deaf. Because the biggest part was the power supplies. Power supplies make noise, and we use these power supplies to activate Pochel cells or Wilson prisms to rotate polarization, and that works at 1,000 volt range. So you could actually hear the photons go by, and zeros and ones did not make the same noise. So we did not need Vadim Makarov to break our system.
Yes, that's precise. Okay, more questions? Yes, Howard?
There's no one. Okay. Could you say more about why, in the photonic case, it's difficult to get the CHS H parameter above
2.4 or whatever the bound was. What is actually the physics?
Yeah, it turns out that the problem is the photon statistics. So, you know, in spontaneous parametric down conversion, what you actually get is most of the time you get vacuum. Sometimes you get one photon pair, but sometimes you get also two photon pairs. And, you know, ideally you want to get rid of the zero photon contribution by pushing the intensity of your laser.
Well, you don't get rid of it.
Yeah, you never get rid of it, but you essentially increase the probability for having a single photon pair, but at the same time you also increase the probability of having two pairs. And together with Nicolas and Pavel, we actually did the job of optimizing the pump power, but also optimizing the number of modes that goes out of the source, of course optimizing the settings. And what we observe at the end of the day is that the CHSH4 is limited, whatever you choose as a parameter, due to essentially the statistics. Yes.
So you're saying that's really a fundamental bound?
Coming from the statistics produced by SPDC source, yes. So we did not assume any form of noise, you know, no DACOMs.
So you can't just take the count rate down to something, you know, which may be useless for practical QKD.
Most of the time you will have vacuum, and vacuum will provide no violation.
Didn't we assume that it would be, I don't know, 1 bit per second or something like that?
Assuming, yeah, are you restricting
I don't
to
remember
practical
exactly,
rates?
but I think we had such an assumption.
So I'm here.
Minimum rate, because indeed, I mean, Howard is right. If you lower the pump laser to almost zero, then you got essentially a key vacuum, but that doesn't contribute. But
it doesn't. That contributes to two, you know. Yes.
No, if you have perfect detector, you never see them.
But then you open the detection hole.
Yeah, so you don't discard this, you keep them, and this is one event that you keep. And this event provides you a violation of two.
Detection loophole is when you get an event on one side but not on the other side. If you don't get an event at all, that doesn't open.
No, but here the event is triggered by the source. You know, I come in with my pump laser, and this triggers the event. And then I get the event, and I keep it. I don't have to post-select it.
No, if you have vacuum on both sides, you just decide that if you don't get any photon, you output +1. It's a systematic.
Right, and you get
and
two.
then you saturate.
You can saturate two.
Then you need a little bit more.
Yeah, and this little
but that is what then reduces
exactly.
the value here.
So whatever you do, I tell you that you're limited to 2.35.
Okay, now
anyway,
2 point what?
2.35 exactly, if I well remember. Yeah.
That's amazing.
I have just a comment because you asked before about this additional noise in the error correction, that it's higher, where you said that all the test rounds are there. And actually what one can say, at least from the theory perspective, is that asymptotically, these two first orders, so to speak, like this doesn't matter because you can always introduce additional random bits into the raw key bit, and then the error correction corrects them out again. And that's basically what happens. So you introduce things that are not really correlated, and the error correction just gets rid of them, and so the net effect is zero. And this just makes it easier for the analysis because these additional test times may still be correlated to stuff. So that's the reason. So it's not a big loss, maybe, I mean, on the finite size level. Okay, more questions? I think we are exactly perfectly on time. Thank you very much. Great, thanks a lot again.
So what's it coming from?
You say that whenever we get
dello stato che ho fatto. Adesso
Pardon? L'enregistrement, ça suit.
I assume that this is not very powerful. So like yesterday, I was writing to him. Yes, I was the first of
Aggiungi il gruppo al gruppo che ho creato. Ma che cos'è il gruppo? Infatti per me chi mi hai messo? Messaggio lo metto. C'è l'unico di questo, non l'ho messo su materiale è un po'
Ho detto che io che
sto dottor lì ma che sono pazzi, non problemi per adesso. La gente non sta bene. No. Io non dico proprio un'altra storia, ma quella è un'altra storia. Non so vede adesso la neve.
So there is this very powerful lens that says, okay, if I have a channel, typically you're interested about
Good. Okay, everybody, welcome back to this short evening session. Emerging at least marginally less ignorant. Otfried will kick us off. So. Okay, go ahead.
Yeah, thank you very much. Yeah, thanks also to the organizers for giving me the opportunity to speak here. It's very nice here, and I didn't expect snow. We just had a nice walk, and it was quite feels a little bit like Christmas. So I will tell a little bit about quantum networks, or about our recent work on quantum networks. And I should say that this is work done together with many people, and I think. So mainly from my group. So this is Sophia Denker, Chiara Hansen, Einbrenner, all PhD students in my group. Tristan Kraft was a PhD student in my group. Zhenpeng Xu was a postdoc in my group. Jan Sperling is from Paderborn, and I will also present you some experimental data. And these are the experimentalists. These are Benjamin Brecht, Nidin Prasalan, and Christine Silberhorn, all from Paderborn. Good. So here's also a picture from some of people. This is Chiara, this is... So, I will talk about quantum networks. And you may ask, okay, why are networks interesting at all? Yeah, I mean, I don't know. Yeah, also, yeah. I mean, just to give you a simple example, that there can be some surprising properties of networks. I will just explain you shortly a very classical model, actually by Erdős already. So you just take a simple network model where you just have a bunch of nodes, and there are a lot of possible links, and each link occurs with a certain probability p. And this gives you essentially a probability distribution over graphs. And for instance, one example could be this one, which occurs with a certain probability, and each link could be. And now you can ask some natural questions about this. You can, for instance, ask, what is the typical path length between two nodes? And actually, it turns out, for this simple model, that it's typically quite small. So if you take two random points, or the maximal path length between these things, it typically scales logarithmically, yeah, with the number of nodes. Which means that actually, so if you have just a model and we have, I don't know, 5 billion people in the world, and essentially the people, that's the probability that you find a path for friendships from one person to the other, that this path is typically pretty small.
That's independent of P. That's independent of P?
Yes, but in principle.
Or P not being 1.
Yes. So, then you can ask, is there something what people call a giant component, which means you look for the largest connected component, here are the red ones, and you ask what is essentially the probability of a node to belong to this component. And essentially one can show that there's something like a phase transition, if p times n minus 1 is larger than 1, then there's a probability essentially goes to 1, and the giant component fulfills entails the entire network, and which means that this is actually quite a weak condition if you think about it, because each node has n minus 1 possible connections, and if n minus 1 times p is bigger than 1, this just means that each node has at least one connection, or probability of one connection. Having one connection is yeah, but this is completely classical stuff, and actually this is already known since the 50s. Yeah, now, why? I mean, of course, I'm not really working on that, but we are working on quantum networks. Yeah? And what is here the picture that we have in mind? It's something like, we have something like a network of nodes, yeah, with some physical links. Yeah, this could be something like we have 6 nodes here and with some physical links. And across these links, you can distribute some entanglement or create some entanglement. It might be by some fiber or whatever, yeah. So you try to distribute some entanglement states here between these links. And of course, typically, this only happens with a certain probability. Yeah, because the photons get lost or the parametric down conversion is not successful, whatever. Yeah, there are different things that can go wrong, but this happens with a certain probability. And now you can ask natural questions. Yeah? So you can ask, okay, what happens in such a scenario? What are the typical quantum correlations that can arise in this network? So if you have, for this structure, which quantum states can you prepare, given certain operations? Yeah? Or you can ask, is this useful for long-distance communication? And what are something like key rates if you want to have some from here to here? Yeah, I mean, of course, depends on the topology of the network and so on. And I should also add, because we are here in a workshop in the memory of John Bell, that of course we have also looked at similar models to study non-locality, where essentially somehow you essentially distribute some hidden variables across some links and ask what type of classical models arise. As I said in my talk, I'm not talking about non-locality, quantum mechanics. Yeah, so but this is definitely a valid question. And it's quite related, some techniques can be used in both systems.
Okay, may I ask a question about how the previous slide relates to that one? Because if I think of this practically, that P is the probability that I actually can establish a link.
Yes.
Then isn't it like if I would scale this up to the whole world, I wouldn't expect the P to be a constant, but rather a P divided. I mean, in a sense, if P is the probability that for a possible link, that link exists, and let's say it's 1%, then if I go to the whole world, this would be many links I will have to try to establish. So I'm just asking, is it natural to
Sorry, I was just a little bit confused.
Okay,
yes.
so yeah, the question is it natural to assume that P is fixed and then one varies N, or should one think of P as something that scales down as I increase N?
Yes. Typically, and also, for instance, if you look in these books, yeah, they typically call this number C, which is just the number of average neighbors that a person has.
Oh, okay. So it's this number that.
Yes. So typically, you consider parameter C, which is just this product.
Okay. So that's what I instead capture by this.
Yes,
parameter.
of course.
Okay, perfect. Yes.
P should maybe go down because otherwise every person will get a lot of it. Yes. Good. So, yes. So this essentially now brings me to the two topics I want to talk about. So in the first part of the talk, I will talk a little bit about network entanglement, meaning I consider such a network, I restrict my attention to a certain amount of local operations, and then I ask which types of entanglement can I generate. And in the second part, I will talk about a project which is about topology detection of networks. So you ask, okay, you have something like a network, but you do not know among which links some states are distributed. The question is, how can you find this out? And which links are working and which links are not working? Or whether the multipartite states are distributed. Okay. So let's start with the first thing. Let's start with the basic notions of multipartite entanglement. Yeah, so typically we have some things like Alice, Bob, and Charlie. They share some state, and there are different classes of states that you can look at. You can, for instance, have something like fully separable states, where everyone is, well, it's just separable, it's just boring, I would say. You can have things like biseparable states, where just two parties share some entanglement, and the other one is separated. And if this pure state is not of this form, one calls it genuine multipartite entangled. And two states, which are actually also occurring later in this talk, are something like the GZ state and the W state. And there are many other cluster states, whatever, which one can think of, but I won't go too much into detail now. Then, if you consider this scenario, what I explained, this is really appropriate for networks. And this maybe gives you another idea how you can try to characterize entanglement classes in networks. That you just say, well, okay, I have my network, and if my state can be prepared by two particle sources only, and then of course it can be a network. But on the other hand, you say, oh, maybe then it's not really multi-particle entangled, whatever that means. If you use this definition, you have to be careful concerning the local operations that you allow. Because if you would really allow something like local operation and classical communication, you can do everything. Because you could have just the following scenario, where one party essentially shares some Bell state with all the other parties, and essentially then this party can prepare some local state, and by teleportation, distribute it to all the parties, and then you can create everything. Yeah? So that's why one has to be careful. Yeah, if you just essentially start with this definition, you have to restrict your local operations in some sense, otherwise it's a trivial definition. So that essentially brings up the question, where you can ask, oh, can a state be prepared using local operation and shared randomness? Which means no communication allowed. The motivation for not allowing communication can maybe, okay, you can see it from a fundamental point of view. You can also see it from some practical point of view, because if you have some communication in a network, you essentially have to wait for the results of the communication, which means that you need a quantum memory. Yeah, and this, of course, is something like an extra thing that you need. And quantum memories are not so good, so that's maybe where you want to avoid this. So, what does this definition mean in practice and mathematically? So we ask you the question, you have some, well, this is the simplest triangle scenario, you distribute some bipartite states here, and you have some shared randomness and lambda, and then each party can make some local map applied to these two qubits or two particles that the party has. And yes, and then you ask which states can come out. And for instance, you can ask which type of 3-qubit states you can do with this thing, where, for instance, still the dimension of these guys might be unbounded. And you can write it more formally. Yeah, you can write something like that you start here with distributed source states, then you do some maps, which occur with a certain probability according to this distributed randomness, and you can ask which states can be prepared in this way. I should stress that this, of course, was not a definition invented by us. Then, well, you can do some more general things, yeah, so you should do other scenarios where you distribute, so on, which maps are allowed, and so on. One very small thing, I should of course say that this notation may be a little bit confusing because this tensor product refers to a different bipartition than this tensor product. Yeah, so because this is depending on the parties. So, some remarks. So first, in this picture, you do not make any restriction onto these distributed states. So they can be high dimensional, but you're asking, can we in the end have a small dimensional qubit state? Yeah? The randomness I put here now, that the channels essentially depend on this randomness. Yeah? Actually, you could also put it on the distributed states. This is mathematically completely equivalent. Yeah? So this is essentially not a big distribution. With this procedure, you can generate genuine multipartite entanglement. So it's definitely a different definition. But also you see essentially from this definition already that this is something like a So how can you tackle such a nonlinear problem? Well, the typical idea if you have some nonlinear problem is to go to more copies. And this can be done, and this is using a technique which is called the inflation technique. The basic idea is the following. If I can prepare something in a network, then I can of course do two copies of a network. And two copies of a network, I can wire them different. So, for instance, let's assume this. I have here the state rho that is essentially just prepared by such a network scenario. Then, of course, I can take two copies of this network. And I can also take essentially such a configuration, which is something like 2 copies of the network, but here this source state are wired differently. Yeah, and definitely, if I have to have such a technical procedure, I can make this thing and I can make this. What's the point here? The point here is that these states have something in common with this state. Yeah? They share some marginals. For instance, here, I mean, this is my state. Of course, here, obviously, this reduced state on ABC is still the old state. And also on A prime, C prime, B prime. And if you compare these two things here, then there are also something in common. So for instance, first, these reduced states are the same. If I just have this, what's happening on this yellow line is what's happening on this yellow line. But what is more interesting is that here, for instance, here this reduced state between C and A prime is just this blue line, corresponds here to the reduced state between C and A, and not C and A prime, because they're wired differently. So you have a bunch of constraints on these reduced states, of a reduced state rho, tau, and gamma. And due to this rewiring, you essentially also swap some indices. And this means now you're having essentially the following problem. You have been given a rho. You ask, okay, is there some tau and some gamma, some quantum states with certain properties? And these are linear properties, and actually this is in a semi-definite program. So I try to solve it. However, there's a problem. Actually, this scale is quite bad. Yeah, so in practice, it doesn't really work. Yeah, so if you want to go somewhere to 4 or 5 qubit states or prove something, it just doesn't work the same, because the dimensions. So the question is, can we do something analytical? Can we derive some analytical criteria for that which work for arbitrary number of qubits and so on? And I will give you just a simple example that you can do something. And for that, because I want to make it as simple as possible, I look at the cluster state, because it's actually simpler than for the jet set. So what is the cluster state? I mean, maybe some of you have heard this already, but just to give a simple the cluster state essentially is a 4-qubit state. It looks like that. And you can write in different bases, one seems like that. And the useful property, what we need, is the following, that this is an eigenstate of certain operators. And these operators are essentially tensor products of Pauli's. Yeah, you take, for instance, x here, z here, and z here. And this guy is an eigenstate, well, okay, it's a slightly different basis, but of this operators and of this operators, we essentially take always x here and z in the neighborhood. And of course, since this is an eigenstate, it has expectation value equal to 1. And of course, it is also an eigenstate of the products. Yeah, because, I mean, naturally. So, well, if you have a cluster state, you know the expectation value, and you know it's an eigenstate of the product. And what is important for us is the following. That if you take, for instance, something like a product where you have x, z, z, and x, z, z, G2 and G4, then these z terms cancel. If you take a product, you get something like just an x and an x. So it's actually x on 2 qubits only. So how can we use this? Well, let's write down now again the inflation, and let's write down up to the 3rd order inflation. So we know that if this state is a network, we can write down this state, and we can write down this state where we actually did 2 of this rewiring. Now let's look at this state here. We have, for instance, something like an observable A1, which is something like an x on a D and an x on a B prime. And if I just take B double prime and D, this of course corresponds to D and B here, because I trace out all the rest. I have also some observable where I have something like an Z here on D, and the Z on B prime and X here, so this is this thing. But this violet-blue leg, somehow, this also corresponds to this here and so on. So what do I mean here? I have a bunch of observables, which actually, they have actually, if you see on D, on the qubit D, they have an X and a Z and a Y, and otherwise they do not overlap. And they essentially correspond to some observables that also exist on rho and on tau. What is the interesting property here? The interesting property here is these guys on this state anti-commute, because they have this X, Z, and Y on this qubit D. On the other hand, if I look for this corresponding states, the observables on rho, they commute because they're part of the stabilizer. And this is, in some sense, a contradiction, because for anti-commuting observers, we know that the sum of the absolute values, the expectation squared is smaller than 1. On the other hand, because they are stabilized, all of them have, the expectation of all these guys have to be 1. And from that you see that you cannot work. And you also get something like an inequality. You can say, look, if a state can be prepared in a network, then this thing must exist. And you can write on this observed, the anti-commute, it's have to be smaller than 1. But here they commute, and for the cluster state, we would have on the one side 3. And now, when you have the trick, you can use it for a lot of other states. Yeah. So, and then, okay, then I will not explain the details because it's getting technical. Yeah, you can use it for the GZ state, which is actually a little bit more complicated, but you can get some. Well, actually, you can use it for any graph state. Yeah. Okay, that is getting complicated a bit, but you can essentially use the same tricks that I used for any graph state. You can use it for GZ states, and you can also get some fidelity bounds. Yeah, because essentially this stabilizing operators tell you also something about the fidelity. Finally, you can use it for other state with symmetries, for instance, like bosonic states, states, or this W state that I had on my slides before, and it also doesn't work, and you can essentially prove that you cannot generate any entanglement in this subspace. Okay, good. This was the first one. If you have questions, you can directly ask them. You can also ask later. Let's come to the second part. This is about what we call topology. And the question is very simple. Let's assume you have an A-type network, and there are some sources distributing some states here. And you just want to find out which configuration the sources have. So is it true that I maybe have something like this 4-bipartite source here and 2 bipartite sources here? Or is it true that maybe I have a tripartite source here, tripartite source here, and bipartite source here? And you want to know essentially what is the structure of the network. This has been mentioned in some earlier works quite recently, but mainly only for pure states. Yeah, and which is not really relevant for an experiment first because we just don't have a pure state. So let's be a little bit more concrete with an example. So this is your network, you don't know what's happening. And let's assume, maybe for simplicity, that the sources distribute GZ states. Yeah? This is just. Essentially, then you can have different configurations. Because you can have something that is something like this is a complete GZ state. You can have something, there's a 4-qubit GZ state between these nodes and a 2-qubit GZ state, which is a Bell state here. You can have a Bell state here, and a 4-qubit GZ state here, or you can just have Bell pairs. And of course, there are a lot of other configurations, but now I'm just looking at these because these have been later discussed in the experiment. Yeah, in principle, you can do. So, why is one interested? Yeah, I mean, in a real scenario, you may just want to check the quality of the distributed state. You want to have something like a test which tells you, okay, between node 1, 6, and 5, there's a GZ state, this is fidelity. Yeah, this could be. You may also use it as something like testing the network, or where something like a provider promises you that he can generate some entanglement between 1, 4, and 7, or whatever. Yeah, that you want to somehow configuration. And in principle, it may also be something useful in some cryptographic setting, where you maybe have some corrupted nodes and so on, and you want to still prove that between some nodes there's some GZ state with fidelity, which you can trust. So, how can you try to do that? Well, I mean, naively, you would maybe just do global state tomography. But actually, this is very costly and not clever. Yeah, so if you look at, okay, maybe I just estimate the fidelity of this graph state, of this state, and Bell state, and whatever. I mean, there are tools how to estimate the fidelity from few measurements for a state. But if you look, actually, they typically work only for one state. Yeah, I want to have this target state, and then there's a protocol how to estimate this fidelity. But in principle, yeah, here now we have a set of states and we want to estimate all at the same time, not separately. And finally, of course, if we really want to do something like a proper test, we need something like a hypothesis test that really tells us a p-value. So we have a certain experimental set of data, we have a certain hypothesis, and we can reject this hypothesis with a certain p-value, depending on the proper statistical test. So, what's the idea here? The idea essentially comes from the fact that if you look closely at the GZ state, how you can determine the fidelity of a GZ state, it's by far not unique. What do I mean by that? So, if you want to measure the fidelity of a GZ state, actually one can show that this is more or less something like, you can decompose it in this way, in the following things. These are just the diagonal terms, and you have these off-diagonal terms, and you can write them in terms of Pauli matrices, the X matrix, and you have some measurements in the X, Y plane of the Bloch sphere, which you repeat on all the qubits. Now you either make this Y measurement, the X measurement, and something in between. Yeah, and from this one can just show that essentially if you measure these operators, it's just equivalent to this operator. Now if you measure the 3-qubit GZ state, you can write it like that. And at first sight, you may say, oh, well, that's a bad thing, yeah? Because somehow here, I have different measurements than here. So for checking the fidelity of a GZ, 3-qubit GZ state, I have to make different measurements. But if you play a little bit with the coefficients, you realize that's not true. Again, no. So, because here you can also write this, actually you can expand it in the same basis here, but with different coefficients. Which means the following: by just measuring these measurements, you can not only measure the 4-qubit GZ fidelity, but you can also measure the 3-qubit GZ fidelity on all the reduced states by just making some post-processing with different coefficients. And this essentially gives them just the recipe. So what do? You make all the measurements for the largest possible GZ state, yeah, which are essentially measurements in the XY plane and with a certain angle. Actually, and then you can use this data to check the fidelity of all smaller GZ sets on some reduced states. And from that you can calculate the fidelities, and then you can also formulate some hypothesis tests in the space of all fidelities. So you have to be a bit careful how that you make them exclusive, the hypothesis. And finally, you can estimate then the p-values of all these hypotheses via some test. Okay. Let's come to the experiment. Of course, I'm not an experimentalist, and I apologize for that. Yeah, so well, I try to explain. I mean, how to make GZ state in an experiment? Well, typically a thing, what people did in an old experiment is the following. You essentially prepare 3 EPR pairs, you let them overlap at some polarizing beam splitters. If you have 6 photons here, then essentially you have something like a GZ state. This, however, is not very efficient. Because in order to make here a perfect overlap, you have to prepare these 2 EPR states in the same time slot. And this makes the rate going down quite drastically. So how can you improve that? Well, you can use essentially something like a quantum memory. And this is an idea from Christine Silberhorn's group in Paderborn, where they did GZ states, but with a time multiplexing. So essentially the photons arrive at different times, I should stress this. And maybe it's best to see, well, if you start here. So this is essentially the time. So that generates some bell state. And, okay, they detect one of the photons. And if they detect a photon, then the other photon is sent to some storage loop. And then they wait. This is, well, okay, not very long, yeah, it's not so, but then it's in a storage loop. And then at some time step later, the second bell pair is generated. And again, they detect one photon, and they know, okay, now the second pair is detected. But now they essentially can, the second pair of photon comes in, and they can, for instance, let it overlap here with the photon in the storage loop, detect one of it, and put the other photon here inside, which essentially corresponds to an interaction between these 2 photons. And then they can wait even more for something like the third thing. When the third Bell pair comes, they detect it and let it interact with the remaining photon here, and finally they detect both of the things. Which means that essentially with that you have something like a 6-photon GZ state. But here it's not important to do photon pairs at the same time. Yeah, because in principle, when this happens here or one step times with L, it doesn't really matter. Of course, you should not wait too long because at some point the photon is lost in the quantum memory. But well, in principle, that's all. So, how can you use this now for our experiment? Well, the point is that we can use a similar thing. But in each time when the second photon of pair comes, wait, no, here, so we essentially can make a decision because we can let them interact, or we can change our setup that they don't interact. Yeah, and actually this is just a reprogramming. It's actually not really a new setup. And depending on that, we either get 2 independent Bell pairs, or we get a GZ state. And again, here, we either get a 6-qubit GZ state, or we get 3 Bell pairs, or either we let them interact or not. And this gives us, in the end, something like 4 possibilities. So the first part, you always put it into the storage loop. You always swap it. But then you can essentially decide whether you want to or not. Or in the third thing, you can again let it interfere or not, and this then gives you essentially all these possibilities that you can have. Yeah, and in the end, you get something like 4 possibilities for GZ state distributions,